This college calculus course is different than other college calculus courses. Like many other ones, you will be learning all the concepts from an experienced university professor. But in this course, the instructor, Ed Pratowski, will also show you how to implement all the concepts in Python. This course is for everybody, but especially those interested in computer science.
Welcome to Calculus with Python. In this course, you're going to learn how to write Python code to do your calculus. And that's going to save you, pages and pages in your notebook, a lot of time. And we're also going to look at the calculus so that you understand the math. And then when it comes to doing the calculations, finding that answer, instead of spending all that time writing out all the factoring, it might be like one line of code in some cases. And we'll look at how to set up your Google Colab notebook so that you can use this in the future and set up, oh, I have this sort of situation. I know what to do. Organize table of contents in my Colab notebook. Go right there. Boom, boom, boom. Solve. And so really then you can concentrate on a lot of the applications. And some of them, it might involve setting up a more complicated formula. You can spend your time with that so that when it comes time to doing the solving, you can say, okay, I'm going to type this in here and run it and get my answer. So it'll be really exciting. We'll look at a lot of the applications and a lot of good things you can do with calculus and with Python. This will be like the springboard for even more complicated math that you could do in the future. So enjoy, and here's Calculus with Python. To start talking about calculus, we first need to talk about limits. And this is going to come up in terms of how we get from our algebraic way of thinking to calculus way of thinking. So let's start with a simple limit. We'll just briefly talk about this. Something I can remove. So if I have a hole in the graph, what's going to make a hole in the graph? Well, remember, limits come up. If I can't have a certain x value, then can I get close to it? Then what's my y value if near that x value? So if I have, if I look at this, x can't be 2. Because that would make the denominator 0. So I get y values, but around right where x is 2, because that can't happen, there's going to be a problem. Now, this is what makes a hole in the graph, because you might notice I have x minus 2 in the numerator, and I can cancel that out. So then I really am graphing what looks like y equals 3x. Now, given that, now I have no problem. X can be 2 because I cancel that out, I have no denominator. But the limit happens when that was there in the original and then it canceled out. So it can't be exactly that value, but it can be really close. So what we have is, if I graph that y equals 3x, there you go, that's what my graph would look like. But only exactly at that value, or x equals 2. Most graphing utilities, you're not even going to be able to see this, but if I was drawing this out, I'm going to really exaggerate it. When x is 2, now this works. 2 times 3, y is 6. So at that point, 2, 6, I'm going to really exaggerate it, and there's a hole in the graph. Because this is the limit. What would the y value would be 6, but approaching from either side, but it just can't exactly at that value exist. So I have a hole in the graph. And these are some of the themes, we're going to look into the code for this, just a little bit to kind of prove this theory, a little bit of how to get to this, even if I didn't notice what canceled, things like that. And then we're going to build upon this, and we're going to see how limits, and especially this notion of being able to cancel something out, like that doesn't exist, that x can't be 2, but I can cancel that out. And that's going to be a key feature in the development of calculus. So let's just take a look at a first thing in our Colab notebook and how to demonstrate this with code, and we'll build upon that. So let's take a look at the code. So here we have our equation, and we see that x minus 2 would cancel out. It'd be y equals 3. but because it's there in the original, x still can't be exactly 2 because that would make it undefined. So what we're going to look at here is, we can do that, we can picture that, but just as a method for whatever other equation comes up, I'd have this set up, any given x value, and then h is what I'm going to use for that value of something, a little bit more, a little bit less. So h is that little difference here. And so approaching from the right, I made my variable y right. I'm just plugging in x plus h here. 3 times x plus h minus 2 for the numerator, x plus h minus 2 in the denominator. And from the left, so then it's going to be a little bit less than that value, x minus h. And that's what we have here. We want to set this up that, if I want to test something out without graphing it, approaching from the right or the left, I can just set up, any given x value and an h value. And then I'm going to print out these two values here. Both of them would be 3 because that's how it would work out. And I even put this if statement in here, supposing it didn't work out, rounding it. If they were not equal, then I'm going to say the limit does not exist. And that way I can try this with other equations. I can put them in here. I can, try this at different x values, different h values. And, that's really what we want to see, that from the right and the left, they're exactly the same. So the limit would be 3. And, it's only exactly at that one value when x equals exactly 2 that would not work. And we'll see how we get some other applications where sometimes this doesn't match up and it's more than just a hole in the graph. Here's a limit problem where we look at the denominator can't be 0, so x can't be 2 because that would make that 0, or it can't be negative 2. And so we'll put these, if I was drawing out the graph, I'm going to put these dotted lines here to show it can't be 2, or therefore no y values associated with that. And these are asymptotes. So vertical asymptotes for that x value cannot exist, and so therefore no y value anywhere near there. So if that can't happen, if x can't be, let's just concentrate on the 2. If x can't be 2, but it can get really close. So x could be, let's say, like 2.001. Really close, approaching from the right. Or it could be something like, x equals 1.999. Again, really close, but approaching from the left. So one of the ways to calculate limits is to plug in, really close approximations and see if they match up, or, what is the trend. And yes, that would still be the go-to method even if I wasn't doing this with code, but since we have the code, we're going to show how to plug in these values and even like really, really close approximations and see what we end up with. And then we'll see, the behavior of the graph as it approaches that value from the left and the right. So let's take a look at that in the code. Let's set up a system where we can look at this and find out where this is undefined. I might see this and say, okay, really this is going to come up when I have a denominator, because we don't want that to be 0. So I can just take an example like this, and I'm just going to look at the denominator and set that denominator equal to 0, x squared minus 4. So I'm going to put that in here as this equation. And we'll work through this one for all the examples. So finding out if that's 0, now we get into, I'm going to import Sympy, symbols, and solvers. And then I'm going to define my symbols. All right, I'm just using x, so I only need to define that. And there's my equation. I'll just call it EQ. And I'm just looking at the denominator. So I want to solve it equal to 0. Actually, that's really like the go-to for Sympy. Everything, we want to set this equal to 0. So here, what I'm going to do is, notice what this will do. And there we go. So we solve this, there's my equation, and again, Sympy expects that whatever I put in here is set equal to 0. So when I solve that, that's what it's doing. It's setting that equation equal to 0 and then solving for x. And so then I have my two x values. And I like to just leave it like this. There's other ways you can do this, and you can anticipate this and like store these as a list or an array. I could output just one of the numbers, not the other. For right now, this is actually going to serve our purposes much better. I want to see what equations I get. Do I get, I would expect that I would get 1, but maybe you do this for 1 and you try it and you get, oh, I thought there was a value, and you get no answer. That could happen. Or I could get 2 or 3. We're setting this up that I can find all the places where it would be undefined. And in this case, I get 2, x equals -2 and 2. So I'm going to keep that and then run the next code block. Now I want to approach from the right and the left, keeping the same one. So let's start with this. I'm going to say, let's just say that this one here, 2, as an example. And we're going to change our h value. All right, that's probably close enough. So let's just leave it at that. 0.001. I just put this comment in here just to remind us that that's the one we're doing here. And approaching from the right, you see x plus h, and approaching from the left, x minus h. Really, the key thing here is just to make sure you get all the Python notation and your parentheses correct, so that you're actually graphing what you're expecting that you're graphing, or checking what you're checking. This is all doing all this without graphing. So then I'm going to print out, well, what is the limit as it approaches from the right or the left? And I threw this in here. If it's not equal, then say that the limit doesn't exist. So we're going to pick that one, and we're going to do this, and we see what happens. As it approaches from the right, the x value gets really big and positive, or the y value gets really big and positive. From the left, it's really big and negative, totally different, so we're going to say that the limit does not exist. And you see, what I can do then is I can test the other one. The other one was -2, all the exact same thing. I just change this to -2 and run it. And you see very similar results, but it goes in the opposite direction. So these are the things we're trying to piece together. Yes, I could certainly just like plug this in and graph it, but this is part of calculus and some other applications. Maybe I need to know, does the limit exist at this point? Or I need to know what about the trends, and maybe doing this without graphing, maybe that's something important that I want to know. So that's the idea. Does it exist from the left or the right? And just as an example, simple example to compare, nothing canceled. I can look at this right away, y equals 3x, and see that, there's nothing going to make it undefined. I expect that to be nice and continuous. So doing the same thing, okay, I can pick any x value and just approaching from the right or the left, and then let's print it. And we see, taking all these decimal places, it's this, but really if I round it, I find that the limit is x equals 2. There we go. So that's really what we want to do. Be able to test any point, where is it undefined, and then approaching from the right or the left, does the limit exist there? And next we'll take a look at approaching infinity and negative infinity. Now we have the limits right side and left side for each of these. So we'll put in the arrows. If we were doing this without code, then we kind of piece all this together, and then next I'm going to show you how to do all these boom, boom, boom with the code. So we determine that it's undefined at 2, but approaching from the right, it goes up to positive infinity. So we just kind of put the arrow there. We'll fill in the rest in a minute. Then approaching this from the left, it goes toward negative infinity. We put an arrow there. And testing this, we find similar patterns, but approaching positive infinity from the left, and then approaching negative infinity. And since this won't cross, we expect that these, this turns around somewhere. So what I would do is I would pick a point in the middle and I would plug that in. And as it turns out, if I pick 0 as the x value, the numerator becomes 0 and the denominator is definitely a number. So it's 0, 0. And my arrows then, you'll see how we'll get this looking a little more elegant with code, but there we go. You become a little bit of an artist, sketching out graphs. So then here, what happens as x approaches positive infinity or negative infinity? Does this just keep going? Does it turn around? Now, we'll again look at how to do this with the code, but here's some insight if you're not writing code, as x gets to be a huge number, squared or whatever exponent, that really has an effect much more than multiplying or just subtracting 4 or something like that. So if x gets to be really big, these exponents make a difference. So we take a look at if the numerator has a larger exponent, then it's just going to go toward infinity. The number just keeps getting bigger. If the denominator has a larger exponent, that's going to really make a difference. And at huge numbers, that's going to be not 0, but so close to 0. The denominator being so much bigger, that's going to, the limit will be 0. If they're the same exponent, which they are here, I look at the ratio of the coefficients. So 3x squared or 1x squared, then I'd expect that the limit as x gets to be really big, as x approaches positive, actually, or negative infinity, because they're squared in this case, it approaches 3. So what I would have is, 1, 2, 3, and I would have a horizontal asymptote at 3. And so this would level out around there. And, a little bit of an artist, but you don't have to be that good. That gives you the sketch of the graph. This is what it would look like. So we piece together, where is it undefined, and then, what's going on, what's the behavior right around there, find the point here, and then as it approaches positive and negative infinity, and then we put it all together, and this is the graph. So we're going to look at this, and again, how to write this with code and be able to apply this to any other function. Find out where it's undefined, and then the behavior around each of these, what happens when x approaches infinity. And Sympy has a lot of these things already built in, which is great. So we'll do all this, and then we'll also just graph it. So, we kind of find these definite values and then see the graph. So let's take a look at this in the code.
Okay, so here's our next piece of the puzzle. Still before we graph, supposing I want to find out what happens as x approaches infinity. What happens to that y value. And I have just a comment here for that equation. I can just loop through it. And in this case, infinity is a big number. So I'm instead of just jumping to infinity, I just want to show you some values. Like I can just loop through a few of these values. As x is 10, 100, 1,000, 10,000. And I'm going to find the limit, plug in that x value and print it out, and we'll see, do we see a trend here? So for that x value, the limit 3.125, but then it gets 3, and then depends on how much you round it. Look at this. There we go. So we can really see this way. This works fine as a way to see these trends of what happens as x approaches infinity. Pick a few key values. Then we could put it all together, and we're actually going to even get better with putting all of this together. But let's just take a look at this graphing. And soon we'll look at an even more efficient way to graph with Sympy, because sometimes that'll be useful. But anyway, this is, hopefully looking familiar. Import matplot library, NumPy, and we're going to use this equation X value, there's my Y value, set up, my graph, at the zoom level, X min, X max. All right, so, my array for my X values, my Y values, and add another equation there, tinkering with, but we're not even going to worry about that. So setting up this, hopefully, again, this is looking familiar, changing axis. I'm plotting these, and I also decided to plot this one point here with a red dot, and I'm going to have the title as the graph. So we've looked at the limits, we looked at a couple critical values, the limits as x approaches positive or negative infinity, and we can see it all together. Here's the graph, and we see these values as x is positive 2. That vertical line is not a part of the graph. That's just showing the asymptote where that whole x value cannot exist, so there's no y value anywhere there either. And same thing at x equals negative 2. So we see then this trend as it approaches. We already looked at this when x approaches positive 2 from the right. This is what it looks like when it's approaching positive infinity. From the left, this is what it looks like when it's approaching negative infinity. And similar but opposite trend for x equals negative 2. Approaches positive infinity, approaches negative infinity. And that's what these graphs look like. That's that trend. It gets closer to that imaginary line, but it never crosses it or touches it. And in the middle then, all right, if it approaches negative infinity, both these here, then there's some value in the middle. Where does this turn around? And so that's why I picked that x value right in the middle. X is 0, found the y value and plotted that point. So we start to piece together what this graph looks like. And then we see here horizontally, it actually will be that similar trend. As x approaches positive infinity, that line kind of levels off, and it should level off at exactly y equals 3. And the same thing happens when it approaches negative infinity. So we see these different parts. We found the critical values. We found out what happens when it approaches from each of those from the right or the left, what happens when x approaches positive or negative infinity, and then we put it all together. I have those definite numbers, and then I also see what the overall graph looks like. So let's look at Sympy doing all this in actually an even more efficient way. So using that same equation, I'm going to go right to Sympy. Here's my equation. Notice I just have the full equation here. But I would have already checked out and noticed that denominator has values that would make it 0. So I would already have done that first step and found those critical values. Solve that denominator for 0, again, using Sympy. Do that in a separate code block. So now I have these two critical values here. And so this is the trend. This is the Sympy expression for the limit, and then it takes these 3 arguments. What's the expression, what variable, what value? And I've already defined symbols that I'm using x. So my first critical point, x equals 2. So there we go. That equation that I've defined up there, x is my variable, x1, my critical point, and look at this. Sympy already has it just built in. It takes that other argument. So I just need those 3, but if I have a sense that it might be different approaching from the right or the left, it has that other argument, direction from the right, and I can do the same thing from the left, Sympy.limit, and there we go, direction from the left. And I'm just going to output those values at x equals this. What is right and left? What are my right-handed limits? You can write it out differently if you want. And my second critical point, x2. So that's the only, all the rest of that is the same, same equation, same variable. Now x2 approaching from the right or the left. And there we go. And since I already did this and printed it out, it's okay that I overwrite these variables here. So, I'm just going to use that. It just works out. I could have kept them and make it, these 1 and 2 or something, but I don't need to. So now I have these 2 critical points, and I have the information about what happens as they approach the right or the left. And same thing here, Sympy has something built in when it approaches infinity. Now, this is kind of cool. The equation, the variable, and so, as it approaches what value in infinity, and that is .00, or sorry, lowercase o, because I can write that as, 00, that looks like infinity, and then that works out typing wise. So positive and negative infinity. So Sympy has that built in. What happens as I approach positive infinity? And I just had this printed out. As it approaches infinity, it approaches negative infinity, and we can run this, and we see, so just like it's Sympy.00 for lowercase oo for approaching infinity, if it does approach infinity, the output will just be lowercase oo, and that indicates that that's infinity. So at x equals 2, approaching from the right, infinity, approaching from the left, negative infinity. At x equals -2, the difference as it approaches from the right or the left. And as x approaches infinity, the limit's 3, negative infinity, the limit's 3. So we could do all of that and then throw that into a graph. And there you go. It works out. So we can just test other limits here. I'll leave that for some other examples. But we can use this just to show you just any other, what I had this one is, some trig values. We'll come back around to that when we look at some of the trig functions here. But you can use the same approach to test other limits as well. And, find the critical values, what happens as it approaches each of them, and positive infinity, negative infinity, and then throw in the graph. So we're going to start now using all this and building your calculator. Your calculator is what I called it. So let's take a look at just putting that together and building your calculator that you can use for any equation. So here's one way to organize your calculator, or whatever you'd like to call it. And we went through a lot of things looking at how to do limits and building upon that. But if you just want to make it that how you can use this from here going forward, you could have your heading, limits, and notice you could put the hashtag there. That'll make it a heading. It'll show up in the table of contents. And just some directions I put in here. What x value makes the function undefined, set the denominator equal to 0. So you could put your code block here, then importing Sympy, solvers, symbols, and right here, whatever equation you have from somewhere else, you would put the denominator here and then solve it. And there we go, solve it. Remember, Sympy wants to, when you do sympy.solve, and sometimes it will work without doing sympy.solve, but I just like to put that in as a habit. So there we go. When will the denominator equal 0? All right. And given that, you would get maybe 1, maybe none. You get some critical values, and then you would set this up approaching each critical point from the left or the right, and as x approaches positive or negative infinity. So given those answers you would get here, there's your critical values. Go back and put the full equation here. if you run it right away, you might not need to re-import these, but I tend to default to putting them in there just in case. There you go, the symbols, and you put the full equation here. You could, for your own organization, put the comments in as well, just so that when you open it up the next time, it reminds you exactly what to do. Critical values from the previous step. You see, maybe I just have one, or I just commented out, maybe I have two, maybe I have three, put in as many as you want. First critical point, and then again, this is the setup for finding the limit, and here we go. Find the limit from the right, from the left, and print that out. I just commented all this out, but supposing you had the second critical point, you would do the same thing for the second critical point. And then that same full equation as you approach positive or negative infinity. So you have this then all set up, finding those critical values, setting up all these, outputting these, and then let's put it all together on the graph. Graph with Sympy, one line of code. From Sympy.plotting, import plot. Okay, 2 lines because I haven't imported. But then, there we go. I still have that same equation. So remember the Google Colab, if you're running this all like right after one another, I think it'll time out maybe half hour, maybe a little bit less. But if you're going running this, then running this, then running this, that same variable that you would have set up, 2 code blocks before would have been just fine. That's still there. So, and that's often what you would do. You would run the one, run the other, and, put all this together. And so, yep, Sympy.plot, and then it'll plot the equation. So that way you have, you can put your full equation, get the denominator, critical values, put the full equation here, get all this information that you need, graph it, and then now you're building this with your, you're building your calculator here that you can find the limits and see the graph for anything. So let's take a look at one of the big applications of limits and how this leads into calculus.
Let's take a look at how limits apply to slope, and this is really the origin of calculus. So if I have a linear equation, it's the same slope everywhere, but if I have something like x squared, there's a curve to it, so the slope keeps changing. But what if I could get a good approximation of the slope at one point or really close to that? So let's start with just 2 points, and all I did was change the x value from 1 to 2. So this point, 1, 1, and then if x is 2, squared is 4. So, the x value only changed by 1, and I get these 2 points. I can calculate the slope there. Change in y, 4 minus 1, change in x. And, all right, that's a linear approximation. It's okay, but we can get better. What can I do to make this better? Well, let's say it's right around 1, 1, right around this point. That's where I want the slope. So I'll keep this, and supposing I move this point closer. So my x value then, instead of adding 1, I'm going to increase it just a little bit by a half. So, that x value would be 1.5. And then squared, that y value would be 2.25. And let's calculate the slope here. So if I have this, then my slope is going to be 2.25 minus 1 over 1.5 minus 1. And then that's going to be, 1.25 over 0.5. And yes, I'm mixing fractions and decimals here in my in-between steps, but I'll put the final answer as a decimal, then that's going to be 1.5. Or sorry, 2.5, don't mind me. So, all right, the slope here, it's okay approximation, but then they got closer and my slope is 2.5. And as we see, this gets steeper, so I expect the slope to decrease, but what happens if it gets really, really close? You see, so that's the thing. This is really what Newton invented, and we're going to talk about doing this with code, but remember, he did all this by hand, trying all these things, and then eventually certain patterns emerge, so we will definitely get to that. But this is like what it builds upon, so I want to make sure, that you get this. So if I take this, well, what if my next point would be, I'm just going to put a notation here. I'm going to keep that same x value. So my x value is going to be 1 plus, and I'll call it h. So that's going to be this variable that I'm going to introduce for whatever little bit I add to that x value. So now h, in this case, h would be 1, h would be 0.5, and then h could be any tiny decimal, however many decimal places you want. And remember, you could do this by hand, and as much patience as you have to like plug this in and do the calculations, we can get a y value. But the general sense is if this is the x value, my equation is x squared, so my y value is going to be 1 plus h squared. And I'll close those parentheses. So that's my point here. You see, the x value is 1 plus h, and then the y value, because I'm just getting really specific with this function, it's squared, so it's going to be 1 plus h squared. And then we can use this to calculate the slope, as then I have change in y, so I have 1 plus h squared minus 1 squared. I'll just leave it squared even though we know it's 1. And then the change in x is 1 plus h minus 1. So that's really just going to be h. That is the change. I've defined that as that's my little change in x. And so we can do this for any h value. And what we're going to do is we're going to look at the code and see how I can get these points closer and closer and get a better and better approximation of that slope, like right around that one point. Because I'm still doing slope formula, but my second point ends up being so close. And again, Newton did this all by hand without calculators or anything, but we can do this with code and get them really close and really see what patterns emerge here and like what's my best approximation of the slope at that point. So, this is the notation that we want to use, and let's take a look at how we can apply this with code and see what we get.
Let's continue on with this way that Newton did this. And remember, he did this without calculators, without graphing utilities, and certainly without Python. So we can see, how to plug in these numbers. I'm gonna have my main x value, like what's the slope at this point. So then, calculate the y value. And h is that slight difference. So then my second y value is x plus h squared. And we have this. Let's graph this. Setting up the graph as we did before. For this one, the matplot library NumPy works well for this. So then now I have this. I am going to calculate the slope, change in y, and then the change in x is h because it's x and then x plus h, so that's that difference. Print out the slope, and then I'm also going to show this plot of these 2 points. So we see our graph here, and the x values, these 2 points, and then the slope there is 3. Yeah, okay. And now we want to get what happens when these 2 points get closer together. I'm just going to I'm going to pick another h value, 0.3. That should be small enough that they get really close, but then you'll still be able to see them as 2 points. So now we see these 2 points got really close together. and look at the slope at this, from these now it's 2.3. So that's the idea. Supposing they get really, really close together. Now, if I just kept changing that, or if I looped through that there, the display here, you will see them as 1 point, and that's the whole idea. But let's look at the actual values there. So what I did is, let's loop through this, but then we'll skip the graph on this, just looking at the values. So I have my x value and y value. And then as h gets smaller, so here's what I did in range from 1 to 11, 10 to the exponent of negative a. So that's my h value. Becomes 1/10, 1/100th, 0.01, 0.001, 0.0001. That's where h gets really small. And we're going to go through that same thing. Change, x plus h, find the slope, and then take a look at what happens here. So already the slope is, different here. But as that h value gets smaller, I get 2.01, 2.009. Look at this. We get more and more zeros. For some reason, this one changes a little. But more and more zeros. And we see that it seems to be approaching 2. In fact, for a while here, if I rounded this to like 2 decimal places, my slope would be 2. So, interesting. Let's look at this. We will get to how how it approaches a particular number and how to get that without even doing this loop. But I want you to see that that's what happens. This is really what Newton was saying. Again, without seeing all this printed out in code. He did all this by hand. That it actually does seem to get to a certain number. Here's another example. Again, not too complex, but complex enough to illustrate the point. Y equals x to the third. And I'm going to go through all the same things. Here's my h value is 1. So when I plot these 2 points, so there we go. And the slope between them is 7. Yeah, that's really a big difference there. So what happens if I change the x value here? Instead of 1, I'll make it 0.3. And we go, yes, they got a lot closer. And then look at the slope, 3.99. And we can imagine them getting closer and closer. How would the slope change then? So then we go through. I'll do the same thing. I'll do the loop and no graph. So x value, my y value, and the same type of thing. H gets really, really tiny. And what do I get? The slope then a little bit lower, but then it keeps even getting lower and lower. And then it drops down to 3. Down here, I actually was thinking about showing this with sliders, but the display doesn't really illustrate the point. You really need to be able to either see these getting closer or see the numbers. So now we're starting to see in 2 different situations. Now, it would be different if the x value was, 2 or something like that. So we could do that if the x value, there we go. If I just make my x value 2, but the second y value is going to be off the charts here. So that's this gets really big really quickly. So we have we see it approaching this. So what we're going to do is we're going to look at the code, or we're going to look at the factoring. Newton did see this, and he figured out a way to factor out that difference to get it to be the slope at, for all practical purposes, 1 point. So we're going to go back and look at the factoring and how we get to this, and then we're going to come back and look at how to do all that with code and stand on the shoulder of giants and have all this long explanation get boiled down to like 1 line of code.
So we saw how we could get approximations of the slope at a particular point. And what we're going to do is we're still going to call those approximations because we're going to find a way to get the exact value of the slope at any point. And I'm still going to use this specific example, y equals x squared. Later on, we'll talk about how we can generalize this. So if that's my y equals x squared, then I have xy as any point on the graph. But let's write it, instead of xy, I actually just want to put that actual y value in there, x squared. Like, there we go, that's my y value. And so then my next point, remember we're still introducing that variable h of like the tiny change in x. So if this is x plus h as my next x value, then the y value is going to be x plus h squared. So we see that's how we can put in these, x and then x squared. Specifically for this function, that would be my y value, whatever x is squared. And then if then it's x plus h, then it's x plus h squared as my next y value. And we see now we have these variables that are all number one based on x, and also then I don't have even a specific number. So I can find the value of that point. So let's look at the slope. So it's going to be x plus h squared minus the original x squared, change in y, over change in x plus h minus x. It really is h because that's been defined as, that is that change in x. So when we look at this, we can see the slope, and certainly we can say, well, okay, well, what happens, h can't be 0, but it can be really tiny. Do I still have to go through what we were doing and plugging in these values? No, we're going to see this math acrobatics that Newton invented, and we're going to say, we're also going to bring in the limits back. So this is the slope, but let's take a look at this as the limit as h approaches 0. So what can I do with this? As h approaches 0, I can factor this to get to what h would be, what the slope would be at any given point. So let's take a look at how we can factor this, but I'm going to need some more space here. So now we have more space to do our factoring. And remember, this is still the slope at any given point as h approaches 0. So I want it to be so close, but it can't be 0. Let's factor just the numerator here. So x plus h squared, if you remember from algebra, that becomes x squared plus 2xh plus h squared. And then I'll bring this down minus the original x squared. All that over h, but let's cancel this out because I have x squared minus x squared. So now we're down to 2xh plus h squared. And remember, all this, yes, is over h. So, still have h in the denominator, but I'm adding in the numerator. Let's write this as two separate fractions. So 2xh over h plus h squared over h. So mathematically, just a different way to write it, just as correct, but this one works for us here because if h is any number, however tiny, as long as it's not 0, these cancel. So I'm down to 2x plus h. Look at that. Now, when we remember this is the limit as h approaches 0, it can approach 0, and my slope is 2x. And that's what we have here. The slope is 2x at any given point. So if I have y equals x squared, all I need to know is the x value, and at any given point, 2x, that is the slope. And what we'll look at then is this and some other functions If you really wanted to do this all the long way by hand, you actually could factor out different functions and as h approaches 0, but cancel out that h value. But then there's all these other patterns that emerge for calculating the slope. But this is really what makes it calculus, that Newton figured out that we can get to that place and cancel out these values, and now I have the slope at all I need is one x value, not 2 points, and I can find the slope at that point, and that's the actual slope there, not an approximation. So for as complicated as this was, we're going to take a look at how to do this with one line of code. But it's important to see this background of what we're doing with that code, so that what the output makes sense to you. But let's take a look at the code.
So here's where we're really going to see the efficiencies of writing code to do your calculus. We're going to import Sympy, and we're going to import symbols, and we're going to set that x and y represent x and y. I always use both of them here, even though the next several examples, we're really not going to make use of the y symbol, but that's just my go-to, and so I have that here. So my expression is going to be, in this case, x to the third power as an example. Here it is. The derivative, sympy.diff. Differentiation is really another way for taking the derivative. So sympy.diff, and then what the arguments takes that expression, and then I'm going to use x as the variable. There we go. That's all your derivatives in one line of code right there. And just, I like printing out that this is the derivative. And then in Sympy, because I'm going to store this, I took the derivative and I stored it as this variable. If I just make this my last line of code, and see, there's my comment, we'll do the derivative at a point in the next block, but this is my last line of code, so when I run this, it'll output it with nice math print. If I instead did like print derivative, it actually will not print it out in nice math print. So that's why it's worth it to just break these up, this block of code, and then do something else in the next block of code. So there we go. We're going to go through some other examples of different derivatives and different sorts of formulas, but you can use this for any of your derivatives. Just change the expression and this will do the derivative of anything. How great. And remember, the derivative means the slope at that point. That's really what it means. I derive this and I find the slope at that point. So often we want to take the derivative and then plug something in. All right, so that's why I stored it as a variable called derivative here, because it keeps the nice Sympy output, because now I'm going to put an x value in, and I want the derivative. So I take that derivative variable, dot subs, short for substitution. And I'm going to for the value x, I'm going to plug in the x value. And so there we go. So I take the derivative, I see that formula, that's the slope at any given point. Plug it. All I need to do is plug in the x value to find the slope. So that's what I do here, subs, and my answer is a definite number. So that's fine. I store it as answer, and I can use that in the print statement because I don't need any fancy math print. I just want the slope at that. So the slope, there we go, at x equals 2 is 12. And there we have it. Take the derivative and plug in whatever x value you want, and then find the derivative at that point. We're going to build upon this and look at just different types of derivatives for different formulas, because even though this does all this for you, boom, done, you almost might be tempted to think, oh, I don't have to think about it. But you want to have a sense of what you expect that derivative to be, or, something. So we'll look at just some general patterns of derivatives. But there we go. Any expression, find the derivative, find the value at whatever particular point.
So we saw one example of a derivative and how we can calculate the derivative with one line of code. So let's look at what the derivative means and then how we can get a general pattern for this. So remember the slope, if it was linear, we could stop here, but it's change in y over change in x. So, so subtract y2 minus y1 over x2 minus x1. And then y, I could also write it as f of x. So I can look at the slope as, here's my second y value, x, the original x value plus h, some tiny difference, minus the original y value. So f of x plus h minus the original f of x. And then that way I have, I can define this in very general terms, whatever that original x value was plus, some tiny difference. And then that's the change in y. And then the change in x is that tiny difference, which is h. So for slopes like x squared or anything else where there's a curve and it keeps changing, then I want to get these 2 points closer and closer together. So that difference, h, this is the limit as h approaches 0. And remember, it can't get to 0, but it can get so close. And we looked at how we can get closer and closer approximations, but then we see these calculus patterns that I can actually figure out, and there's certain ones we'll memorize, there's certain ones we can factor out, and we can see what is the slope at any given point. So remember our other one, we did y equals x squared. So then we said that the slope is 2x at any given point. And we said, okay, then all I need to know is the x value, and then I can figure out the slope at any given point. So, at 0, the slope is 0, and we see that. And then as x increases, remember that x squared, it curves upward, the slope gets steeper and steeper, and that's exactly it. Given the x value, 2 times that, that's the slope at whatever point that is. And this is really cool. So let's take a look at, what are we doing here to get this? There's this definite pattern, and yes, you can write the line of code and see the answer, but you want to know what it means. Well, one of the things that we're looking at here is that this is, and I'm going to do one other example, and then that'll really illustrate, what's going on here. So if I have 2x to the third, and then while we're talking about it, the slope is change in y over change in x. And you might remember this from some other notation. It could be delta y over delta x, because that's a notation for change. And then in calculus, somewhere along the way, instead of delta, the notation evolved for it to be dy over dx. D for delta. So we see that this notation evolved. Yes, it is the slope. I can write it the slope like this: delta y, change in y over change in x, delta y over delta x, dy over dx. And I'll tell you, more advanced calculus classes, it's still dy over dx, but they write the d a little bit fancier, at some point. So anyway, so what am I doing here? And this is one of the patterns that we'll look at. And this one's the power rule, because I just have some, coefficient, but then I have x to some power, some exponent. So this pattern is that exponent times the coefficient and then exponent minus 1. So 3 times 2 is 6, and then that would be x squared. So if I have something like this, yes, Python makes it easy, I can just plug that in, but also, there's a few patterns we want to take notice of so that when we do plug this in and we see the answer, they kind of make sense to us, like, oh, okay, yeah, that's not what I expect. So if y equals 2x to the third, then the slope, or dy dx, would be 6x squared. And once again, these functions, all I need to know is the x value. I could go to take the derivative, then plug in whatever x value, and I can get the slope at that point. And that's kind of what we really want to get to. I get this general pattern, and then I get the slope at that one point. So then, here's the other interesting thing about doing these calculations. And I will just keep it as, dy over dx. And sometimes people just say it dy dx as the slope. So if I have a few things, so if I have like, x to the third plus 4x squared plus 2. Let's say I have something like that. Really, anytime you're adding or subtracting, you can take this as the derivative of this plus the derivative of this plus the derivative of this. 3 separate things. And then if we take a look, so I would take this this would be 3x squared because my understood coefficient is 1. Then plus 8x. And then here, remember every monomial, you might remember this from algebra, that there is an understood, this is x to the 0, because each term has a positive or negative sign. So the first one's positive, but since it's first, I don't have to write the plus. So this is still positive. My coefficient, if I didn't have a coefficient, it's 1. For something else, like let's say x to the 4th, that would be a coefficient of 0, and it zeroes out, so I don't need to write that. But then I have that sign, the coefficient, and x to some exponent. Anything to the 0 is 1, so then 2 is really 2x to the 0. So then then the next step makes sense, because when I do exponent times coefficient, it's 0 and it zeroes out. So I don't have to write that. So just as an example of one of the many patterns that come up as we do derivatives. So even though same step, sympy.diff, you can take the derivative of each, and we're going to go through next like all these different patterns. Just even though you can do this with one line, it's still you want to have a sense of what the derivative would be, and if you were doing this without code, then you would be in a calculus class memorizing a lot of these derivative patterns. Some calculators will do that for you. The TI-89 will actually do the derivatives for you, but the 84 won't. And the 84 with Python, what's going on here in the Sympy is more than what the TI-84 with Python can handle, so that won't do the derivatives. But the TI-89 will do the derivatives for you. But we're going to concentrate on doing this in Colab with Sympy. So let's take a look at the code and look at a bunch of these derivative patterns.
Besides looking at this general power rule and that pattern for derivatives, let's just take a look at one way to organize your Google Colab. You could even split out these import statements and the symbols and do that once if you are going to do a lot of derivatives. But I just put that there, importing the symbols. There's our equation. I just called it EQ instead of writing out the word expression. There's my equation, derivative. And then you see I have just the equation here so that when I run it, I can see in nice math print what equation I'm taking the derivative of. So it's good to check that, because I know what this looks like in math print, and something more complicated I might wonder, did I write the Python code correctly? So we check to see that that's what I expect it to be, and then I run another code, then take the derivative, and then I have another one where I'm going to substitute. So you see this code block literally just one word. Do that because up here I did the derivative, sympy.diff, stored it as that, but I didn't output it yet because I want this to be the last line of code so it prints out nicely. There you go, this, so it prints out nicely. And then this one, pick an X value, 0, 1, 2, 3. And then there we go. So we see that this is the original function, this is the derivative, and so I would plug in an X value to get the slope, and that's what I'm doing. So when X equals 3, the slope is 27. Yep, 3x squared, or X to the third gets to be really steep really quickly. So when x is 3, the slope is 27. Next, we'll look at some other derivative patterns.
Now that we're starting to get into some derivative patterns, let's take a look at the chain rule. And this is really important because it comes up in so many different functions, all kinds of other derivatives. So if we just had like x to the third power, then I would take the derivative its power rule. But instead of x, I have this whole inner function here, x squared plus 1 to the third power. So the outer function is everything in parentheses to the third power. Oh, I'm going to use power rule. So that's exponent times this unchanged to exponent minus 1. But this is where the chain rule comes in. If I have, so whatever this is here, that's my inner function, then the next part is times the derivative of this inner function. So I'll do this, that was power rule to get me to this, and then the derivative of the inner function, oh, I'll do power rule with this, 2x times 2x out here. And usually, especially if you're doing this with Python code, Sympy will do that simplifying for you. A lot of multiple choice tests, you're not going to see this as an answer choice because it really is obvious that, hey, you can combine these and simplify this a little bit. So I'll write this as 6x times x squared plus 1 squared. And so there we go. Chain rule, derivative then times the derivative of the inner function. And again, this comes up all the time. Let's take a look at another one that the actual derivative without the chain rule is the simplest derivative in calculus. So y equals e to the x. And remember, e to the x, that constant Euler's number 2.71828. So the derivative of e to the x is e to the x. How cool is that? So that exact graph, the y value of that graph is the slope at any given point. It's one of the things that makes E so useful. It's all these other patterns that are associated with it. But anyway, so this, if it was just x, now it still follows the chain rule, but the derivative of x is 1. So times 1, I don't have to write that. But supposing it was the derivative, like instead of just e to the x, it was e to the x squared plus 3x, let's say. So now my exponent has a lot more going on. So the derivative is this exactly, e to the x squared plus 3x. So that first part, that doesn't change here, but then it's times the derivative of this inner function. So then that times derivative of this, which is 2x plus 3. There we go. And so you see the chain rule comes up all the time. I have these overall derivative functions, but then it might not just be x as the exponent, it might be some other more complicated things that I can do the derivative of that inner function. And so we'll take a look at the code. Again, you can, Sympy will output your derivative, no problem. But some of the things you want to be kind of aware of what's, even if you're not memorizing all of these, aware of kind of what you expect so that if you typed in something wrong and it outputs that, you're like, wait, hold on a second, let me double check this. And also for some of the more complex things we'll do down the road in the near future, it's going to really help you. Even if Sympy does certain things, it's going to really help you work with that to get the answer to certain problems. So there we go. So chain rule, it's always that, then times the derivative of the inner function. And we'll take a look, just a couple other examples in the code, how we can see this play out. So let's take a look at the code.
So because the chain rule is so useful and important, we're going to do a few examples here. And again, this will just do the derivative for you no matter what you put as the equation here, but you want to have a sense of what it's going to do. So that's actually making use of the chain rule will be really important in a couple other things we do later on. So, the derivative by the inner function. So just showing this here, again, making sure, yes, this is the one I wanted. So you see, I have this inner function of x squared plus 8 in the parentheses, and then all that to the fourth power. It's not just x to the fourth, but it's this whole thing x squared plus 8 to the fourth. So then the derivative would be this. Yep. So 4 times this to the third power, x squared plus 8 in there doesn't change. And then I would have multiplied it by 2x, and then notice that simplifies it too. So we see that that is the derivative using the chain rule. Another one, so if I see square root, now square root, if you remember from algebra, I could write that as all this to the 1/2 exponent. So when I take the derivative, that to the 1/2, but then it's always exponent minus 1, so then the exponent would be negative 1/2. Negative puts it in the denominator. There we go. And 2x, and there would be a 2, they cancel. So we see, if you weren't writing the code, you would be doing the factoring for all of this, but just seeing that, all these different, some of these different options here. And then I could always, pick an x value and substitute. Here's one. Now, we'll talk about trig derivatives, but we have sine of x to the third, and so the derivative would be this. You see, the derivative of x to the third is 3x squared. And then, so it's the cosine, the sine becomes cosine, and times that. Just seeing some examples here. Cosine. So you see the sine of the cosine. So you see my inner function can be another trig function. And so that's really making use of the chain rule. Many examples, but you get the idea. And just, again, this is going to do your derivative for you, but just to see some examples of what this would look like, I think that's going to be really important.
So we're just going to look at a couple other general rules, even though you're just going to type this in, sympy.diff, to calculate the derivatives. But again, being able to be familiar with what comes out. So one of them is the product rule. So we're going to learn all these different derivative formulas, but then supposing I'm multiplying two things, and what's the derivative formula for that? Well, I can actually take them each individually, and there's a pattern to this. So if I had something like x squared e to the 2x, so two separate things, and we see that as two separate functions because you can't really combine them any more than this. So I can take the derivative, and the product rule is first times derivative of the second plus second times derivative of the first. So I would do x squared times the derivative of the second is e to the 2x, and remember chain rule, it would be then times 2. I'll simplify that in a bit. Plus second, so that's e to the 2x times derivative of the first, which is going to be 2x. And so we see that I have this nice pattern, these two separate things, and we talked about derivative patterns for this, derivative patterns for this, but if I'm multiplying two of them, I have product rule. And certainly the Sympy output and most other places, that's not going to be a good, that's correct, it's not going to be a good enough final answer. We want to simplify this. Let's bring the 2 out front. So it would be 2x squared e to the 2x plus, and if actually that is the convention, but certainly since I did this already, put the algebraic expression first, then e, so I'll bring this to the front. So then that's 2x e to the 2x. And then that's the derivative. And that's probably more likely what you'll see for the Sympy output. All right, and so that's product rule, and then there's one more, quotient rule. So here we have two functions that could be separate that I'm dividing. So I don't have a formula for this exactly. I have a formula for this, and so I use quotient rule, which is denominator times derivative of the numerator minus numerator times derivative of the denominator, but then all of that over denominator squared. So let's take a look. We have the denominator, which is e to the x, times the derivative of the numerator, which is 2x, minus numerator, so there you go, x squared, times derivative of the denominator, which is e to the x. All of that over the denominator squared. So e to the x, and then all that squared. Okay, so that's the formula, but we can simplify all of this. Again, let's bring out the algebraic part first. 2x e to the x minus, and I already have x squared here, x squared e to the x all over, then that becomes e to the 2x. There we go. And possibly I could factor out e to the x out of here, and then that becomes e to the x in the denominator. Like, that's another way. So we could say then, you know, e to the x, divide everything by e to the x, and then you could get then that cancels, and e to the 2x is really then e to the x. So sometimes if it's, you know, if you're doing the factoring, if it's really obvious, then you would simplify it. And there's so many things, you know, the focus of this course is writing the code. So really a lot of calculus could potentially just get into factoring. And what we want to do is get the concept of what this would be so that, you know, it kind of makes sense, you know, understand what the output is. But we're not going to focus on factoring. We're going to focus on, you know, here's some examples of some of the rules, and then let's write the code to do it all of it. Because that's our goal, like to understand the concept of calculus, write the code to do the math, and then we can really use this for some, you know, other applications without getting caught up in all the factoring. So let's take a look at just a few, again, different derivative functions, different functions and their derivatives, and just going through and just seeing what that output looks like in Colab. So let's take a look at a few different other types of functions and the derivative examples.
So going through a few of the main derivative formulas, each of these does not require anything new if you set it all up like this. The only thing you need to do is change what equation you put in there. And you see, like we did before, calculating the derivative, but I'm just displaying this equation, and then in another code block, I'll display the derivative. So I have this, run it, you know, just to display the equation. Yes, this is the equation I want. And I could distribute this, but I'm doing it this way to illustrate the product rule. You know, I have one thing and then in parentheses something else. As the product of two things, I could do the derivative, and it would look like this. Then, again, you could combine like terms if you wanted to, but just to show you, you know, an illustration of the product rule. Quotient rule, again, the code's the same, so, you know, you really could just put in whatever you want here, but just showing a few of these. This equation, and it would be something like this. If you were doing this by hand, you would need the quotient rule. And then calculating the derivative, right away you can see some of the time it's saving you. This took 2 clicks. You know, click here, run this, there's the derivative. And you could always plug in various x values, but you don't need to for our examples here. Chain rule we already talked about. So all the different derivative functions. This is worth mentioning with Python because in Sympy, exp, a lot of times we think about our common log 10 to the x, but exponent function here in Sympy is e to the x. So sympy.exp, I do want to output this so that you can see, yes, that's e to the x. That's the function that I want to do. And the simplest derivative in all of calculus, the derivative of e to the x is e to the x. So there we go. If I have other numbers, that I will use this function sympy.exp. But if I have another number, like 2 to the x, I'm just going to write it like this, 2 to the x, and it'll output it this way, 2 to the x. Then the derivative of this is 2 to the x times the log. Now, that means natural log. So, that comes up in the next step. Log in Sympy is really ln in other math notation. So you have to make that adjustment coming from your calculator. So notice if this is ln, so the natural log of 2, which is the base, if I had something like 3 to the x, there's 3 to the x, and then the derivative of that would be 3 to the x times the natural log of 3. So that same formula, because here the natural log of e is 1, so it would be times 1. I don't need to write that part. So you see we have any exponential function, and I get the derivative. And we remember that log in Sympy is natural log in math notation. So sympy.log, and if we run it, it even still just outputs the log. Just does never change it to natural log. But we know then that that's the log, and then when we run the derivative is 1 over x. That is the derivative of the natural log. So change your base formula if I wanted any other base. So it's sympy.log, but then I have to do not just x, but comma, and then whatever the base. So I put it here like this so that I can just change the base easily here. You see, and then if I change the base to, 5, there we go. And that change of base formula, Sympy just doesn't want to write it as log with a little subscript for the base. So it's written like this. You might remember this change of base formula using it on a calculator, solve anything, but there we go, change of base. And even if you put a 10, it doesn't do anything, because normally we would think just log without a base written there is 10, but there we go. So we have that base and then the derivative. So remember 1 over x, and then in the denominator times the natural log of 10. So, up here, the denominator, if it was times the natural log of e, that would be times 1. We don't need to change that. So we get this and then the derivative. So there we go, just a quirk with logs. All the trig functions, again, I'm not going to go through a lot of this, but to show, all these trig functions, sympy dot, and then whatever the trig function is, sine, cosine, tangent. And, there we go. Show the equation, the derivative, that's great. Cosine. Sympy.cosine, show the equation, the derivative. Tangent, if we take a look at tangent, there we go, fine. But when I do the derivative, it takes it as, fine, it displays tangent, all normal. But the derivative is tangent squared plus 1. Now, I always remembered it as secant squared. This mathematically does equal secant squared. It's one of the Pythagorean identities. But Sympy just really wants to output it this way instead of secant squared. Then I'll take this derivative, and one of the other built-in functions, if you might remember from pre-calc, sympy.trigsymp, it'll simplify trig functions. So if I take this and simplify this derivative, still it wants to put it as 1 over cosine squared, which again is secant squared. So it outputs this correct, not maybe, if you're familiar with these, it might not be what you expect. Same with this one, correct, might not be what you expect. And then, so I really tried to see sympy.secant squared to see, if it output this. So sympy.secant squared, there you go, I just output that. It can do that. And then so I thought maybe if I just force this in here and output this, but no, it just goes right back to 1 over cosine squared. It somehow, unless I just say for, no math involved, just output secant squared, it will do that. Every other time it wants to output it somewhere else. So this is just something to be aware of. Sometimes, if you're using this to check other work or something like that, some things might, a couple of the quirks here, they might be mathematically compatible, but, again, if you're trying to check your other work, it might not match up, but yet it's correct. Cotangent, there we go. And the derivative, really, again, I remember it as negative cosecant squared, but this is mathematically the same, just written differently. I'm not going to go through all the other, but to show you, there we go, that is the derivative. Secant, there we go. Yep, secant, fine, outputs it. The derivative, tangent secant. At least that seems normal enough. I always tend to write secant first, but it doesn't matter. It's exactly the same thing. Cosecant, there we go. And the derivative, there we go, negative cosecant cotangent, correct. For whatever reason, that displays it as I expected it, but anyway. So just showing, again, you could any of the trig functions, equation, the derivative, just there's a couple quirks that might not output exactly what you expect. And the same with all the inverse trig functions. I just want to show you just another thing that you can do. You could have all of them. So inverse trig or inverse sine would be like arc sine. So all of them just have the A in front of them. And another way to do this, if it's something you use a lot, you could put all of them in there and then just like comment them all out and then just only uncomment the one, you want the one you want. So you totally could do, there you go. There's arc sine and then the derivative. Yep. And then you could say, oh, well, let's see. Supposing I wanted tangent. And so arc tangent, run it. And there we go. So another way, other things you can do. Hyperbolic trig functions. So again, you go through all 6 of them and just have the h at the end. That's the common notation for all the hyperbolic functions. This is good because you can, see it will just output it as hyperbolic sine and then the derivative, hyperbolic cosine. That all matches up nicely with the original trig functions. So, that helps you. But then you can have inverse hyperbolic functions and same thing. You can put them all there, A for arc because it's the inverse and then H for hyperbolic. So all of them have this just to show you that all these are still built into Sympy. And again, you can output any of those equations, any of the derivatives. And these are kind of just like the core basic ones. And any more complex functions or derivatives, you can mix and match all of these. So one of the other twists, and we'll talk about this in the next section, would be implicit differentiation. Certain aspects, you're going to imply some things. But it's all the basic derivatives, and you could always run them all, and then you have, a whole reference sheet if you wanted to. All right. Now next we'll take a look at implicit differentiation.
Now with implicit differentiation, we're going to bring in some of the concepts we've been talking about with chain rule and some other things. So implicit, so that's the adjective for imply, where you imply things. Let's contrast this with, this is an example of a derivative we were doing, and this is explicit. It's very clear that y is a function of x. And so it still follows the same algebra rules, do the same thing to both sides. There's my equal sign. Take the derivative of this side. Derivative of y is dy dx. The derivative of x squared is 2x. So you see, one of the things we can do to both sides, take the derivative. And that's explicit. It's clear y is a function of x, and it's clear that that's what we're doing. So now, when we get to implicit, the implicit differentiation is when we have like x squared plus y squared equals, I'll just say 25. So I have y on the same side as x, and it's squared. So remember, it's not a function of x strictly, because there's going to be, for all these x values, there's going to be 2 possible y values. So I definitely can graph this, that's going to be a circle, but I'm implying that y is a function of x. So when I take the derivative, I still want to do that. I'm not going to need to rearrange it in this step, but I'm just going to go through and then take the derivative of each term and remember that y is a function of x. So the derivative of x squared is 2x. That part didn't change. Plus, now, y is a function. So y itself is this inner function, chain rule. So I'm going to have 2y, because exponent times this unchanged, and then exponent minus 1 is 1, times the derivative of this, which is dy dx. And then derivative of any constant is 0. So you see, we go through and we take the derivative just anytime y comes up, chain rule, because it is a function, and that's what we're implying here. So wherever y shows up, if I had something like xy in my function, I'd have to do product rule. So you see how implicit differentiation works. Now, that's great, but I still want to get dy dx equals. I still want that actual derivative. So I'm going to have to do a couple steps of algebra, subtract 2x from both sides, and I get, 2y times dy dx equals negative 2x. Divide both sides by 2y, and I get dy dx equals, the 2's cancel, so it's negative x over y. And you see now, in finding the derivative, before, when I took the derivative and then I wanted to find the slope at that point, I just needed an x value. Here, I need both. So if I had just an x value, then what I would do is I would need to get that x value and plug that in to find possible y values. In this case, there would be 2. So my slope, just having the x value, not enough, x, and then the y, but one of the y values that goes along with it, I could get the slope at that point. And remember then, this being the graph of a circle, for one of those, the slope will be positive, one will be negative. We'll take a look at that in the code and see how that plays out. But, implicit differentiation, this is the math behind it. And, useful to realize when you're doing implicit differentiation, because as we'll see in the code, it's a slightly different Sympy function, idiff instead of diff, because we need to account for the fact that the y value can show up anywhere. So we're still implying that y is a function of x, and we're, if I was factoring, I'd take the derivative and then solve for this. Okay, so let's take a look and see how all this plays out in the code.
So here's the way to do the implicit differentiation with code. And you'll notice some similarities. We're still importing all the same things. And now it's going to be really important that I use both x and y as my symbols. I have a couple equations here, but let's look at this one. So setting the equation equal to 0. Before we were setting the equation equal to y because they were definite functions. But it's y could be on either side of the equal sign, y could be squared, whatever, all kinds of things. So everything here is set equal to 0. So in this case, I have x squared plus y squared minus 25, then would be equal to 0. And the next thing is, when I do the derivative, instead of diff, it's I diff. So implicit, this requires some different things, so it is a different Sympy function, I diff. And I need one more argument. I have the equation, and y is a function of x, so I need to mention that first. If I switch these, my derivative won't be exactly what I expect, and it will be wrong. So y is a function of x. There we go. And so when I just see the equation, there we have x squared plus y squared minus 25. And then the implied equals 0. And that's really the implicit means that we're implying things compared to explicit, where we really spell it out. So there we go. And take the derivative of that, negative x over y. Now, that's great, all correct, but I'm going to throw in some plotting here so that we can put that in perspective here. This x squared plus y squared minus 25, if I were to graph it, now also, very similar import the plot, and instead of plot, it's plot implicit. So again, slight variations because of the implicit function. So Python likes to stretch out the graphs, but this really is a circle. It just stretched out. But you see 4 and then a little bit more. It really is. So you might remember this. X squared plus y squared equals r squared. That's a circle. And then now when I look at this derivative, the slope at any given point, I see why we do need both x and y. Because if x is 0, if we take a look at this, look at the top. If x is 0, then my slope is 0. It would be a horizontal slope up here, or a horizontal line, tangent line up here. Same with down here, actually. But if y is 0, that happens over here on the right and left, that'd be undefined because I'd have a vertical tangent. And then we can see that in the first quadrant, x and y are both positive, so any point along here would have a negative slope. X and y are both positive, but then make it negative, that's the slope. And down here, where I would have x and y, one of them would be, in this case, the y value would be negative, and times negative makes that a positive slope down here. So it just puts it in perspective here, seeing the plot. All right, now, one of the other things, if I need an xy point, now for this part, I happen to know, 3, 4 works. 3 squared plus 4 squared equals 5 squared. So I'll just start out with just putting those in. But I need 2 steps. So we see I need that derivative, and I'm going to subs the x value. That is actually the same function. Dot subs. But I need that stored as answer x because then I need to take that and substitute in the y value for y. So that'll give the slope at any point. So there we go, negative 3, 4. Because if x is 3, y is 4, there we go, somewhere over here, then the slope is negative 3, 4. Now, that's great. This is a nice example that I have set for you, but here's what you would do. Certainly if you're expecting multiple y values, which happens a lot in implicit differentiation, these x values each have 2 different slopes depending on your y value, and they're both very different. So I could start out with an x value that I know is on the graph, and here's what I'm going to do. I'm going to substitute that into the original equation, get the x part, and then set that equal to 0. So sympy.eq, set that part equal to 0. That's my y part. And then I'm going to solve for that, solve for y. And then that's my y value. So we see these multiple steps here, and then I get 4 and -4. So if x is 3, yes, 4 is is a y value, but -4 is also there. And I can take this. I have two values. Each, y value now is actually an array because it has two elements, and I'm going to loop through them. And notice however many elements I get, this loop still works. So y loop in y value, and I'm going to take the same thing. I'm going to say, substitute the x value, and then substitute, that first y value, and then now I have the slope at this is this, and it'll loop through. The slope at 3, -4 is 3/4. The slope at 3/4 is -3/4. So we can take a look at this and we see, the subtle differences with implicit differentiation. I need to do the idiff. I need to do, plot implicit. And then when I plug in, I need to do this in a couple steps because I need to plug in for the x, then solve for y. I can't just plug in both in one step. So I just wanted to put another one on here because this really comes up with implicit differentiation, and it's probably my favorite equation. All right, and then as this is set up, it'd be equal to 0. This is the folium of Descartes because, Rene Descartes, this XY coordinate plane, he invented this, and so this is his equation. Now, we can take the derivative of this. There we go, nothing to sneeze at. But then, what's this graph look like? Because if you're the guy that invented this whole coordinate plane, you can graph a loop. So I just think that's really cool. That's just, they didn't have microphones back then, but if he had a microphone, he would drop it. Boom, loop. And so we see, some of these x values, let's say x values like 1 maybe, you have 3 possible slopes here. So you could do that. I'm going to skip this because I don't want to do this. Actually, 3 works for this too, but I'm just going to show you. So supposing if I have an x value of 1. So what I can do is plug that in, and you see I have all these possible y values. Now, one of the things I can do is if I comment this out and then just put y value here. Nope, didn't get any better. There's a way to make this nicer print. But anyway, just to show you that we have these multiple y values. So then if I loop through them, it just becomes this whole mess. Anyway, and we do get 3 different slopes. One of the other things you can do is there's another one like 3. If I plug that in, that's not as bad. And then I can loop through that. Yeah, not as bad. At least it's manageable in this one screen. So you see some of the things that we can do. You can have, all kinds of weird answers. But the key is, implicit differentiation. How can I still get the derivative? How can I plug in different values? How can I find the slope at these points? It's a few extra steps here. There we go. And this next we're going to get into just putting this all together and, again, building your calculator so that you can just plug in any derivative, graph it, do all kinds of things. So there we go. We'll take a look at that, and I'll leave you with the Folium of Descartes.
Now we're going to get ready to put it all together. And when you think about calculus or the derivative, what are the steps? What are the things you want to do? You want to see the function, the equation. So we'll look at like just putting that in, displaying it to make sure the code you write matches what you think this function should be. You want to see the graph, and you have the function, the original graph. You want to be able to take the derivative, so see that equation for the derivative, then graph the derivative, maybe graph the derivative and the original function on the same graph. Then what you want to do, derivative at a point, because very often, okay, what's the slope at this point? That's what you want to know. Then maybe you want critical values, which is take the derivative, set it equal to 0, because those values tell you when is the derivative 0, which is a horizontal tangent, which gives you the minimum or maximum points. So derivative equal to 0 to get the critical values, and then you might want to go to the second derivative, because very often that's important. Then, how quickly is the slope changing? The second derivative. And so we can go through that second derivative, see the equation, see the graph, see maybe all three graphs, the original function, derivative, second derivative, all in the same graph. And also you may want to take the second derivative at a point, or the second derivative, set it equal to 0, because then that'll give you the inflection points. So all these things, that's what we're going to do. We're just going to look at putting this all together into your calculator and setting this up so that you can just put in one equation and then just run the code. All right, now that I have that original equation, I can go through and see all these different things, because if I'm trying to answer specific questions, each of these is going to give me the information that I need. So let's take a look at how to put all this together in the code.
Notice in any of your Colab notebooks, up in the top left, you can click on this for the table of contents. So we put all these, we already had limits and everything we did with limits, graphing. So now we get to derivatives, and over here, so we see what I did here is derivatives. If I double click this, one hashtag, so that's our heading, and then to make everything indent, the next things are two hashtags, a heading, but it's indented under this one. So that way you could minimize all that, or minimize just one thing, and we have all the headings. So you would go to your table of contents, what do you need to do? And if you go to derivatives, we can even X out of this, and we have the first thing. Hey, what do I want to do? Remember, we went through all those different derivative formulas, but all of it boils down to this code here. I just wanted to display the y equals equation. So all this importing, again, my symbols, I use x and y, but for the next few steps, I probably won't use the y variable. And whatever the derivative, you just put the equation there. This would be the y equals equation. And I just have this extra printout that this would be y equals, and then it displays the equation. Then we get to the derivative. Notice that I just completely did as a separate thing here. So equation, the derivative, sympy.diff, and I just had it print out here, the derivative equals. And then just so if you go back to and look at it, you'll see y equals, if you're making yours, you could eliminate that print statement if you want. So we display the equation, display the derivative, find the derivative at a point, and then you have your one line here, x value, pick an x value, and just put that right there. And then all the rest, derivative.subs, and then it will print out the slope at x equals this is this. There we go. it probably will look okay, but you could put another space there. Just to, you know, this is where you could always tinker with that output and have it display. So we find the equation, the derivative, slope at a point, set it equal to 0. Again, common things you might want to be doing. So I still have that derivative. So make it an equation, sympy.eq, set the derivative equal to 0. This will display it, and you'll see the equals 0 equation. And then solve it, because now that's first, and then we'll solve that to get the zeros. Again, the way that outputs, you could see multiple values. So at this point, we could plot the original function and the derivative. And if you just wanted to plot the original function, you could just delete something here, or you could add another code block here. Maybe you wanted to display the original function and then graph just that. That's also possible. Original function and its derivative. There we go. Remember the one line of code to plot it. So it will center it nicely for you. So now we get to the second derivative. And that's why this variable here was called first, because it was the first derivative. And now we get to plot it. Now we get to the second derivative, because sometimes that's important. So I just made this long variable named second derivative, and there we go, just sympy.diff, take the derivative of the derivative, display it, find that at a point, we go through all the same things. There we go, second derivative dot subs, and there we go. It is the slope of the second derivative, so you could keep that word in there. And remember, at a point, it was really the inflection. It's how quickly is the slope changing, but it is the slope of the second derivative if you wanted to keep that word there. Second derivative set equal to 0, because that also gives us, and now that's why I use that variable second. So sympy.eq, set the second derivative equal to 0, find the zeros, sympy.solve, and then output that. I did use the same variable here, zeros, because the other one would have already printed out, so it's okay to overwrite it. You can always change those variables. And then I decided to plot all three functions. There we go. Because then sometimes you can see that, you know, the y value of the derivative is the slope of the original equation. The y value of the second derivative is the slope of the derivative. And, you know, other implications here. So you see all of these, and then that way, you know, derivatives, you see all the things you want to be able to do with it, and you can jump to one of them if you want. It kind of all builds, so it kind of makes sense to just go down the list and, you know, you start with one and do all of it. And then I have all of it for implicit differentiation. As you see, hashtag, that's its own heading. And, you know, just the setup here. All those, all the same code, equation equal to 0, and then sympy.idiff, eq, comma, y, comma, x, takes the 3 arguments there. Yes, I want to plot it, plot implicit. So display the equation, plot it, find the derivative. So notice this one, I did want to plot, whereas the, you know, it just helps. Finding the derivative, an xy point to find the slope. So you start with an x value, and looking at the plot or having an idea of the equation, just what x value, pick an x value that will work, and it will go through and find, like we were doing before, put the original equation, you know, substitute that x value in, then that becomes x part, then set that equal to 0, sympy.eq, set the x part equal to 0, that's the y part, solve the y part, get the y value, and then you print the y values. So now we have an x value and a y value. You can loop through those y values and print out the slope at this x value, y value is the answer. Y loop, because that's what it's doing here. All those different y values, each of them become that variable. And again, just the variables I picked, you can slightly vary them. That's the idea, that you want to understand this well enough that you can put in your own values if you want. All right, so notice we're going to get the slope at a particular point, maybe a few different points, and I will plot the equation. Now notice this is just the equation, which you could have just plotted this here. That actually works, but this is another way to have more arguments in here. Especially, you need all these extra arguments when you start throwing in, a couple points here. So I want to plot this equation, but then I also want to plot these markers, which are these points. So, and because this got really long, and Python convention is that the lines of code shouldn't be so long. It even gives you that line here to guide. So I could continue this past that line, but Python convention says keep it shorter than that. So I just made these two other variables. I could have just stuck with these variables. And notice of that x value, I'm going to pick one of the y values. I just picked the first one, and just storing them so that when I plot them here, that's a little bit shorter, and I took out all the spaces. So there we go. Very often, I might want to plot the original. I might want to plot the original at a particular point. But we often, for the implicit differentiation, we often don't really plot derivatives or second derivatives. I mean, you absolutely can go back and find that, we have the derivative, and we absolutely can go back and find the second derivative if you want. Sometimes that's just an interesting exercise in doing that, but usually it's what's the original graph look like, what's the derivative at a particular xy point. That's usually what we'll do for implicit differentiation. So there we go. Now you have it. As we've been going through a lot of different examples, but then you can put it all together here. You're ongoing building your calculator, and then you come across other things. What are the things you're going to need to do? Oh, yeah, I might need to find a limit. I might need a graph. I might need to find, a lot of the other applications to answer the questions. What are you often needing to do? Derivative, at a point. So now we're ready to go, and we can get into some other applications of this and using these.
So we're just going to look at an example here of putting all this to use with like one particular equation here. So y equals x to the third minus 9x squared plus 24. So let's say, your math intuition tells you see the x to the third power and other stuff. So you get the general sense that the graph looks like this. But more specifically, without just graphing it, it looks like this. Where is that maximum value, the local maximum, and where is that local minimum? I remember it's local minimum or local maximum because this will continue on forever, and then that's going to be the absolute minimum, and then this will continue on forever. That'll be the absolute maximum. But what x value gives us this maximum, this minimum, and then this inflection point. Because if we look here, this is concave down if I look just this side. And so then if I look at this side, it's concave up. Well, somewhere in there, it changes from concave down to concave up, and that's the inflection point. So we get that from the second derivative. So what we're going to do is we're just going to take this, and we have this general sense of what this graph might look like, but we're going to walk through the steps and look at this, look at the equation, look at the graph, take the derivative at a point, set the derivative equal to 0 to find the local minimum and maximum, and then we will take the second derivative, look at the inflection point, and put it all together. It's just putting together pieces of the puzzle for things you might want to know about a particular equation. So let's take a look at how to do this in the code.
So this is how we can put it all together and use that calculator notebook that you're building to calculate the derivative and just whatever you need to know about a function. So all within the derivative, all of this code you'll keep, and if you just keep that variable as EQ for the equation, all you need to do is change this. So we'll put this equation here, x cubed minus 9x squared plus 24. And just, that's written in Python. So if you want to display, it might be a good idea then to display this. And, there we go. We see it, nice math print. So now we're just going to build upon that. That's the equation. And then when I do the derivative, I'm just going to plot that equation. So I don't have to change anything. I have this notation here you'll see in a second. Because the Sympy, it's great. Look at that. Plot it all with one line of code. But it seems to compress it a lot. See how really big this y-axis gets? Negative 250. So if you added these parameters here, and if you made that y limit, so what's that minimum? I want to at least see this turnaround. So I might even just call it negative 200, and that's going to be plenty. And then the maximum, let's even try negative 100. And then the maximum would be 100. And we remember that I need to close that. So you see we added this other parameter, and there's other ones you can add, but this is kind of the big one, either xlim or ylim or both, so that when we plot this, we really see, instead of stretched out, that y-axis is negative 100 to 100, and now even that is still way more than that x-axis, but it's enough that you can see that nice turnaround, and that's kind of what we want. Like, what's this graph look like? So there we go. There's the equation. Plot it, and what's the derivative? So we'll have this just built in here, derivative, and all this. It's, I'm taking the derivative of that equation. Nothing needs to change, you just run it. So once you put the equation in once, it should be able to cascade down nicely to each of these. What's it look like? What's the derivative? And slope at a point. Now, I just put a default in here, x value 0. And you could pick a point here, oh, what do I want? Well, what's the slope at 2? I expect to be kind of a steep negative slope. Whatever value you want, you can put in here, 2, and slope at 2 is negative 24. Set the derivative equal to 0. Now, again, just in 2 steps here, just to show that that's what it looks like, and then solve. We're going to solve that one for the critical values here. So we see 0 and 6. So when we graph the original function and its derivative, now I can put that limit in there if I want again. Because again, it's not, it's kind of compressed. And look at that, even just this little bit is 500 to negative 500. So maybe I want to put that in there, negative 100 to 100. That's probably going to be plenty. And it's only on the y value. So you can do this on the y or on the x. And we see just adding that other parameter. So we still see that nice curve, and we see this, so that the derivative, we see the y value of the derivative is 0 right here where the slope should be 0. And we go down here, over here at 6, because we found that exact value, that right here the slope should be 0 and the y value of the derivative is 0. So we found those values at 0 and at 6, and then we see what it looks like together with the graph. And second derivative, so I just take the derivative of the derivative, and there we go. Second derivative at a point. Yeah, I'll put this one. The y value is 6. You can leave a default value in there, but at 6. And second derivative equal to 0 at 3. And we see that's the inflection point. Up to here, it's concave down, and somewhere in here it changes to concave up. Where is that point? I set the second derivative equal to 0. So the second derivative at a point, I still kept this as slope. It's the slope of the first derivative, though. And second derivative equal to 0 is 3. And we can plot all three functions. You could still get in there, manipulate it, and add things, but you have a lot of it just already in there built in. And that's what we want to be able to do. Just go through and, you can even take out this y limit if you want, but the big thing is that you start out with just changing this equation. If you didn't want to change that y limit, you can just go through and it cascades down, see everything you need to about derivative, second derivative, what all the graphs look like, and you can apply that to all sorts of things, which is what we're going to do. So let's take a look at some other applications.
Let's look at a financial application here. And you would need enough information, enough data points to get this equation. But let's just say, tickets to a concert. So if you had enough information about all these different concerts and, how many tickets were sold, what was the price, find some way to get some correlation or regression line and develop an equation like this. I kind of made this up from some information that I've seen. Don't take this as oh yeah, this is a good use. But with some data points, you can find something that you can develop an equation like this. And that's kind of the key link to this, to some financial applications, some data science. This is what data scientists might do. Can I get all that information to develop this equation of supply and demand? Can I get an equation for this demand? Because then I can turn this into a y equals equation. Oh, okay, y equals 31,500 minus 100x, let's say. And then we see that, might not be perfectly linear, but that's okay. That gets us a good example here. Because, if x is the price, maybe a lot more people would go if it's free, if the price is 0. So there's a little curve there. And then whoever it is, there's definitely going to be a price that is so expensive that, people will decide, okay, I'm not going. So if I have this, then for the concert promoters, the business side of it, they want to maximize their revenue. And what you want to get into this point is anytime you hear minimum, maximum, you want to think calculus. So maximize the revenue. What is my revenue? It's the demand. How many tickets did we sell times the price? So I could have that, equals the demand 31,500 minus 100x times the price, which is x. That's what we said here. So if I have that, and let's just distribute this, 31,500x minus 100x squared, I'll make this its own y equals equation. And again, your algebra, your math intuition might tell you, hey, negative x squared, that this graph is going to look like an upside down parabola, and there is some point there, some price that maximizes revenue. What we want to think is calculus, okay, y, and then, shorthand for the derivative, I might do y prime. And all these are just power rules, so that'd be 31,500 minus 200x. And then that would be the derivative, and I would set that equal to 0, solve for x. And we remember then that that would just maximize it, and then a little bit more, a little bit on either side. We're getting close to that maximum revenue. So this is where people might make that decision. Oh, okay, well, anywhere close to that maximum revenue, what's the size of the venue? Is it worth it to go to a larger one or a smaller one? Because we might not always exactly get that number. We could try, hey, what exact ticket price maximizes that revenue? But there's a lot of other factors. We want to do the math, but life doesn't always work out so neatly like that. But as an example here, so we'll take a look at this in the code and just see how you can actually set this up, that from some other source, if you were able to do that, get that regression equation, get that equation, that then you could set it up that then it would just cascade down, that once I have that, I can figure out what would maximize that. And people would do this for all sorts of things. If I can get enough information, what price should I charge for something? So that's using calculus for the financial applications. But let's see how we can work this out and get these answers in the code.
So here's the example I have for you here. This actually comes from somebody online who actually wanted to ask a question about his particular store, some product. They raised the price from $6 to $7 and noticed that demand dropped by 4 people. So the question is was that a good move? Or the larger question is, what would be the price that would maximize revenue? So, I mean, if you wanted to just maximize customers, then, the cheaper the better. But to maximize revenue, there's a price in there that, you see, that price, $6 times 480, there's the revenue. $7 times 476, that would be revenue. And we'll look at those and check those later on in this example. But we'll say that, there might be a whole nother price that would maximize revenue. And the way I have this set up, that if you just put in different prices, so as an X value, because if I were to graph this, X price 1 and Y is demand here, Y demand 1. So if you have 2 data points, there you go, price demand, that's enough, because the more the better. But really what we're doing here is we're doing a linear approximation. So if I have 2 points, I can figure out the slope, and there's my slope formula, and then I can figure out the y-intercept. Remember, y equals mx plus b, so it's that y value minus slope times price, or y minus mx. So then I can print out the demand equation. There we go. And we can check the math. This works out. So the y-intercept would be 504, but that would be a price of 0. Nobody really wants to give away stuff. And yes, we see an increase of $1, decreased the demand, decreased 4 customers, so that's why the slope's -4. So we see this, there we go, and I have these as definite numbers, so now when I want to get them to Sympy, I really want to put them into that equation so that I can solve. I like the way Sympy solves. That's really the theme we're going to be going for in a lot of the stuff in calculus. Sympy does a whole lot. So I import Sympy symbols, x and y as my symbols, and my estimated demand equation. So, y equals mx plus b. Slope times x, which now is a symbol, and then plus the y-intercept. So now that's my demand equation, which then I could print that out. I'm not even worried about that. I'm going to generate my revenue equation, which is the x value times demand. And that's what I'm going to print out here. So there we go. With Sympy, instead of putting the -4 first, it puts it second. That's fine. And it doesn't distribute. It just says x times this. There's my revenue equation. And you might remember from algebra, when we distribute, that's going to be a -4x squared. And get that up, that parabola that opens down. So somewhere in there, there's an X value for price that will maximize that revenue. And that's what we're going to find out. So max revenue. So the calculus answer. Once I have that revenue, take the derivative with respect to x in this case, and then sympy.solve automatically solves it for 0. So there we go. So I'm going to set that as max x. That's my x value that would maximize revenue. Then I'm going to take that and I'm going to go to the revenue equation, substitute in for x, max x. And I store it here as the variable max x, but the way Sympy works, it has to be max x and then that 0 in the square brackets, because it really is an array. There could be multiple zeros, there could be multiple answers. So even if there is only one, and in this case there is only one, I still have to put it this way. So now I solved, there we go, maximum, right? Calculus, you see here, minimum or maximum, take the derivative, set it equal to 0, and to get that y value, I'm going to go back into that revenue equation and substitute in that x value. So there we go. All these things that if you couldn't already set this up with code, that's you get into a bunch of factoring, some tedious calculations. This is already set now, and we're going to set, here's the maximum revenue is this when the price is this. And we get this surprise. Maximum revenue, $15,000 when the price is $63. Now, this might sound ridiculous for some item that he was talking about going from $6 to $7. But the math of this works out. And so looking at this, I just did a quick check here. And, you can even leave this in here. Maybe, you doubt some of the answers you get, so you can leave this check in here. So the revenue 1, I'm just going back to those original equations. Price times demand. Revenue 2, price 2 times demand. And then revenue 3, rather than relying here, I am just going to use that x value times demand. And I needed to do that substitution here too because the demand also had that x. So now I'm going to print this out, but also I'm just going to actually solve for demand because I think this is interesting too. Given that demand equation, where is that 0? And when we do this, the numbers really just confirm everything, even though it just seems ridiculous for that $63. That revenue, $2,880, or revenue 2, $3,332. Now, at the very least, for that person's specific question, I see that raising it $1 lost 4 customers, but the revenue absolutely increased. So for that specific question, then that's answered. Yeah, keep it at $7. This takes it even further, saying, hey, you can raise it up to 63, which is kind of ridiculous, but we'll talk about that in a second. And the revenue 3, just the way we do this, it just confirms, yeah, that would be the same 15,000. So what did I do here? Demand, not subs. So this one here gives me that demand, just because I wanted to see that too, 252. So we do see that, yes, from the original demand of 480, and then, yes, we are losing, let's say, every $1 increase, we lose 4 customers, that it really would be, if the price was $252, that would be, that's where the demand equation goes to 0. So, that's the point where people be like, oh, that's so ridiculous, there's no way. But it comes back to that, yes, the demand definitely decreased. We were talking 480, the original, we're saying from 480, 476, every $1 increase. And it goes down, yeah, you only have 252 people to take it even further, I just was curious about the 0, the 126. So if the price was $126, nobody would buy it. But this is just interesting. It shows that, yeah, 252. And then if we do this, do that 252 times 63, the price said it should be 63 times 252, you actually get to that 15,876. So, that works out too. So what can we do with this information? Does this really mean that this person should make this item that he was thinking of $6 or $7 be $63? Probably not. Though, here's the danger of it. Even though this particular one seems to be very extreme, what happens is people can do this math, and people do, and if they have enough data to really confirm that whatever they're selling should be a lot more expensive to maximize revenue, they'll do it. And there's greed's part of economics. So people will maybe try it, make something really that expensive. But the idea that we could it answers that simple question, yes, was the slight increase worth it? And the answer to that simple question is yes. What should that price be? I mean, if we're saying $63 seems extreme, then really anywhere, whatever that person decides to increase that price, it's probably going to be just fine because it's still on the upward slope. We really need to also have that human interpretation here too. Just because the numbers say I probably could sell this for $63 doesn't mean I should. The way that this is set up, if we're doing this based on 2 data points, you just need to change these values here. And everything else, I have it set up in separate code blocks so you can run each part and see. But if you just change those 2 values, run each code block, and then you can see it gives you this answer, but then you can get that analysis. Because if you're running a store, or if somebody running a store hires you to look into this, you want to be able to get the correct numbers, but you also want to be able to provide the human insight and do the full analysis. So that gives you an idea. And as with so many things in calculus, this is the main, there you go, one step of calculus right here. Remembering that minimum or maximum means take the derivative and then set it equal to 0. So there, and then the next line setting it equal to 0. All the rest of this, we're certainly now getting into Python code, but then it's algebra, Python code, one line of calculus. So, in doing calculus, there's definitely so many other non-calculus parts. And, I want to make sure that, you're ready with the human insight to fill in those gaps.
Here we'll talk about one of the physics applications that really goes back to Newton and some of the things that he really developed as an offshoot of calculus, was really calculus being the language to explain some things happening in physics. And so we have a general projectile equation here that, and this is upward motion if I launch something straight up in the air, where there's other equations that vary based on the angle. We'll look at them too, but if I had upward motion, so this position equation, where is this projectile? And really, if it's upward motion, that's position is the height at any given point. So y would be the height, and then x in this equation would be time in seconds. So this first part, negative 4.9, because we'll do everything in meters, so that's half of gravity. And we'll look at why that's half of gravity in a second. But negative 4.9 x squared, and again, x is time in seconds. That will be the same number in any of our equations because that accounts for gravity. V for initial velocity. So I'll leave that open there as, that could be whatever number we put in there if I know the initial velocity. And h would be the initial height. So something starting at ground level, h would be 0. I could even, drop that out. Something starting on a cliff, let's say, or somewhere up in the air and then dropped, then v would be 0, and then that term would drop out. So you see, that's it. H could be 0, v could be 0, but we'll put it all together as, anything that's possible in this equation. So, and we see that, anything launched becomes a parabola. We get that negative x squared. And that's the thing. It really always is a parabola. So then let's talk about the calculus. Derivative of this. And I'll use that shorthand notation y prime. So if this is the position, how quickly is the position changing? Y prime is velocity. So I have velocity, and this is power rule. So what do I get here? Negative 9.8 x plus v. H would be that the 0 drops out. And now we see this is gravity. So we have that, what's my velocity at any given point? It's that initial upward velocity minus gravity. So gravity keeps working against it. You have that initial upward velocity once, but then gravity keeps working against it. So it will get to a point and then turn around and then come back down when it, can't overcome gravity. And then we look at escape velocity for, launching something into space. How much does it have to accelerate to escape that to the point that the height it gets to, it's beyond Earth's gravity. But, all these things kind of start with equations like this. There we go, I have velocity. So again, if something was, dropped from somewhere, then the initial velocity would be 0. And we really just see, something falling, it keeps accelerating. So 9.8 meters per second going down, and then it's going faster. 2 seconds, it's going, almost 20 meters per second, etc. So that keeps falling. And then if we take a look at this, the derivative of this, how quickly is velocity changing? And that would be acceleration. So that would be the second derivative, and that's why I use y prime, because then this will be y double prime. The second derivative is, that drops out, and then this is really just negative 9.8, gravity. So we see this, that I have the position at any given point of a projectile, either launched upward or dropped, and velocity, I can figure out the velocity, and then the acceleration. And what we do is then, given these, maybe if I knew the time, if I threw something up in the air and I calculated how, to stopwatch, how long did it take to go up and then back down to the ground, then I would know, in this case, I would know x, and then I can figure out the initial velocity. I would know the initial height too. So if I knew, how long it took, I can figure out what initial velocity. Oh, I threw it up in the air. I was wondering how fast I did throw it. Well, I can calculate that. Or if I knew the initial velocity, I can predict how high it will go. Because there we go. At the top, velocity is 0 for that split second, and then it drops back down. So position, how high will it go? Maximum, derivative. Take that derivative, and set it equal to 0. When that velocity is 0 for that split second, it's at the top, and then I can figure out that maximum height. And then it comes back to gravity then. So we'll look at a couple examples of just how to set this up in the code so that you can plug in some different numbers and, figure out some things that you don't know. So let's take a look at how we would apply this in the code.
So here's how we can put this together. And this is all very similar code to the general calculator notebook that you'd be creating. We're just modifying it here, making t the symbol, because time. And I'm just putting in these numbers for initial velocity and initial height, but it really could be any numbers here, and then you just put in whatever velocity and height you want. And our position equation as the original, so we have that negative 4.9 t squared, that will be a part of it. And we just put in here times v plus vt plus h, and that would get plugged in here. So you can run this and see that equation. And the derivative, well, we'll call this one velocity since we're using this for a specific application here. Derivative, and we're just going to output velocity as this. There we go. At any given point. You could also, at any point, put in another block of code and that velocity dot subs and plug in a value. What's the velocity at any given time? And here for the height, remember, taking that velocity and solving it for 0. So it will automatically, if you just say sympy.solve velocity, it'll automatically say, yeah, okay, that set equal to 0. So we can get that height. And once I get that x for the max height, I will get the max height by plugging this in. I'll take that position function, that original, substitute in that max height. It will be an array. That's why I have to have that 0 here, because there could be multiple answers, so it allows for that. So I'm going to plug in for t for that. I expect only 1, so, max height 0, that first answer. And I'm going to print it out so we can do this. And you see, we get, where is that max height at this many seconds? And the max height at this point is, all in meters, 17.79. So this is just for fun. Acceleration is gravity, negative 9.8. So there we go. So really you can see, you can have other notebooks if you want for various applications. But this is just one example for our physics applications, and there's many more.
Here we're going to talk about just one slight variation on the derivative, but this becomes an important distinction, and we'll revisit this again in some future topics. But it's the differential. So if I have my y equals x squared, and we take the derivative, I'll call it dy dx equals 2x. But then I really want to take the dy dx, that's its own thing. The derivative of y is dy dx, and that's the slope. The derivative of this is 2x, and there we go. But if I do decide to split it up and say, oh, instead of dy dx as the slope, I want to call it the differential, and I'll say dy equals 2x dx. You see, we just multiplied by dx on both sides. If I do that, and we'll see this come up in just a couple applications here and there, then I really do need to go back to the linear approximation. So here I can just say, yeah, that's right, the derivative, slope at a point, calculus. Here, even though I did this and I know that that's calculus to get to this, I do want to go back into what is that exact little change in dx that I chose and plug that back in, slope formula, derivative by definition. So just knowing, derivative, differential, these subtle differences, that's just an important distinction. But in putting this into practice, we're really going to look at this in the code and just see how we can write some code to do that when I need that linear approximation to find the derivative at that point for some, exact value of dx that I choose. So let's just take a look at how we would apply this in the code.
So here's what this looks like in code, and we'll use that similar example, y equals x squared, derivative is 2x, so then that would be dy dx, so then dy is 2x dx, splitting it up like that. And we'll set it up here in a way that, these imports, this equation, you could use this again for any other equation besides this, because then we'll just set up EQ, take the derivative, great, and now looking at the differential, we can just pick any x value here, and dx, how how many decimal places you want. This is probably fine. And so dy, so let's think back to the slope formula. So dy here, we'll calculate it this way. There we go. Going back to that original equation, subbing, for the x value, x value plus dx minus that original subbing x value. So we have, change in y is the true dy. And knowing calculus now, hey, if I just want the slope, I'm going to take that derivative, substitute in for the x value. And so that's just the slope at that point. This is our go-to, that's what we want. But we're going to show how similar these other answers are. So I'll print out that slope, which is using the derivative, that's going to be our go-to best answer. But to compare dy dx and this way. So I will have dx up here, whatever I defined it as, this tiny value, and then dy, and I'll actually just do that division. What's that answer? Or dy. And just going back to here, dy this way, and I'm going to print out dy the other way, which is, in this case, 2x dx, or that slope times dx. And when we run this, we'll see really how close they are. Slope is 4, yes, that's right. That's the exact. And if I did it this way, dy dx, it makes it really similar, just off by so many decimals. And dy calculating it one way, we see again dy calculating the other way. So all these, if I take it up to 4 decimal places, they're the same answer. But it's beyond that I go, and that's probably not much of a coincidence that, that's how many zeros I had here. So just another way to see, how this works. And sometimes the differential, you might get in a situation where you want that differential instead of just the derivative. And you can use this code to do that.
So sometimes we want the equation of the tangent line, and that could be the tangent line is the straight line that touches that curve at exactly one point. So we're going to get to a linear equation here. But sometimes that line is just, I want to see that tangent line, but sometimes it actually just has to match up. Like, let's say I wanted to design, a highway or a roller coaster that has a curve, and then at some point it straightens out. And then from that point on, I want it to be, linear, perfectly straight. So that's only going to happen and be nice and smooth if at that point the slope is the same. So what can I do? I can take the derivative here, I'll just say approximate it with x squared, and then there's the derivative is 2x. So at that point, I have to define, what point do I want? Let's just say I want it to be where x equals 2. So when I plug that in, times 2 is 4. So at that point, the slope is 4. So I want to see, okay, for that point, x is 2, the slope is 4, but then I need that y value. So I'll move this out of the way. If I have x is 2, 2 squared, y happens to be 4 also. And I want that linear approximation, so if I have my x value, my y value, and the slope, yep, it goes back to y equals mx plus b. And you might be thinking, hey, I thought I was doing pre-calculus with Python, or calculus with Python. What's this algebra stuff? Yes, algebra comes back up. We're doing a lot of stuff even in code with Python, Python to do your calculus. But if you weren't writing code to do all this, there's a lot of problems that are like one step of calculus and a lot of steps of algebra. And some things like this, hey, we used calculus to get the slope at that point, but this plugging in stuff, that definitely goes back to algebra. And then I want the equation of that tangent line. That's a linear equation. There's my go-to, y equals mx plus b. So then I know my y value is 4, my slope is 4, my x value is 2, and I'm going to solve for b. So 2 times 4 is 8, subtract 8 from both sides, so then I get negative 4 equals b. Now I have all the pieces of the puzzle, so I can put this all together as y equals 4x minus 4. A little throwback to algebra there. But you see, like you think you're done with algebra, it comes back up throughout calculus and other math courses. So we're going to look at how to do this in the code that, take the derivative, get the derivative at a point. We've been doing some of that, but then also get that actual linear equation at that point. So bringing back, just plugging this in, plugging these values into the equation we need to, getting these values, getting the linear equation. And yes, it ends up being these quite a few steps. That's really what calculus ends up being, and math from here on out, quite a few steps. So then, hey, if I can write a few lines of code to do this, then maybe I can get this point to ask that question, slope at a point. If I plug in, my particular equation and a value, an x value, the code would then do all this for you. So that's what we're going to look at, how to do all this and set it all up using the Python code. So let's take a look at the code.
Here's the tangent line equation in code. And we see in the beginning, we're going through the usual imports, set up the symbols. I'll stick with calling the original function EQ. And we'll stick with this one as an example, x squared minus 4. So we'll calculate the derivative. And I'm going to pick a point, some x value. So what am I going to do? I'm going to substitute that in to get the slope. In the derivative, I'm going to substitute. And then I'll substitute that in the original equation to get the y value. So now I have, all you can set this up, and all you have to do is change whatever equation you want and what x value you want. And there we go. We go through the substitution. Now I have the slope from the derivative. Now I have the y value, and y equals mx plus b. So y minus mx gets you b. So the y value minus slope times the x value, and that's b. And we're going to output this. So for our equation here, there we go. We just run it, and there we go. Y equals 4x plus a negative 8, 4x minus 8. There we go. And all you have to do is change that. Maybe I want just a basic x squared. And what's my tangent line equation at an x value of 3? There we go. Plug it in. Y equals 6x minus 9. So there we go. The slope at that point is 6, but the y-intercept is all the way down to negative 9 because of that steep slope. And there we go. So you can set this up, again, very often. Some things we want to do, get the tangent line equation. So we can just change whatever my original equation is and what x value and go from there.
Now, parametric equations, para meaning going around. So parametric equations have something that I can graph on an xy axis, our normal Cartesian plane, but I can define x and y as their own equation, each as a function of t, which is time. So I can have my two equations, x defined by some equation, y defined by some. They can be any equations. So on the xy axis, on our Cartesian plane, we can see things that look like not a function. I can have circles. This actually would be the graph of a circle. But then each of them, time is the one variable that increments sequentially. And then okay, now that time is 0, then 1, then 2, and it's continuous. So even the in-between values, time can be whatever. And then once I know that time value, I can figure out x, time value, then I can figure out y, and then I would plot that xy point. So let's talk about this in relating calculus. Then if I would take the derivative of this, great, I graph this, and this happens to be a circle, but now that I have these points, what was the derivative mean? Well, if I have this derivative, let's do the y first. It would be dy dt. So not dy dx, but dy dt, because t is my variable here. So the derivative of sine is cosine. There we go. And I'll just put the other one here. The derivative of x would be dx dt. So again, we see things, each of them is a function of time. And derivative of cosine is negative sine of t. So I have my two derivatives there. Derivative of cosine, derivative of sine. Great. But how does this dy dt and dx dt relate to my slope on the graph, which I wanted to be dy dx? You say change in y over change in x, because it's still, these are separate, but then I graph them together as this one xy point. So I can look at this, and what if I have dy dt over dx dt? Dy dt, and I'll put a big line here over dx dt. So if I have, the fraction over a fraction, dy dt divided by dx dt. Well, what does that equal? That would be dy dt times, dividing by that fraction is multiplying by the reciprocal, times dt over dx. You see, dividing and then multiply by the reciprocal. And when we do that, dt cancels out. So then it really is dy dx. And what is dy dx then? It's this derivative divided by this derivative. So in our specific example here, so when I do that, when you do parametric equations, you would take them and then take the derivative separately relating to t, but then the derivative, the slope in that Cartesian plane, dy dx, is my dy dt, in this case is cosine of t, over dx dt, which is, in this case, negative sine of t. So that would be the graph of my equation then. And there we go. We see that we can graph these. We'll also look at in the code as how do I do this? How can I separate this out in a nice way that it works every time? Defining these variables, now I'll define t, and we'll define these as separate in the code. I'll have different equations here, and then take the derivative. We'll look at how all this plays out. But you see, this is how it comes together as parametric. X and y are each defined separately, but I'll still graph that as xy points on our Cartesian plane. So I'll take the derivative separately, but again, I can still combine that, and we can see how those two separate derivatives actually do combine to get dy dx. So pretty cool how it all comes together. And let's take a look at how to put this together in the code.
So parametric derivatives, I'm going to do this first part here, just the usual imports, x, y, and t as symbols, and I'm going to define y as this function of t, x as the function of t. I'm not going to worry about any output here. I just want to run this and just have it that this is my x and y. Then, just to see what the graph looks like, because I'm going to graph those on an xy coordinate, here's one way to do it, and I want to introduce this because sometimes you might have data that's an array or other lists or values. So this is how, my x and y values, empty arrays, and I'm just going to loop through it for some a value, for angle, and then I'm going to come up with these, xt. I'm going to substitute that in for t. And what this is really doing, because I did sine and cosine, I just had like pi over 12 as the increments, 1 pi over 12, 2 pi over 12, etc., and go around the whole circle. So that's just what I did here with this, and, the range of 36. So, substitute in for t in my x equation and then y, and then I'm going to append that to my array, and then plot this. Notice I imported the matplot library to plot these. Again, I want to show it works better for an array, and then you see, just because of the limited number of values, we see it not a nice smooth circle. And now let's look at the Sympy graph. So I can go right back to this. I could even, since I have that, I could just put the graph in here right away if I wanted to. And from Sympy, if I haven't imported that yet, import plot parametric. And there we go. Plot parametric. What am I plotting? X, Y, and then as t goes from 0 to 2 pi. There we go. And so we get that nice smooth graph because it has all those values. So you see we can have those. And just, I wanted to show you this, but you could easily put that with the import. And once you have the first two, just, automatically plot that so we see what this looks like. And separate derivatives. Here's another one where you don't have to separate these. I mean, you definitely want to have, there's my dy dt. I made that a variable, sympy.diff, the derivative of y with respect to t. And I'm just doing all these separately just to show that. There we go. So the derivative, we know it's sine, so the derivative is cosine. And then this one, dx dt, derivative of x with respect to t. Derivative of cosine is negative sine. And then dy dx is dy dt over dx dt. And I just made these variables so that we can just see each step. This is another one. You could put all this in one code block. There we go, dy dt, dx dt, and then this one, and maybe display it at the very end. So there we go, and now I have that dx dt as this. Now, cosine over sine is cotangent. So this could have been negative cotangent, and Sympy does simplify trig values, but certain ones it just seems to be resistant to. I don't know. It's kind of funny. So it won't put out cotangent. It'll just do this as cosine over sine. And there we go. But now we have this. That's stored as dy dt, dy dx. And so I can put this, import math. And I'm doing this to, again, compare some different things. Here we go. I'm going to substitute for t. So now, to get the slope, I'm going to substitute here for t. And this is why I imported math. I want to show you these different answers. If I want that numerical answer, I'm going to use this math.pi over 12. I just decided to pick that value, pi over 12. And then I'm going to print out the slope. I'm using actually the same variable because I have this and I print it out, and then I'm just going to overwrite it again. So substitute again, but this time notice I'm doing sympy.pi divided by 12. And then I'm going to output the slope. So we see the math.pi, it's going to give me a numerical answer, and sometimes that's what I'd rather have. And Sympy will give the exact answer, including radicals and however weird it gets. That's the exact answer. So there we go, just showing you a couple things along the way. But this is really, parametric equations. You really could just, right from the beginning, you could shorten this a little bit and have, define your x and y, maybe a lot, another import, and then maybe one line of code here to graph it. And then you could combine all of these, get dy dt, get dx dt, get dy dx, output it once. All that is one block of code. So this could all simplify and get shorter. I just wanted to show you, some of these in between steps. And then there we go. You could have, I think it might be nice to have both of these in, and I would comment out the one I don't want. But actually, you don't even need to do that. It'll do both. And you get the slope. So now we see you can set this up for any equation. I just picked sine and cosine. I feel like that works out nicely. But you can do this for any two equations. Parametric, graph it, get the derivative, plug in a value, and you'll be all set.
if you remember when we did implicit differentiation, so we still took, x is my independent variable, y is a function of x, and we took the derivative that way. But now we're going to say that everything is a function of time. So everything is going to be derivative related to time, and that's the related rates. Things are moving at different rates, but they are related. So if we take a look at one example of related rates, if you have a ladder, so if I have a wall, there's the ground, and I have a ladder, and there's a person on the ladder at the top. And this person doesn't know yet, but the ladder's about to start slipping. So when the ladder's slipping, so I can define this value here from the wall outward. I can call that x. Makes sense? It's horizontal. And this ladder, let's say, is sliding away from the wall at a certain rate. Then I can talk about my vertical distance from the ground up to the top of the ladder. So that is y. Makes sense. It's vertical. And when that's going away, this then is going to be sliding downward. Here's the interesting thing. They're not moving at the same rate. And, x is moving away, y is moving down, but then they're not moving, but they are moving, and it's relating to time. How many feet per second, meters per second are they moving? Whatever the rate, but it's going to be something probably per second. And there we go. That's, the change in x related to time, the change in y related to time. So in setting this up, what I can do is, let's set up an equation for the snapshot of the situation. What do I have? This vertical, this horizontal, nice right angle there, and I have my ladder. Definitely looks like a right triangle. So I'm going to do Pythagorean theorem, and I'm going to say x squared plus y squared equals. Now, the ladder won't change. Yes, I know there's some ladders that collapse, but we're going to say that this ladder won't change. So I'm going to give it a value. I don't know, let's say it's a 10-foot ladder. That way, there we go. Pythagorean theorem. But that's a constant, so I'll know that. So the ladder's not changing, but this is the situation at any given point. X squared plus y squared equals 10 squared. Wherever the ladder is, it's going to fit into this equation. So now let's talk about the derivative of this, because it's all changing. So the derivative will be the derivative of x as a function of time is going to be, I'll write it down here, 2x times dx dt. You see, because that's a function. So I'm doing chain rule. 2 times x, 1 less power, but then times the derivative of that function, and the derivative of x related to time is dx dt. So that's that derivative related to time. And then y is going to be the same, plus 2y times dy dt. And the derivative of this, or any constant, is 0. So that's the big thing with the related rates. Can I get an equation for that situation and then take the derivative with everything changing related to time? And if there's anything I know that's a constant, that helps, because that derivative of that constant is 0. Because even if I took this as z or something like that, another variable, and then I took the derivative there, when I plugged it in, as soon as I say that, derivative of that, and then times, dz dt, then how much is that changing? That's 0, so it would zero out anyway, because that rate of change for that would be 0. So now I have this, we draw out the situation, sketch it out, with this guy who doesn't know he's about to plummet, probably get hurt, but, don't try this at home, but on a marker board, that's okay. So, sketch out the situation, which leads me to my equation, take the derivative, everything related to time, and then I would know, at any given point, like maybe I know X and Y, or maybe I know one of the values, and then, how is each of these changing? Maybe I know that. So right now we see, 1, 2, 3, 4 things that I don't know. If I would know 3 of them, I can figure out the 4th. Actually, very often for something like this, I might know either X or Y, one of the two. And then I have to plug that in to this original to get the other one. Maybe I want to know, like, okay, I'm saying that, the rates are different and they're changing as this slides away and he slides down. So maybe I want to know, if this is in feet, then maybe I want to know, what's his change in Y, how fast is he sliding down when he's like 1 foot off the ground. That might be interesting. Or, maybe that, or when the ladder is so far away. These are some of the things. So I would know maybe it's the Y value that I'm interested in, when Y is 1. Plug that in to get the X value. Now I have those two, and I would then have to know one of the other two. Different situations you'll see, textbook or real life, that, I would know how quickly one thing is changing. Maybe I know how quickly X is sliding away, how quickly is that base, that ladder sliding away from the wall, and then I can figure that out. So, so let's say this is in meters, and yes, that was a really big ladder, 10 meters. So, he's up there and, worried, because he's starting to realize that he's in the math problem and he's about to start sliding down. So then I want to know, let's say, how, if I'm saying that this, I would define this somehow, that maybe I'm going to say that, dx dt, I'll put that over here, that dx dt equals 1. So maybe we'll say that how quickly is this sliding away? 1 meter per second. We would already know that. So I want to know, when Y is 1. So if I would do this, so then I have 2, when Y is 1, this is really what I want to find out, dy dt. So if dx dt is 1, so I don't have my X value here yet. So what do I need to do? I need to plug this in. X squared plus 1 squared equals 100, and X squared equals 99, and square root of 99, it's like 9.9 or something, close to 10, but not. So, if I put the square root of 99 times dx dt, which is 1, and then we can solve for how quickly he is sliding down that ladder at that point. So all of these I can divide out a 2 everywhere, and then I can divide out the 2 everywhere because that's 0, and I can then that's times 1. I can subtract that, so it would be that dy dt at that point equals square root of 99. Not quite 10 meters per second. So even if this is sliding away at a constant rate of 1 meter per second, this ladder is still sliding down, slightly accelerating, not like gravity because it's not a total free fall, but at that point when this guy's 1 meter off the ground, he's going that fast. Who knows? It might be like really close to 9.8 meters per second. But again, gravity would have been, just a drop. That would have been an acceleration, and he would have been going a lot faster than that. He would have been going that fast. If it was just dropping, he would have been going that fast, like right at the beginning. But no, just sliding down the wall while the other lights are sliding away. And so we can figure that out. So knowing the calculus, somebody else on the ground, who doesn't know calculus might say, oh, that's only sliding away at 1 meter per second. That's not that fast. He's going to be fine. But then you do the calculus and say, oh no, by the time he gets close to the ground even, that's going to be going he's going to be going pretty fast, and that's going to hurt. So related rates, saves people. But that's, this is the idea here, that all these things are changing related to time. So, draw out your situation, sketch it out, write the equation, and then when you take the derivative, everything is related to time, and we'll see how that looks in the code. Because Sympy will do this. I feel like it doesn't look as organized as this. You have to just be ready to decode the Sympy way of displaying it. But we'll take a look at that, and so you can see what this is and how you can plug in some values here, what this looks like and how you can plug in some values. And we'll look at how to do, this is a good straightforward related rates because the equation's Pythagorean theorem. And we'll look at this, we'll look at a couple other related rates examples. How we can set up the situation for things that are changing, but at different rates, but they're related to each other, how we can take the derivative, how we can do some substitution, and what all this looks like in the code. So let's take a look at the code.
So here's the example worked out in code, and you'll see where you need to have some calculus understanding. It'll display, but it's not going to do every single thing for you. And we'll use this example here. I'll just make it 25. So our ladder would be 5 meters, and then their squared is 25. So we are going through the imports. Notice I'm also importing symbols and derivative. We'll make use of that. And I want to use x, y, and t as our symbols. So I'm going to set up the expression. Remember, I want it to be equal to 0, so I include everything, just move it all over to one side. If I wanted to output the expression, I can make that the last line, comment these out, see that. But this is the derivative here. So remember, I'm still thinking chain rule beyond the code. So I want that times the derivative here of x with respect to t. And then we're going to do the same thing, expression derivative with respect to t here. And we see these different parts. So that first part got me the 2x, and then the other part got me the dx dt. And notice it just displays, it puts the x here, but it still takes it as one thing. And then that would be equal to 0 here. 2x dx dt, 2y dy dt equals 0. Here's another way to do it that I kind of like better. That one works fine, but I think this is a little bit better. And I'm using the same expression, same imports. So broken down here, the substitution works a little bit better. That's why I did it this way. So again, this XPR line here, I definitely need this. There's my expression, but this line won't end up doing anything because it overwrites it in the next line. But there we go. Just breaking it down into dx, dy, and then I have dx dt and then dy dt as variables. So you see, then putting it out this way, the derivative is this. And again, there we go. It outputs the same. I just like breaking it down this way. That might be a good, useful way. Again, you want to think about how this all fits together and the chain rule with respect to time. So I could just plug in, I could just plug in something if I want to just substitute, for dx dt. Or then notice this dx up here, I get the derivative, so it's 2x. And down here, I can plug in all the unknowns. Look at this dr.subs, and I'm plugging in all the unknowns. Notice the syntax here, the square bracket, and then each of the things I'm plugging in parentheses, dx, and then I'm going to plug in 6 for that. dy, I'm going to plug in 8 for that. And dx dt, I'm going to plug in 2. So you see, I get this. So notice, because I had dx and dx dt, so you see that becomes 6 and that becomes 2, and so that's why we get 12 here. So you see, we substitute for this whole thing, dx, this whole thing, dx dt, and it will multiply them as it is here. So then you have 12. And then with dy, I plugged in 8, but then I still have the dy dt. Now I've plugged in these 3 things that I know. I still don't know dy dt, and that's where I can solve. You see, I'm going to set this up as an equation equal to 0, and then solve for dy dt. And then I'm going to output the answer. And see, there we go. So then we get that -3/2. So that is the dy dt value of how fast is that ladder sliding down the wall. Notice I even had, like, I plugged in for this whole dx. So I would have to think about what I'd want to do. I need an x value, a y value, and they have to work in Pythagorean theorem for that ladder, which is 5 meters. So 3, 4, 5, like that's just what I did here as an example. But if you're thinking about what you're plugging in, you're still plugging in dx, the whole thing here. So it's not like some of the other ones where you're going to just plug in and just have it done. But if you have an idea and you're expecting what this is going to look like, then you can set it up a lot like this and then substitute for different values. So, that's really something to think about. All these related rates, there's a few key types, but all of them, it is that similar thing, derivative related to time. And, we'll do a couple examples. You can't do every single example, but hopefully you get enough of an idea of how to take this, what am I doing here to create this derivative and then substitute in what I need. So hopefully this is a help, and then we'll look at another example next.
One other classic related rates problem is inflating a balloon, because the volume going in, usually I'll have something like, I know the rate at which, it's inflating. But then what else is changing? The radius is changing. We could also do this with like surface area of the balloon or something else, but usually then we approximate it that a balloon, even though I know it's rarely a perfect sphere, but we're going to say that it's a sphere for this. So I'll take the volume of a sphere, 4/3 pi r cubed. And if we say that the balloon's a sphere, then, as it's inflating, the volume is changing and the radius is changing, both related to time. So when I take the derivative, it's related to time, then I have dv dt, how quickly is the volume changing, and then when I do the derivative of this, so 4/3 pi, that's still a constant, so I'm just going to do power rule, 3 times all this becomes 4 pi r squared times the derivative of this, which is an inner function of time. So times dr dt. And this is what it's going to look like if I was going to write it down. And we'll see what it's going to look like as we do the Python code, Sympy. So we want to remember that chain rule notion, so that sometimes if you have to work that a little bit, instead of just like plug something in and just what is Sympy output and take it, you want to have a sense of what you're expecting the output to be, so that when we look at how Sympy displays these related rates problems, then you know what's what. And we'll look at this, setting this up, what's that derivative look like if I do this with Sympy, and then taking it from there, plugging in values for, really, I just have 3 here, knowing 2, I'd figure out the third one. So we'll look at how to do this. This part then, the code might be straightforward. And notice how much is beyond the code that you need to do. Being able to set up the situation and say, okay, yeah, that's the appropriate model for this. Yes, it's a balloon. I know it's not a perfect sphere, but this will work. So many of these related rates problems, that first part, sketching that out, the figuring out what equation, sometimes that's even beyond the code. That's just human creativity. We need to take a look at, well, what does this look like? We're not going to necessarily get to the point where I'm just going to type in a word problem and it's going to output. Some of that we want to be able to figure this out. What equation is appropriate? What model is appropriate? What sketch? What do I kind of expect the derivative to look like so that when I see it, I recognize if it didn't, if I missed something, if I didn't do it correctly. We want the code to do something to help us, to be a time saver, but we still also have to bring our own intellect into the situation. So let's take a look at, how to do this. Just for this example, as a sphere, derivative, plug in, and we'll see what that looks like in Sympy. So let's take a look at the code.
And here's that volume example. Volume is 4/3 pi r cubed. So I'll just have this one block of code here that I'm going to import everything, set up my symbols, and just identify this expression that I want, because it's really going to be helpful to see it. And yes, this one, I want that 4/3. I'll write it that way because, that's really the exact, it's going to put it out like this as the 1.3 repeating instead of the 4/3. For our purposes, that's going to be okay, but not as elegant as I'd like. You want to see each step. You want to have a sense of what you're looking at, because it's not so much like click and set up once and it'll do everything. You really want to, be able to break this down here. Notice I'm going to break this down so the substitution in the next step works. I know I'm going to be taking the derivative of this. So I'm setting up this variable dr as the main expression .diff. So I'm going to differentiate r. Great, that would work out. I'll see that, and I'll take the derivative as r being a variable. Nice. But then remember, we know that r is a function of time, so I have to have this, and I'm going to put this as dr dt, its own variable, the derivative of r with respect to t. And that's where, again, you kind of have to have that chain rule awareness that, okay, I'm going to take this, I really want to set up as this separately, and then this, and then my full derivative, I'll put it all together. Notice I can just put this times this, and when I display it, that's exactly what it's going to do. It becomes 4 pi r squared times dr dt. Sympy displays it this way. I'd kind of rather it be the r also in the numerator. It is what it is. But that is the one thing, that dr dt. So now I can see the original expression, the derivative, and now that separate, I'm going to use that separation to plug in a value for r. So if I just want to plug it in here, I'm going to create another variable here, dr plugin, dr.subs, and in this original dr, I'm going to plug in 3 for r. And then now I'm going to just create this other variable plugin, which is, notice, dr plugin times dr dt. I didn't change that dr dt. I just plugged this in for this part. If you take it and plug it in a step later, it's not going to display well, and it might actually affect your answer too. So we really want to see, like, where am I substituting in and where do I still want to see that dr dt. So I'm going to do this plugin, and now we see, yep, I plugged in r is 3. So remember, squared is 9 times 4 is 36, and that's where I get that 36 pi. Sympy leaves that in there, times dr dt. Now, you see, we really want to see, you can still set this up for all these different situations, and we can, work through this. We want the Colab and we want the Python code to help us do the calculations, but it's, we still will need to have that, like, math awareness. So now I'm going to solve for dr dt, remember, which I still kept as its own variable. So now, remember, the original dv dt is 9. So you see, remember, I've been just working on the right side here, and then on the left side, volume v, the derivative is just dv dt. There's nothing else going on the left. Volume, derivative is dv dt, which I will make its own variable, rather than the fraction looking, just the letters dv dt is 9. So I'm going to take that as this is something I would have known. Now I have that value 9, and see what I'm doing here, then set this equation, plug in on one side, which we created here, that's this, and then dv dt on the other side. That's what I'm setting equal to each other as my equation here, and then I'm going to solve that equation for dr dt. So there we go. So this is really the use of related rates. I want to, take the derivative, plug in for the things that I do know, and then for what's left, I want to set up that equation and solve it. And that's what I get here. That if this is the volume, then, if this is dv dt, then the rate is just this tiny amount. Also here, when I plug in this r value, that's the rate, the change of dr dt at that point. So there's two things. I can change the dv dt, or I could also change this r value. Supposing I just make the r value 1. And so I have that. So if I plugged in 1, I still have my derivative here. Supposing that's 1. Oh, now it's just 4 pi. And then let's say dv dt is still the same. I can plug that in, and you see it's a little bit more. And maybe I can plug in, if the r value is even higher, I'm even just going up to 4. We'll notice that that's going to make a difference. 64, there we go. And even smaller than it was before. Because if my volume is changing, as that radius gets bigger, then it takes more volume to increase that radius. So we would expect the volume change to be, that dr dt to be smaller and smaller. So, that's really, really what we want to be able to set this up, that, what that expression is, and be able to break it down. What do I expect to be this, derivative, in this case, dr, I made it, and then dr dt. So we can set this up and then do the substitution. And then now, this substitution here, I can, in this step here, I can plug in for different r values. This is probably something for this example, like, inflating a balloon, let's say. That's probably, the dv dt is probably something I would know. So, there we go. If for some reason I knew everything else and wanted to solve for dv dt, then that I wouldn't know. So I would have to, do another step of algebra and set up a slightly different equation. But this is usually, for this one, this is usually what we want to know. So these are some of the things that we can set up in our related rates problems. So hopefully it all comes together and you see how you can break it down using some of your math intuition, as well as making use of the Python code to solve for these unknown values.
So the mean value theorem states that if I calculate the slope, which would be the average slope if I did, from like any 2 points on this line, that somewhere in between there, the actual slope will be that same average slope. There we go. So the mean value, because the average slope, the mean. So that's it. Why this comes in calculus is because we're going to use calculus to prove it. But that's what it is. And if we take a look at this, so the idea is if I'll take these 2 points, whatever they are, I'm not even going to worry about putting numbers to them right now. But if I calculated that slope, then, I could draw the line and maybe I can match that up with somewhere along there. That's one way to look at it. But the idea is it has to get from here to here. So it has to get to that slope. But of all the ups and downs, and it could be even more complicated than this, the slope, somewhere in between, at least one place, will equal that average slope. And there we go. That's the mean value theorem. What we're going to look at is, we're going to look at in code how to use calculus to prove this. We'll find that average slope, then we'll take the derivative and match it up. Do I find a point where that derivative, the value of that derivative, or the slope at any given point equals that average slope? And we're going to see that yes, it works out every time. So pretty cool. This might come in handy sometimes, filling in the gaps of some other problem we're trying to figure out. But there we go. That calculating the average slope, the exact slope will equal that at least one point in that interval. So let's take a look at how to do this and how to prove this with code.
Here's a good way to test the mean value theorem using code. Remember, it's at least one point on the curve will have a slope equal to the average slope. So I'm going to set up my normal inputs. I'm going to pick our classic example here, x squared, because the slope changes. So any x values I pick, x1, y1, x2, y2, then you see whatever x value, and then I'm just going to automatically plug that in. Any points I pick, I can then calculate the slope. Old school algebra there. Now, that's the slope, the average slope, however the curve changes. So we're saying that the slope will exactly equal that at least once. So now that I have that slope from the 2 points, any 2 points I pick, what I'm going to do, I'm going to take the derivative. So first of all, I'm going to take that derivative equation and solve it. Now notice the extra EQ here, because I'm going to take this and set the derivative equal to the slope, and then that's my equation. That derivative equal to the slope, and then solve, so then I'm going to solve for x at that point. That's my test, which is actually going to be my test x value. And then the slope, I'm going to take that derivative and substitute that. So test, it could come up with multiple answers, so I definitely want the first one. And I'm going to substitute that in for x. So there we go. So now I have, at that x value, then the slope equals this. And there we go. I actually could just put it, since I'm doing this test 0, but it actually works this way. So I'll still put the test 0, but that's either way, for this one, it actually works. So any equation, and then I can run it, and at x equals 1/2, the slopes are the same. So there we go. And we can go through, a long way and plan it out. And what I can do is any other x value, let's say I just have there we go. We'll just take this for whatever it gives us, and 0, but maybe I'll make this, 5. Any equation I can come up with, then automatically calculate the slope at any of these 2 points, take the derivative, compare the slopes, and this is the x value. What if I try this? Capital N, because that'll give it a nice numeric answer, and I'll do the same thing over here. There we go. So this actually should work to be the exact same. Let's just give it a numeric answer. You see, at this exact value, the slopes are the same. So you see, this is just a way to test this. And the mean value theorem, it is really interesting because sometimes you might need to use that assumption to solve something else. So there we go. And you can try this with any examples, and it should come up to be, again, continually proving the mean value theorem. But then we'll look at Rolle's theorem as a specific example of this mean value theorem.
Rolle's theorem is a specific subset of the mean value theorem. And Rolle's theorem says that if I have 2 points, that that have the same y value. So the slope between these 2 points is 0. And let's pretend that my drawing is good enough that that's exactly it. So if the slope between these 2 points is 0, then the graph would hit 0. The slope of the graph would be 0 at least one point in between. It could be an actual straight line and it's 0 the whole time, or it could be that it turns around. And that one is probably easier to even think about even without calculus, that, if you get back to the same y value, then if you went down, you have to come up, or if you went up, you had to go down, and then therefore somewhere in there, in that turnaround, the slope's got to be 0. But that's what it is. It's a specific version of the mean value theorem. If the slope is 0 between these 2 points, then somewhere in between, the exact slope of that line must be 0. Even if I have a line that curves up and down a lot more, but that's it. And that's Rolle's theorem. So unique enough that, you got a theorem named after him. Definitely when you get a theorem named after you, you've arrived in life. But nonetheless, so let's take a look at this and just an example of this in code and how to prove this and find this when writing the Python code. So let's take a look at the code.
Remember, Rolle's theorem is a unique version of the mean value theorem. So instead of saying, what's the slope over this range, we're saying that if Rolle's theorem is if the y values are the same at the beginning and the end of the range, then the slope must be 0 somewhere in there. It doesn't have to be 0 the whole time, like, a flat line. The slope could change, the graph could go up and down, but somewhere, if the y values are the same at the beginning and the end, then the slope must have been 0 somewhere. And that's, a version of the mean value theorems. So we're going to use all this same thing, x squared, and here's what I'm going to do. We know that that's nice and symmetrical, so I'm going to pick 4 as my first x value and then -4 as my other one. The y value should be the same there with that symmetry, so we're just going to print that out just to show for Rolle's theorem that the y values would be the same. And then we're going to continue, we're going to calculate the slope. And then if I have these 2 points, the slope will be 0. And I'll take the derivative, and we're saying, given that derivative, does the slope equal 0 somewhere? And that's what we're going to test. So we see that the y values are the same, and then the slope at x equals 0, that's where it'll happen. Then the slopes are the same. Check. I could even do a modified version of this. Let's shift it. Instead of x, let's do like x minus 3 squared. So to make it symmetrical, maybe if I make the first x value 10. So that'd be 3 plus, because remember this shifts it to the right, so that'd be 3 plus 7, and then 3 minus 7, that'll be -4, we'll keep that. So that's all we're doing, shifting it, and we'll run this again, and we see that for those 2 values, y value is the same, and at x equals 3, right in the middle, the slope would also be 0. So that's it. It's just testing that theorem, showing that, I might need this information for solving something, and that's what we have, Rolle's theorem.
So how can I figure out the area under a curve? Well, Bernard Riemann wasn't the first to ask that question, but he's the one that came up with a really great solution. So what can I do? I have a curve, but maybe I could approximate it with rectangles. And if I drew a bunch of rectangles, I get, reasonably close. An example that's simple enough yet complicated enough to illustrate this. If I put rectangles here, I could figure out the area of each rectangle, and that'd be a good approximation. So first of all, we notice that if I pick this, there's a bunch of gaps here. If I do these rectangles, I'm missing a lot of area. And what would make that a better approximation? If I had more rectangles. So what if I had, twice as many rectangles? So we see, and yes, my rectangles aren't perfectly straight, but that's okay because it illustrates the point also. It's an approximation. And with more rectangles, we see we have fewer gaps, smaller gaps. It's a better approximation. And so if I had more and more rectangles, I could get really close. And this is exactly what's happening with high definition video, or, from whatever the resolution of your computer screen is. It's all just pixels, but I get a better resolution if I have more pixels and they're smaller. You look at an old video game, it's very pixelated because the pixels, there were only so many and they were bigger pixels, and you really see these angles and the boxes. If I get, millions and millions of pixels and they're really tiny, then I get a nice curve. So that's what we really have. Like, if I have more and more rectangles and they're each smaller, I can get a better and better approximation. And this is really what he looked at. And so what's the area of this? Let's just say, however many rectangles I have, I'm going to define the width of each rectangle. So each rectangle, and since this is my x value, the width of each rectangle is going to be some like delta x. What's my change in x? And then the height, given my equation, is going to be my y value every time. So I can cycle through, if I've defined this curve as y equals x squared, I can cycle through, pick my delta x, define that ahead of time, and then go through, and for each of these different x values, same delta x, but given that x value, what's the y value at that point? Calculate the area of that rectangle and add them up. And that's called a Riemann sum, after Bernard Riemann. So what I can do is, I can use this to approximate the area under the curve. And notice I used the left endpoints here. You see, if I pick this x value, that went up to the curve and then I went over. So you see each x value, that went up to the curve and then over. So I called it, I can use my left endpoints here. In which case, if a left endpoint, I might have a value back here that would be 0. And then this value here, I'm not going to count because I'm only, for this rectangle. You see, the height of this last rectangle, that left endpoint, that's the height I'm going to use. There we go. And then that x value and wherever that would go, we're not going to worry about that. So we can approximate with the left endpoints in this case, and because of this curve, that gives us an underestimate. I can approximate them. I can use the right endpoints instead. So if I use the right endpoints, as we see, I could have, this is the height of my rectangle here. You see, so it's that 0 that I'm skipping, but this x value defines the height of the rectangle going over. And in that case, if I go up to 3, then that's going to define the height of the rectangle. And we see if I use the right endpoints, then my rectangles go over the line and I have all this extra area. So I could do that way. That's another way, and I would have an overestimate. And as you can imagine, I could probably do the left endpoints and I could do the right endpoints and get some average, and that would probably be a really close estimate. But that's the idea, that these approximations, and they become Riemann sums after Bernard Riemann, these approximations give us a way to estimate the area. And what we're going to look at is, in the code, then, if I were to do this by hand, a better approximation would be a whole lot of rectangles. So that would take a long time, but we're going to look at, if I have this function and once I define my x value, I can set up a loop to, however, what am I going to define as my dx, delta x, my width, and that's the width of the rectangle. And therefore, how many, what's my range? What's my width of the rectangle? How many rectangles? And I can loop through this and add them up. And that gives us a way to do a lot of rectangles and get a better and better approximation. And then we're going to connect this with calculus and see how we can get like the exact answer. So let's take a look at how we can use these Riemann sums approximating the area with rectangles to get better and better approximations, and we'll then connect this with calculus. So let's take a look at how to do all this in the code.
Here, when we write the code, it's going to be a lot better. We can set any number of rectangles we want. We can set dx to be as tiny as we want, and we don't have to, think about, oh, I have to draw this or I have to do these tedious calculations. We can really see this. And I just put in the comments here, we're using this example here, y equals x squared from x equals 0 to x equals 3. So let's just set this dx to 0.1. And, I'll set my starting x 0, ending x 3. And so I'll even just put this here that we can set this, because then I can determine how many rectangles do I want. End x minus start x, what's that range divided by dx. And I need this to be an integer, so I'm going to do all that and then cast it as an integer, because then I want to know the number of rectangles. And I can't have half a rectangle. That doesn't work. So now my sum, that I'll take that variable, set it equal to 0, because now what we're doing, we're looping through that for a in range rectangles. So what's my x value here? I'm going to loop through these x values. So my starting x plus whatever that dx is times a. And remember the range, if I don't give it another argument, it's going to start at 0, and then it will not do the last number. So if there are 30 rectangles, it'll start at 0, and a will be 29, and then it'll stop. And there's my x value. And then my y values take that, x squared. So now I have that y value, and then the area is, for each rectangle, that y value times dx. So once I get that area, then I'm going to get my cumulative sum here, sum plus that area, because that's what we want. We want to get the, we're going through this, how many rectangles, and, given dx here, so all those x values, plug it in to get y, so dx doesn't change, but that y value changes based on this. So this is where I'd put my equation right here in the loop, and I have, the area of each rectangle, add it all up. So if I do this, there we go, 8.555. All right, not bad. But what happens if I make each rectangle even smaller? Look at this, dx is 0.01. All the rest of this can stay the same. And look at this, I get 8.955 because I have less empty space. Now, remember, this is going to be the left endpoints, because my range will start at 0. My range here was as x goes from 0 to 3, my range here will start at 0, and then I'll go through this here. But what if I wanted to do my right endpoints? I don't want to start at 0, but I do want that 30th. So my range here, I can change that from 0, or not 0, because that would be the default, from 1 to the number of rectangles plus 1. So that way, if I didn't have this, it would by default start at 0. If there were 30 rectangles, then it would do, up to 29 and then stop. Here, 100th, so there's going to be 300 rectangles, and it'll go from 1 to, it won't do 0, but it'll rectangle number 1, and it will do rectangle 300. And if I do this, look at that, it becomes, if I go to my right endpoints, because then my rectangles go a little bit over the graph for this y equals x squared. So, we see this. So we have the left endpoint, which will end up being an underestimate, the right endpoint, which makes an overestimate. But either way, I can just change dx here. In this case, I'm keeping the same x squared, but I can, change all these, and I can go to my left endpoints and my right endpoints and, see these estimates. I could probably get really close. Like, let's say if I get 0, 0, 1, everything else stays the same. Now my dx is really tiny. Look at this. So I get, from my right endpoints, 9.0045, and that should be an overestimate. Now, if I go back to doing the left endpoints, there we go, 8.9955. And we see, we can imagine here that the true area might be exactly 9. Kind of nice how it works out. But then we see the overestimate and the underestimate. And that's the whole thing with the Riemann sums. It really is the origin of integral calculus, but also, sometimes you might have a situation where you want to do these. Definitely, if we're talking about actual pixels or something, or things where I have to cut things that are not on a curve, this might be some way that I have to do this. But certainly we can see how this builds up to calculus getting these number of rectangles getting to be more, and dx being tinier and tinier, so I get more and more rectangles, and we should see these values approach a certain number here. So let's take a look at how this leads into that exact number and doing the calculus.
Now that we see that we can get the area under the curve with all these rectangles, let's look at the math notation for this and see how it connects to calculus. So this is the true Riemann sum. I just drew one rectangle here, but for any of these rectangles, I'm going to define that delta x as that same constant width each time. So the width of the rectangle is delta x, and then the height is y. And so, that's the area of one rectangle, y times delta x. And then I want, however many rectangles in, wherever I define my my range here, we were saying 1 to 3, but wherever I define it, I can, for that range, given that delta x, how many rectangles do I have? So the notation for that, we can go through these iterations. Mathematical iterations existed before we were writing code and doing loops. But the mathematical iteration, maybe I'll say, for each sub n, and that's why I put the parentheses there so that distinguishes it. So this is like the first rectangle. So what I'm going to do is I'm going to bring in sigma for summation, and our summation notation is saying add up each rectangle. So I probably don't need the n there because that's the same, but anyway, for each rectangle, I'm going to add up, calculate the area, and then add them up as we go through, as n goes from 1 to, if I make this a huge number, the greater the number, the better it gets. So let's say as n goes from 1 to infinity. So there we go. Great. Infinite number of rectangles, because now, beyond what I can draw, if I have an infinite number of rectangles, that's going to really approximate it pretty well. And, as we see with the code, we could, make thousands of rectangles. That's like an even huge number, but it's a manageable number. It's a finite number, and we can get, a pretty good approximation. But if I say this is, the number, as the number of rectangles goes from 1 to infinity and sum them up, that really should be the exact area. And that's the Riemann sum there, taking this to this, infinite number of rectangles. So connecting that with calculus, this summation evolved into this symbol here. And the idea was that it was an elongated S for summation, but also it very much looks like the holes in the side of a violin. They appreciated that look, but that's the notation that evolved, this integral symbol. And so what we'll say is the integral of, and in this case, I'll make it specific for this one, of x squared, and then the delta x, the notation for that evolved to dx, d for delta. And in this case, as my definite integral, like let's say, as our example, let's say we went from 0 to 3. This is all not drawn to scale. I'd put them here as x goes from 0 to 3. So this becomes the notation here for the integral. So this is the area under the curve, x squared, as x goes from 0 to 3. And that really is that infinite number of rectangles to approximate it. So let's take a look at, in the code, how we can get our definite integrals. And we can write this with a line of code that will say, okay, now once I've defined my function, let's take the integral from here to here, and what's the exact area? And we'll look at that. We'll actually even compare that to the Riemann sums. So let's take a look at how to do this in the code.
Now that we have that notion of area under the curve, kind of that rectangle method and the number of rectangles approaching infinity, that's great. How do we solve that? Sympy comes in handy again. Sympy.integrate that equation. And, import, and I have all these symbols, x, y, and c. We'll talk about c later. I just want to show you this. So you see, if my equation x squared, then the integral is x to the third power over 3. And every equation is going to have an integral function associated with it. And we'll look at how to recognize these patterns and everything in a little bit. So rather than, trying to approximate it with the rectangles like we were doing earlier, I can take this integral, get that equation, and my definite integral I'm going to substitute. So notice I have this, and I still wanted to just display this integral. But now I'm going to go through, my lower value is 0, upper is 3. Just, we'll continue with that same example because I'll call this variable integral definite. And what am I doing here? Sympy.integrate. So you see, if I do this, it will give me the equation. If I do this with other arguments in here, integrate that equation, and then plugging in for x, my lower bound and my upper bound. So it's the area under the curve as x goes from here to here. And you see, it does turn out to be exactly 9. So our estimates up here, 8.99 or 9.05 or, they were dancing around it. But then we get the definite integral here. So we see now we get that area under the curve from one place to another. So we can just change this to any different values here. I can have my equation, anything. I can do, sympy dot sine of x. And I don't need to also display it. So if I just do that, yep, the integral of sine is negative cosine. And I can have a definite integral, that sine of x from 0 to, who knows, yeah, we can just keep 0 to 3. It has that curve, that'll be, something. And, what's the area? It's actually, you see, it wants to give it that exact answer. 1 minus the cosine of 3 is exactly the answer. So we can have any value here. Sympy dot, log. And remember log, and sympy is the natural log. And the integral. So some of these integrals you might actually commit to memory, and some of them you might say, you know what, I just want to see what this ends up being. And applying that as a definite integral, we can just say, 0 to 3, and sympy gives us this exact answer. So we can have this sympy take the integral, what's that equation look like, and then plug in those values, from where to where, like, because I want that area under the curve as x goes from here to here. And this is really then the exact way to get the integral from, getting that equation, which is the integral equation, and then plugging in these values. If I was doing this not on the calculator, what it would do is I would get that integral and I would plug in the upper value. So it would be 3 here, 3 times the log of 3 minus 3, and get that value, and then I'd plug in 0 and subtract it. 0 times the log of 0 minus 0. So it would be that other answer minus 0, and that's what I would have. 3 log of 3 minus 3, because then the other one would be minus 0. This is where we're going to really get into calculating the area under all sorts of curves.
Now this brings us to the fundamental theorem of calculus. We've been talking about integrals, we've been talking about derivatives, and you might think, how can the area under the curve be related to the slope? Integrals and derivatives. So let's take a look at this. When we were talking about the slope from 2 points, what do we have? From here to here, we have dy, and then over we have dx. D for delta, change. So the slope is dy over dx. Then we were talking about the area under the curve, and that width is dx. And since it goes from 0 up to there, it's not just y, it's dy, because the difference from that to 0. So then we have dy here. And then so what do I have for any individual rectangle? I have the area equals dy times dx. And we see from dividing to multiplying, 2 sides of the same coin. I multiply, I divide, I go from slope to area, and then I see the connection of integrals and derivatives as being 2 sides of the same process. And in fact, so we had Newton came up with derivatives many years before Riemann came up with integrals, and it was somebody else after that that saw that, hey, these are 2 sides of the same process. It really takes a lot of different perspectives to put it all together, and that's what we want. We want different perspectives, and everybody sees something and contributes something. So we see that this fundamental theorem of calculus is that these are connected as opposite processes. So when I look at the integral and I look at the derivative, I can take from whatever function I have, take the derivative, and then from that new function, I can take the integral back to the original. And that's what we have. I can take the derivative of something, and then the integral of that goes back to the original. Really interesting, and it connects it all. So that sometimes maybe I'm looking at applications with derivatives, but I have some missing piece of the puzzle. I can do the integral to find something. Or I'm doing integrals, I can do the derivative to find something. And then when we get into all of our, we looked at the derivative formulas, when we look at integral formulas, we'll see the ones that match up. And, oh, the integral of this matches up with the derivative of something else. So let's take a look at just some examples of this in the code and how we can demonstrate this and, take the derivative and then take the integral and see how it gets back to the same thing. So that's the fundamental theorem of calculus, that connection between integrals and derivatives as 2 sides of the same process, like multiplying and dividing. So let's take a look at this in the code, and we'll tinker with some things and see how we can make these connections.
We're really just going to go through a few examples here and just show you how this, you could take the derivative, you can take the integral, and they get you back to the same thing. So the first thing is, notice I'm throwing in another variable there, c. And I'm just going to just show the equation there, x squared. And notice we didn't use C yet. And C is going to come in this next step where we do the integral, because remember, now thinking about how this is the derivative in reverse, you do the integral here, but then there could have been another constant that when you do the derivative would have dropped out. So when I start with this and I do the integral, then it's really x to the third plus over 3 plus c. And Sympy puts the plus c in the beginning. I usually put it at the end. That also, in your notation, remember the plus c, and also then that reminds you, hey, that's the result I just did an integral. So now that is a variable, and what I'm going to do is I'm just going to substitute any c value, as long as I have a number here, because if I take the integral, so what I'm doing here is, so if I just take this integral and substitute c, and then I'm going to take the derivative of that, and it gets us back to x squared. So we see x squared, I did the integral, and then I did the derivative of that, and it got me back to x squared. And so notice we can just go back and forth here. So I'm going to take this derivative, and I'm going to take the integral of that plus c, and it's going to get me back to x squared plus c. And notice I did this all in, just changing this equation here. So I could do like sympy.sine. There we go. And we can do their sine. And if I do the integral, then it becomes the integral of sine is negative cosine. And so, again, we put the c first. But then plug in any c value, and I do the derivative again, gets me back to sine. And I do the integral again, it gets me back to... So just the idea that we can go back and forth, that's really what this is just showing you, that, you can always do the integral, then the derivative. That's really at the two sides of the same coin. And thinking about that, I do need to put the plus c when I do the integral, because that's part of the answer. But I could get to, knowing some initial conditions, get to an exact value for that c. So that does exist. It could be 0, but it's not always 0. So we have to put that and account for that c that will drop out if I did the derivative, but we need to include that. So there you go. Fundamental theorem of calculus. Integrals and derivatives being two sides of the same process.
Let's say I wanted to do the integral, get the area under the curve for a graph that goes above and below the x-axis. Well, we need to see and think about what our applications are, because the area above the x-axis will be positive, but then the area below the x-axis will be negative. And remember that dy was the same as the y value because it's the change from 0. So then if it goes down below, then the change is negative. So sometimes I do want that. Maybe if I want displacement, if I have a velocity graph, let's say, the area under the curve is total distance, the integral of velocity. So maybe I want that distance from a point. So, positive distance in one direction, but then negative distance in the other direction. Does it get back to where it started? Maybe that's the answer that I want. But maybe I do want just the total area under the curve. So in that case, I need to find a way, I need to get this area and then get this area and then add them. But I need to identify where these zeros are so I can take the area from here to here and then the area from here to here and do absolute value. I can do absolute value there too, that won't change it. But I do need to do it here, get that absolute value, and add them together. Because this one, as an example, like a sine wave. So if I did the area under this, if this was y equals the sine of x, from 0 to 2 pi, the answer is going to be 0. Because this area as positive will completely cancel out that negative area. And maybe that's what I want. But if I don't, then I have to identify where are these zeros, and then integral from here to here, integral from here to here, absolute value. And then add those up. And so we'll look at this in the code, how I can find a nice way to identify the zeros and then use those answers to set up my integral from different ranges and then add that all up together. So, sometimes this could potentially be a laborious process, but we're going to see how we can set up code to do that. And for applying this to other situations where I have graphs going below the x-axis, I can just change a couple things and then use the same code. So let's take a look at how we can do this in the code, identifying these zeros and then getting the area to make it a positive area even if the graph goes above and below the x-axis.
So with the code, finding the area above and below the x-axis becomes straightforward because you can set this all up ahead of time for a lot of different situations. Now, first we do want to plot it. So I'm going to go through all these imports here in this code block. And yes, I'm going to include C if I need it. So I just keep these standard imports and I want to graph it. So I'm just going to pick this one, sine of x, because that gives us area above and below. And let's plot this. And so we see the plot. I could, if I wanted to, limit the x value here and just like focus on one part, but I'm going to keep all this. That's fine. And we see the zeros, 0, 0. And even though it doesn't show it exactly here, we know that that's going to be pi. And then over here, it's going to be 2 pi. So, that's one complete cycle. And since it has that symmetry to it, then if I did the area, just a normal integral from 0 to 2 pi, the area would be 0 because all this positive area would cancel out the negative area. Because remember, all the integral gets the area from wherever this curve is down to the x-axis, and then it'd be negative below the x-axis. So these would exactly cancel and the area would be 0. Maybe there's situations where I want to see that overall displacement and cancel that out if necessary, but not here. So we plot it, we get the view of this, because then I'm going to follow this up with finding the zeros. And it really is just sympy.solve. If I don't put anything else, it will default make that equal to 0. And we see it gives me the 0, 0, and then pi. But if I really want this whole thing, there's my 0, there's pi, but I actually want 2 pi also. And looking at this graph and knowing that, then that helps me in the next step, because really all of this, we want to use the code to help us, but it's not going to just be like blindly doing anything, doing whatever we want, and I don't have to think about it. We want to make sure that it does what I want it to do and includes all the values. So I have this 0 pi, but I want it to go to 2 pi also. So I'm going to get the area with the zeros. I'm going to identify my lower value as 0 and my upper value as 2 pi. Now, just because I know that that's the lower and upper, my overall range. But remember, if that first 0 was 0, I'm just going to keep this in here and notice that doesn't, that's going to 0 out. And I kept that here in the print statement at the end, but that will be just 0. I'll do sympy.integrate, and then that equation as x goes from lower to my first 0. And so it really goes from 0 to 0. There's no area. That variable 1, that's going to be 0. And then my next one, see, I just want to identify these. I call the variables 1, 2, and 3 for my 3 different parts of this. And then I made this the absolute value. That way you don't have to overthink if which part is above, which part's below, and then make the other one negative. I just made an absolute value for all of them. And that way that works. It doesn't have to, you don't have to change this for different ways that other graphs might curve, whatever equations you use. So the next one, integrate that equal 0 from the first 0 to the second one. So I'm going to get that area. And then the third one, I'm going to do from that 0 is 1 all the way to the upper, which I identified here. So that way we really see that, this one has that extra one that's, nothing, but then I have that first area and then the second area. I did absolute value on both. So if I were to graph, let's say, instead of sine of x, maybe the negative sine of x, which would flip it, I could keep the same code here. and I don't have to change it which one's above, which one's below. So now I have these, and really I have the total area, and then is 1 plus 2 plus 3, and I just wanted to print this out. So really, that's kind of the advantage of what you want to do with Colab. You want to see the code so you can double check it. You want to see the inputs of the different parts. We're really making use of this for all, math knowledge for all the different in-between steps. So we get the area is 4 because that first one I did was 0, then 2, and then 2. And you see if I didn't do the absolute value, that'd be -2, and then that would cancel out. So there we go. This is all set up then for whatever other equation I want to do. I want to plot it. I want to find the zeros. And then I can identify, upper and lower and take it from here. This could be all set for most any other thing. Like I said, I have this set up for 2 zeros within the range. So I can have my lower, my upper, and even if, I had other zeros in there, that still works for this. This code still works. And there we go.
So if I want the area between curves, I can, remember every area it goes from that curve down to the x-axis. So I can just use subtraction. I can identify this top curve, and then the integral gets me that area, and then the integral of the bottom curve gets me that area, and then I can subtract them. So one of the things I want to do is identify which curve is the top curve, and then I also want to identify, a lot of times we want to go, just the area between, where do they cross? So I want to identify these 2 points, and then I can set up my integral. And so these are some of the things that, I might use on a calculator, I might graph something, and we're going to look at in the code just how to do this, how to get to this point, set up these two, identify the points where these 2 curves intersect, use those as the bounds, and then do the integral of the first curve from here to here minus the integral of this bottom curve from here to here, and then I get the area in between. So that's what we'll look at, and we'll look at how to set up code to use this for whatever curves may come up. How to identify these 2 points of intersection, and then calculate the area between the curves. So let's take a look at the code.
We're really just going to add another step here to the other code, finding area. Imports. I'm also going to import EQ here, and we'll see later on why that might help. Now I have 2 equations that I want to graph. I'm just going to pick this as an example here. Y equals x squared and y equals x. So remember, the understood would be that each of these would be equal to y. And so if I plot these together, then it looks like this. Now, this is the default Sympy plot. Fine, it helps. But actually, I am really looking at this tiny area here that you can't even see because of this plot. So one of the things you can do is when you plot this, you can limit or show a range for x values or y values. So if I put in here one more argument, so after I'm plotting these 2, comma, and then in parentheses here, I'm putting in my x value, comma, and it goes from -0.5 to +1.5. So I'm going to give that x value limit here. And you see what it does. Then it gives my graph from -0.5 up to 1.5 much more zoom, and then I can really see this little area that I'm talking about here. So my default, I would go to sympy.plot and just plot these 2, but just remember that you can do this. You can limit this, and that's kind of how you would do the zoom, and that works out nicely. There we go. Now I want the area between these 2 curves, and I'm going to see that y equals x is the top curve and x squared is the bottom curve, because from 0 to 1 it does curve around, and then after that x squared is greater, and it keeps getting greater. So I want to see these, and I want to see that it goes from 0 to 1, but let's say I didn't see this exactly from 0 to 1. Where do these cross? That's these points where these 2 lines intersect, I can find the intersection points. So you see my x points, I'm going to solve, set these equal to each other. What x values make that true? Now, this is interesting because I see that there are 2 points, 0, 0, and that's pretty easy to see, and then this confirms it. The x value would be 0, but what's this other x value? I happen to know that it's 1, and it kind of, you can see it looks like it lines up there, but it didn't show up here, so how do I know? This is another interesting trick. So this works usually, it'll give you answers, solve, just set these equal to each other, or if I just had one of them, it default sets it equal to 0. But within this, and you don't need to make this another separate step, this is where I can put EQ, and I'm going to put another parentheses here. So what I'm doing here is that I'm taking these 2 things, but then the Sympy function EQ, making that an equation, which should it, it would have done anyway, and thus solved and gotten that answer. But this works sometimes to give me both answers. And for, some like behind the scenes reasons, when I solve it, I know that there's 2 answers. It only gave me 1, but if I throw in this other step here, it works, and it gives me these 2 answers. So there we go. So that's that other layer of officially making it an equation with EQ. So now I have these 2 points. That's the x values where they intersect. So remember that we get the area under the curve down to the x-axis. So to get this area between, I can get the area under y equals x minus the area under x squared, and then the difference is that area in between. So that's what I want to do. I want to get, the integral of 1, the integral of the, top, bottom, and then subtract them. Now, it happens to be that I called equation 1 x squared and 2 x. So actually, equation 2 is my top equation. But I want to show you that even if you wanted to do it, whichever way, this works, because when I do this integral, Sympy to integrate equation 1 from, as x goes from this to this, lower to upper, and you see I'll define, because I want to use these for both, my lower bound is my first 0, x point 0, and my upper bound is my next one, x points 1. So that's going from lower to upper. And I have it written this way. That way, if I'm doing something else, we want code that we can use for a couple things. If I'm doing something else and I want to just put in a lower and upper limit, maybe it's not related to the zeros, I can do that. So there we go, my lower bound, my upper bound. And then the other one, I'm going to do the same thing. Integrate equation 2 from the lower bound to the upper bound. And then what I'm going to do, that's top and bottom, and I'm going to subtract them. Now, I happen to look at the graph, and I know that the way I have it written here, I have equation 1 and equation 2. But really, the top equation should be equation 2. I absolutely could just change this. And I could make this equation 2 and switch this one to equation 1. But whether I do that or not, that won't matter, because when that will still give me the correct number. It's just that the area might be positive or negative, depending. Now that I know that this is the case, I could just eliminate this, and I could just do this here, because now I know that it's going to give me a positive area. There we go, 1/6. I could have just kept that as I did here, the absolute value, and then supposing I get it wrong, or whichever one I define, then it won't matter, because I'll just do that subtraction, and it may be negative, but I'm just doing the absolute value anyway. So you see, it works out either way. And that's kind of, you want to build these in here for ways that you can look, I can always look back and change this, or I can use absolute value, but either way, then I get that, subtracting those 2 areas, and the difference is 1/6. So then that's the area between the 2 curves.
what happens if I want to get the volume of a three-dimensional shape that I revolve around? So let's say I have our y equals x squared, nice curve to it. But supposing I wanted to revolve this around, and we'll see why I have this random shape here in a second. Supposing I wanted to take this and revolve this around the x-axis here, so that I make this like, 3D shape, maybe like a pointed hat on its side or something like that. As an example, supposing I wanted to make this 3D shape, but then get the volume of it. How can I get the volume of this weird shape? Now, definitely we can be like Archimedes and put it in a tub of water and see the volume change. But mathematically, if I'm looking at this, if I have this, if I have a shape where I do have an equation that gives me the bound of the edge of that, so when I want to revolve this around, what can I do? Now let's think about the rectangles when we got the area under the curve. And if I wanted to do this, supposing I slice this here, I'm not going to draw all the slices, but supposing I slice this, so instead of rectangles, I have slices that are really thin cylinders. So that's why I drew the cylinder there. If I have a really thin cylinder, each of these slices here, and what we see is then if I slice this way, just like we have the rectangles, if I have more slices, they're each thinner. So I will define, whatever my slice is, I'll define, that common dx. And never mind that my bad drawing doesn't have a common dx. And certainly our slices would be thin beyond what any of us could draw. But we'll get to that. So then, that's the height here. There's my dx. And it's that constant height of the cylinder. So what's the volume of each of these cylinders? So the volume is pi r squared height. That's the volume of any cylinder. So if I have my common dx as that height, these cylinders on the side, what about the radius here? So that radius there, if I'm revolving this around, then my radius is always going to be my y value. And so what I have here is the sum of pi times my y value
squared
times dx. Or I could call it delta x, but I think we've gotten to the point now that we're looking at this as dx, d for delta. So if I revolve this around, and then, this is it, and the sum of each of these
cylinders.
So remember, we can just give them, like I for iteration or something, and then as I goes from 1 to infinity. So I'm summing up this infinite number of
cylinders
as I goes from 1 to infinity. And remember then, now, we've done this, we could see that, yes, this summation of these infinite number of
cylinders
is the integral of my y value times dx. And in this case, my y value is going to be x squared. So if I call this, x squared dx, and let's just say, I start from like 0, let's just say I decide to cap it off at 3 here, then it'd be, from 0 to 3. There's my definite integral. So we see how just picturing this, slicing this, the same way we were, we get that calculus logic of, yes, I can break this down, but can I, these slices, a few slices, it might be crude, might be choppy, then I get more and more infinite slices. Then we start talking calculus, each of these, we can get a handle on it. Oh, it's a very thin cylinder. So then that would be the volume of each cylinder, and then I add them up, which then infinite number becomes calculus. So sometimes these can get really, if I were doing this by hand, really intense factoring and some more complicated things. But we'll look at how to set this up in the code that since it's this, if I just set this up that I can define what is that radius, in this case my y value, and what's my range, lower bound to upper bound, and work this out and calculate it. We'll also, in the code, I'm also going to introduce a little bit of 3D graphing. Python can generate this shape, and you can really get a sense in 3 dimensions, hey, what would this look like? And we can use that, for other more complicated graphs. So let's take a look at this. So we get the logic of this, equation to define the edge of the curve, because then that y value becomes my radius. So then summing, make these cylinders, sum them up, and we'll look at the code. We'll look at how we can just show this, what this would look like in 3 dimensions, and then set it up that all we have to do is change the equation and the upper and lower bounds, and we can get the volume here. So let's take a look at how to do this in the code.
Before we even get into the calculus, let's talk about how to visualize this in 3 dimensions. And I'm going to show you how to set this up that we can use this for any other 3D, function revolved around an axis, and all the rest of this can stay stable and we can just change the function. So we're going to import NumPy as NP, import matplotlib as PLT, things we were using more in the algebra stuff, sometimes in the pre-calc stuff. And here we've been doing a lot of Sympy plots, but this can do more, including the 3D. I like the way that this works for 3D, so that's why we're going to use this library. Then I'm going to import these toolkits so that I can see the stuff in 3D. I'm going to set my range here for x, lower bound, upper bound, and then that way I can use these variables and I don't have to change this everywhere. And all this stuff we're going to keep the same here. All this to set up the graph. I'm only going to plot 1 and I'm going to put it in row 1, column 1. So there we go. But then here we throw in this projection 3D. I have my points, that difference, whatever I pick as my lower bound, lower minus upper, upper minus lower, times 10. That should give me enough XYZ coordinate points to plot. So this should work out nicely. So, here's the, define it once. Here's the points. And then I'm going to set this up U and then V. So lower minus upper points and then V. U is really what we're going to use here. But remember, I'm revolving this around. So this lens space, if you notice the trig in here from 0 to 2 pi and then 60 points, that should be enough to give us a nice smooth curve going around in a circle. I'm going to set this up. Notice the capital letters here for the mesh grid from U and V. And this is where it connects. That capital X equals U. So what I'm going to do here is I'm going to define my function. And this is where you're going to change this. Like this, going forward for other functions. So really this is going to be y equals x squared is my function. So that's going to be U squared. Capital U squared, that's my function. And can't spell function without fun. So then I'm going to have, and I have these as 1, y1, and z1 because I'm building this in. We can build upon this to plot more than one. We'll get to that later, but we can plot more than one. So my function here, and now notice this function is going to be U squared. There's my function. And then in 3D, so then the y value is that function times np.cosine of v. And then the z value is np.sine of v. So remember, with our parametric equations, sine and cosine, as my x and y values, that'll give me a complete circle. So I'm going to take this, and this in 3 dimensions is what plots it going around in a circle, revolving around that axis. So now I have that equation. See, I can define it here and then just use this here so I don't have to ever change these two. And that will plot this going around that axis. And then here, I'm going to say that I'm going to plot the surface. And what am I plotting? I'm plotting my x value, y1, z1. And I'm going to pick this color, blue, and then this alpha 0.04 refers to like how dark or the shading of the blue. So I like to keep that in there. If I didn't, it's just a dark blue, and that's okay, but I decided to adjust this here. So this is what we get. So we see we've made it 3D, and going along the x-axis, there we go. You know, we can see the edge of this curve is that y equals x squared, and then it revolves around. This is what this shape would look like in 3 dimensions. Now we can picture this. Here's another, we'll just modify this a little bit here. Supposing instead of just x squared, it was x squared plus 1 revolved around. So we see it doesn't go down to 0, 0. It revolves around like this. And again, we get this like, you know, horn or megaphone, you know, looking shape. But now we can picture what that looks like. You know, this, you know, we imagine this as a solid, and we're looking at getting the volume of that. And I just need to change my lower and upper bounds. What do I want it to be? And I can change what is the function that I want to plot. And with all that, the rest of this will plot. And we can use this to visualize a lot of 3D plots, and that's going to be really helpful. This is what we would add, and actually it ends up not working very well on its own. I do need to include this in the other, but when I graph a second function, but we'll look at this in a little bit. I'm not going to worry about this right now. So now I want to calculate the volume. So for that, I'm going back to Sympy and my symbols, and this is my function here, which I'm just going to call it radius, and it's its own function. So if I had y equals x squared, then, you know, I could actually probably connect it with what was up there already, but I'm not going to worry about that. You know, you can copy it and paste it here or whatever you'd like to do. But there's my function. This is what you would change. And remember, you know, if I'm revolving it around the x-axis, the y value is the function, so this would be y equals x squared. And then remember pi r squared, so sympy.pi times the radius squared. So that's already built in there as the area. So really, that's our function that we're taking the integral. And here I'm just defining the lower bound and upper bound. Sympy.integrate that area, and then as x goes from lower to upper. You could link this all together, use these same lower and upper. The difference would be the radius here. I definitely want to use x, and I'm using those Sympy symbols, and then the other one I'm using u. So that's one way if you wanted to. But anyway, this is the exact area, and it's going to be, you know, this exact number because I'm using Sympy. If I needed a numerical answer, I could then add Sympy.n, the numerical approximation of this. So you see, I could get this as a numerical approximation if I wanted to. And there we go. So anytime we want to revolve something around an axis, we can use this, and then you see, you know, there we go, u squared plus 1. I could, you know, copy or something like that, lower and upper. There we go. I could represent it in 3 dimensions because that's what I want to see. And then I can go down here and calculate the volume. I'm not worried about graphing this because the graph of this, the numerical answer is what I want, but the graph of this doesn't look at all like what I wanted. But notice the graph of this in 2 dimensions, the numerical answer to that over that same range is the volume of that other shape. So there we go. So we can get this, and then we can get the numerical answer if we want. I like to include both because sometimes we want one, sometimes we want the other. And then next we will look at the hollow shape. Like supposing I want something like this, but maybe part of the inside is missing. What's the volume of that? And that's what we'll look at next.
So what happens if I have a more complicated shape that maybe it's like a hollow shape? Like if I have this this would be, let's say, y equals x squared plus 2. Let's say I have that revolved around the x-axis around here. That would be like the bottom part. All right, so I get that, but let's say it's a hollow shape, and in the middle I have maybe something like, y equals 1. Just a cylinder down the middle here. What happens if I want to get the volume of this shape, but not the volume of that cylinder? Because, I want to know, I don't know, maybe I'm making this out of plastic, I want to know how much plastic I need. So, for maybe making like end of a horn or clarinet or something like that. So what do I want to do? Well, if I have this, odd shape, I can do the volume of the outer minus the inner. I can do that. And if I was factoring this, I would set these up as, two integrals, but then if it's, integrals over the same range, I could combine them as one integral and still do the subtraction. But what we're going to do is we're going to look at just in the code how I can just, once I identify the outer and the inner, and again, each of these defined by an equation, then I'll just set this up and do the complete integral of the outer minus the integral of the inner, and what's left is, the volume of that shape. This is a lot of things that you can create in 3D modeling, and then maybe you want to print this out, with your 3D printer. So in doing that model, one of the things you might want to do is say, okay, when I print this out, how much plastic am I going to need? So we want to do this, we want to do the math, we want to see the sketch of this and be able to do the calculations. How much plastic do I need before I even make it? So we're just going to do the volume of the outer minus the inner, and we'll also look again at a 3D model so you can see what that would look like and how to set this up and calculate it.
When we're doing the volume of a hollow shape, which is really going to end up being the volume of some outer shape minus the volume of some inner shape, this is where the non-code calculus, doing all the factoring, could get really involved, but the code's going to help us here. And we have this code that we set up when we were doing the volume of one shape. All the same imports to see what this looks like in 3D. And I'm going to have my range and all these things that we still have to set up the graph. None of that's changing. I can change the range if I want, but I don't need to change any of this. So now I'll define the functions here. And the first one, I'll make this, u squared plus 2. So it's still going to have that curve, but you see we'll have a shift here. And then that'll be the outer function. So let's say we have like some, we can leave this, but let's say we have just even like y equals x. So that's going to be u, capital U, here. And I'll define this as function 2. So all the rest of this is still the same. I just have, fun for my first function, and y1, z1, and then fun2, y2, z2. And remember, each of these, we set it up that u is my variable here for this mesh grid. And then this multiplying by sine and cosine, like parametric equations, gives us that 3D shape revolved around the axis. So if I just have this, or I could even have it as a constant. Let's just say I have this as 1. So let's take a look at this. So I have this u squared plus 2, and this is just 1. It's going to be this constant. So now, when I plot both of these, you see I'm going to plot this surface, x, and then y1. Still that's those same x values. So notice that's the same for both these, y1, z1, and my color is going to be red, alpha equals 0.03. That gives it the level of like how dark it is. I'll do the second one, same x, y2, z2, alpha 0.02, slightly lighter, and then on the color blue, just to show the contrast here. And you see, we have this. The volume, I'm going to get the outer minus the inner, but this is what I see what this looks like. And then we could even have, let's say, supposing I have some like interesting, y equals x. And this one would be, I could have like that inner shape, maybe, hollowed out for some reason, but then comes to a point, all kinds of different things. So this is what it would look like. And I'll just define these. Let's just say these are the outer minus the inner. So I want the volume of this, but I don't want that hollow part. Like, let's say it's like how much wood or foam or plastic or whatever I'm making, how much would it require to make this. So it's that outer shape minus the inner that I'm not going to use. Now we see it, but then calculating the volume, I'm going back to Sympy, import all this, and same lower and upper bounds. So if the outer radius, I'll use this one, so it's going to be u squared plus 2. And remember, that's the radius, so x squared plus 2. And all this I'm just setting up for the outer. Remember, if the y value is the radius, so Sympy.outer radius squared, pi r squared. And then I'm going to take the integral, and that's going to be my outer volume. And I'll do the same thing with the inner volume. Remember, I just made that the actual function was y equals x, or this equals u, so equals x. That's my inner radius, and pi r squared, and then the integral for that one. And notice the outer volume, I want it to be outer area, so that should be what I'm taking the integral of. And then this one is inner area, so then that's the one I'm taking the integral of. So I get outer volume minus inner volume, and then there we go. So I get this, there's my difference, and that's the exact answer. Maybe I want that. But remember, I also could make it Sympy.N. Sympy.N is the numerical approximation. So I like to get both of these. So I want this to calculate the exact volume, and I want to output this. And that needs to be its own. I can't do this in the same block of code because this is the last line. So then it gives it the nice display. And then I can do the inner volume. There we go. Or the actual volume. So I could do this for all kinds of different things. Maybe I had this, plus 2, and maybe I make this, to, I don't know, some sort of like thing that comes to a point. That'd be really thin at the top. But again, let's just say that is the case. Then now I see what that looks like, how things line up. And then I calculate this. There we go. What's that volume? There we go. And then, slightly different than before. So these are the things that we could do. All that's set up to display this complicated volume and then to calculate it. And then we really only have a few things that we need to change. What I want is my upper bound and lower bounds, and what functions I'm using as the outer and inner functions.
Now, what happens if I have a shape that I revolve around the y-axis instead? If it was written as y equals, I just need to rewrite it as x equals. And why am I going to rewrite it as x equals? Because if it's revolved around the y-axis, so if I'm doing this, that's what that would look like. And where's my radius now? So we're still using that same logic of, cylinders here. But notice I'm going to draw the cylinder this way this time because here now is my radius. And so my radius is my x value. So I really would rather write it like this. So my radius is my x value. And then if I'm slicing it this way. So then this is dy here. So the math of it is kind of the same, but the picturing it and what variables we use and where, that's what we really need to just be able to picture. anytime if I'm revolving it, where is that axis? And then what's my radius? So then once I identify the radius, and then perpendicular to that is always like, how am I slicing it? So identify the radius here. In this case, it's the x value, so I want it written like this. Then since I'm slicing it this way, it's dy. So then the volume is going to be pi times, in this case, my x value, y squared, dy. I get that, and then the sum of that, so it just becomes the integral here of pi times y squared, because that's specifically for this, times dy, and maybe my y value still goes from 0 to 3 if I want. Let's say, if I wanted to cut it off here at 3. So, 0 to 3. That would be the setup. So in the code then, when we look at this, it's really going to be the same setup. It's before we get to the code that you want to be able to picture, what you're doing and make sure you set up the correct function for this to get the radius. So that's really it. As with a lot of code, you do, and certainly with math and code, you're doing more of the thinking before you're writing the code, so that when you write the code, you're like, oh, okay, it's like this that I did in a different situation. But then you want to make sure that you're putting it the correct way. So as we look at this in the code, it's actually going to be almost identical to what we're doing when we're revolving it around the x-axis. Really, I'm just going to swap out the variables. So if I'm developing something in some like 3D software with the intent on printing this out, then, hey, if you're doing this, make that center, whichever way you want to do it, like X or Y, whichever works for you, make that the axis your center, and then, define an equation for that. That's just going to help. So let's take a look at how to do this in the code and how similar it is to revolving it around the x-axis, and then just what you need to do differently if you decide to revolve it around this way. So let's take a look at the code.
To help picture revolving this around the y-axis instead of the x-axis, just like we did this code here to revolve something around the x-axis, and you remember this code, x equals u, and we work from here. We're just going to change a few of these things, x, and then you'll see we change y and z here. If I'm revolving it around the x-axis, lower and upper still works as variables for my range, and all of this stays the same, but here's what I'm going to say: z equals u. And I'm going to say z instead of y because of the way this Python graph displays it. I like that output better. So I'm going to say z equals u. I can still define the function the same way, same variable, but here's what I'm going to do. I have x and y as my variables here. So that's the shift. Z and then x and y here, compared to here x and then y and z. The reason why I don't switch it from x to y is, like I said, you'll see it looks nice here and it shows vertically, and that's what this whole part is. This is really just about trying to picture this, because you're doing the math of this, and there we go. So we can picture this now vertically. That's what we want to do. We want to be able to just picture that. But you're doing the math, solving, making it x equals instead of y equals. So this is, just to help you. And we'll come back to the second function. Calculating the volume then, if we look at this, now again, this is just comparing if it was, y equals x squared, we see the radius, x squared, or if I put x squared plus 1, and here, the hollow volume. So if I wanted to calculate the volume, here's what I'm going to change. Then I still define both of these symbols, but I'll just call it, notice the math of this is very similar. Y squared. And once I just define that as a function of y instead, all the rest of it falls into place the way I have this defined, lower, upper, there we go. And it's just here then I'm going to change this variable from x to y. So you see the math of it, and I expect the same answer. The math of this and the code is the same. It's really, you're just changing that variable from x to y. So really the advantage is just picturing it differently. But once you solve it and realize that the radius is my x value, then, we change this here. There we go. And then, oh, now that's my y value. There we go. And, all of this, I don't have to change anything here because I just calculated that, and then there we go. And same with the hollow volume shape. If I look at this, there's my hollow volume, and I left it as this. Maybe I'll just change this to +1 just because, again, this is the hollow volume revolved around the x-axis, and we can picture it that way. So then around the y-axis, so these are the changes that we're going to make. My y range instead of my x range. All this stays the same. I still want that z equals u. Remember, I change it from x to z instead of from x to y. Still define this. And then here, remember, that's going to end up being z. So x and y are these functions here. So for the second one, I'll define this one, and again, x and y. So then we see how we plot the surface x1, y1, z, x2, y2, z. That's really what we want. And then, again, we can picture it vertically. So that outer and then the inner shape. And like before, calculating volume is really going to be the same either way, as long as I just change these. So if I just want my outer radius, I'll make this, instead of x, I'm making this y. I've already defined the symbol, so that's it. And this doesn't change, and then this just becomes y. So really, we're really just switching x and y for this. Picturing that, that's what helps, but the math of it ends up being the same. Inner radius 2, that's it. And so, again, I just change x to y. Outer volume, inner volume, and it should be the same. And again, sympy.n, still the same. So really that we're just changing x to y, but it's all about you being able to picture if it's a function of y, then making it this. And then these are the things that help. Can I picture what that looks like? Just like I wanted to picture the other way. But that's really it. It's just, where is my radius? And then that's what, where's my radius? And then therefore, how am I slicing it? And then what value then am I going through? If in this case, x is my radius, and then the y value is the direction I'm slicing it. So all these work out really nicely to switch it from revolving around the x-axis to revolving around the y-axis, picturing that with Python graph and solving it.
So if I wanted to find the center of mass on, let's start simple. Let's say it's just on one dimension, and I have some, where is the center if I have, a bunch of things on each side, and, maybe I have each of these represents some mass that I have, the mass of this object and then the distance from the center. And I can, calculate these distances times the mass, and, where is that center so that this would all balance out. So we could do that if it was just in one dimension, and that's discrete, not continuous. I just have certain things that I can measure for each one. And then that's the moment of mass. Notice that connects with like the moment of inertia, how like I have to move, I have to move this, if it was the moment of inertia. But the moment of mass is that distance times the mass, and then, I have all these moments and I need to balance them. So if I have this in 2 dimensions, I would be doing something very similar. I would have like all of my, I would calculate all the masses, as it relates to x values, horizontal. And then I would calculate all the masses as it relates to y values, vertical. Again, doing that, multiplying, adding them all up, finding that center. Averaging them out, that type of thing. So all these are nice if it's nice and discrete. Not really. I guess you don't really need calculus. So summation overlap, you could almost call it calculus. But what happens if I have something continuous? So now, not just on 1 dimension, not just on 2 dimensions, but we'll do it with 2 dimensions with a common thickness. So really, it is in 3 dimensions, but we'll say that there's a common thickness. That if I have something here that, if I'm graphing x, y, and for whatever this graph might be, I'm not even going to worry about an equation for this. Then, maybe I'll bound it by like the x-axis, y-axis, and there. Something like that. Let's say I have some shape like this, that I would definitely have an equation to define that. That really makes a difference. That really helps. Because realistically, if I don't have an equation to define it, and if it is a bunch of points, then I am just doing summation, for a lot of different discrete values, and then it goes back to the non-calculus. So let's talk about this. What's the total mass of this? Well, I can get the area, and then that times a common thickness, so that would be the total mass. We'll call it the common density. So the total mass of this is the integral of this, whatever my y value is. Let's say I don't know, I'm not going to worry about like what exact equation this is. The integral of that y value times dx, and then all that times a common density, which I'll just do as a capital D for density. So that's going to be my total mass from A to B, from wherever the range is. So now I have this. This is good. Now, how can I calculate those moments? Let's take a look at each of these. Supposing I have, and now as we think about calculus, just like we were thinking about before the rectangles, like let's say I have some particular rectangle here. There we go. And so adding these up, let's talk about each moment then. So if this rectangle now has this density here, so that would be, the y value times the density times the y value times, dx. So, that would be, like the density of that rectangle. So if I wanted to then get the center there, as it relates to the x-axis, if I have some center, then what's that center is that y value and then half of that. So, that y value and then half. So if I wanted to get this density as related to the x-axis here, what I'm going to do is I'm going to have this moment for x, and it's going to be the density times y squared. Well, because it's y, that's going to be times y over 2. So it ends up being, I'll even write it like this, y times y over 2 dx. So this becomes this moment of, how much mass is, at each of these rectangles. This one in relating to the x-axis here. So if I have, from here to here, so that density times the y value squared, so that would be like that density, this distance from the y-axis. And taking that to calculus, we would have the integral of that density, and you can bring out the d times y squared over 2 dx. And that becomes this moment relating to the x-axis. So we can get that density there. Now, let's talk about it relating to the y-axis. So if I still have that, there's my rectangle still, and then now, if that's the density of this rectangle, but now it's that as the distance from the y-axis. So what is that distance for the y? Well, that's my x value. So then it becomes x times, times the density, I'll just put the d here, times y times dx. So that becomes my value here. And since all this, I'll define this as a function of x, it's going to be then then that my relating to the y-axis is going to be, I'll bring out the d for density, so it's x times y times dx. And again, all of these would be the integral given the entire range, because we're doing this same type of thing with every rectangle. So then that's calculus. We're taking the integral there. And how do I get the overall, let's put this all together here. So how do I get this overall center of mass is that I want, all right, so if that's my, and then remember mx was the integral density times the integral of y squared over 2 dx. So we get that. And then remember the total mass of all of it was just the integral, of y, whatever that y value is defining it, dx. So when I have these, so then the center of mass for the x value, because remember this one, it was related to, we called it my, distance from the y-axis, but that, a lot of times I've seen this in the textbooks. It always seems weird at first, but this is my because it's the moment from the y-axis, but the mean for the x value, and this gives a number, which is the x coordinate of this center of mass, would be that my, as you calculated it, divided by the overall mass. And then the y mean would be, because remember when we did this, it was like the moment from the x-axis. So then that would be mx, as we calculated there, over the total mass. And so this is what we have here. As you see, like, taking it from being these discrete amounts to calculus, this continuous amount with this common thickness, we can look at this and we can get, that moment. So each of these moments, but then that's not enough. I need that as it relates to the overall mass of the whole thing. And so I can figure out, doing this, where is the xy coordinate of that center of mass. And I think that's pretty cool that we're able to do that, so that if it ends up being something discrete, then we're going back to summation and we're doing that. But if it's something and that I can at least get a pretty good approximation with, that I can define by a function, some y value, then use that function, and then I can get the center of mass on some continuous area. Now, given all this, I want you to see how, like, hopefully in looking at this explanation, it makes sense, because now we're going to see just how we can do this with code. Once I just define that y value, what is that function? And then what's the range that from where to where, above the x-axis is this example here. So once I define that, then integral to get, and all these integrals would be within that range from a to b, from a to b. So once I define that function, then I can figure out, there would be that common mass, all these with a common density here. And so what we would do is, if I have this, define this, calculate the mass, write the code to do that, and then you're going to have that mass. Then you already have that y value stored, y squared over 2, take the integral of that, calculate this moment, y times x, and Sympy, you can just incorporate that into another equation, get this moment, and then with all those functions, then we're going to calculate the exact point x, y. So we get that point of where that center of mass is. And like a lot of things we're looking at, you can set this up so that in the future, if you have a function, just having that one function to define it, and then you can boom, 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 all the other steps cascade down and changing that function, changing the range, and you can figure out where is that center of mass for some different things. So let's take a look at how to do this in the code.
Now we're going to translate all those equations into code using Sympy again to find the center of mass, the usual imports, and we're going to have this that I have a common thickness. If this was, something in 3 dimensions, there would be a thickness to this, but as long as it's the same thickness everywhere, then this works. And I'm going to, as x goes from here to here, so I picked this range because this is the equation, and we're looking at this from this down to the x-axis. Where is the center of this? So I'll pick sine of x, and then we go to these formulas that, I want to get the mass. So I made that my variable. I'm going to take the integral of this and, keep using this from lower to upper. So once I get the integral of that, remember that's total area, but then for our purposes here, that would be the total mass of whatever shape I have here. And then I'm going to use this. I want equation 2 here. I made it's separate. I like to split things out here. So that's going to be that original function squared divided by 2. And remember, that's the one I want to use. So then I have that equation 2, so that when I solve for mx, I'm going to integrate this as x goes from here to here. So there we go. So I have equation 2 as a separate, so that way I can just put equation 2 here. I just like doing that a little bit better. Equation 3, and then, that's mx. Equation 3, remember it's x times that first equation, so I'll do that. And now for my, I'm going to take the integral there. So now that I have mx and my, remember to get that x center, my divided by mass. And remember, I kept the conventional notation, this is mx, my, and my divided by the mass is actually the x center, because as x, it's like, distance from the y-axis type of thing. And y center is mx divided by mass. So now I have these two. I'm going to print these out. And Sympy, if it involves pi or something like that, it's going to give me, something like that. So I want that exact answer, but I'm also going to print out the point. And for that, I'm going to do Sympy.n. I want to convert that to a decimal number, however many decimal places. Sympy.n here, and there we go. So I want to see these. I want to see the point as an xy coordinate in decimal form, and then I'm going to plot it, and plot that original from over to upper. And then I'm going to include these markers so that I can plot that point in there. And when we do this, so given that, the x center, y center, and then here's the point, and we see it graphed. There we go. And 0 to pi, and the point in the middle. So there we go. Sometimes it gets weird. Sympy sometimes will plot things where this x-axis, the numbers on the graph are correct and it shows, but the x-axis shows up in the middle of the graph, and that just gets kind of weird. So, I could find, maybe I have that, but maybe, I don't know, if I have like sine of x plus 1, just that little shift. And supposing I still want to do the integral from here to here. So when I have this, you see, it really does, the x-axis goes down here, but it doesn't go all the way down. It's, you can force that in here and do like x lim, y lim. I put this other one, you instead of just x with this upper and lower, you could put in, x lim equals, and then give it a range, y lim equals. But just to show you, sometimes it gets weird. And for the limited aspect here, the graph is there, and the numbers are correct, and this point is correct. It just looks weird. So you can change the dimensions. And you see center of mass, like this is the Sympy answer, but then, I'm going to go like that's the point here. So the x value would be the same, but notice the y value changes because we shifted it. And yeah, so these are some of the things. It will also, if you do this, let's say I make this sine of x, but I go from sympy.pi to, so from there all the way around to 2 pi. So now we have the negative value. So it will still do this and give this value. And you see here, the y-axis now showed up in the middle. Sympy just likes to do that, put the axis somewhere. There's an algorithm for how it feels like some line of symmetry or something. But you see, the x values are here. Like, this is not the y-axis, but Sympy just put it in the middle here as we see this graph go from pi to 2 pi and then down below the x-axis. So there's the x, there's the y, and as decimal numbers, it all looks correct, but the axis, the way it displays it, just gets weird. So remember, these are designed to help, to give you a visualization, but sometimes the output just gets a little weird, but that's okay. Let's do one more here. And supposing my equation isn't trig, supposing it's Sympy dot square root of x. There we go. And I'll make this from 0 to 9. How about that? We'll make it, some nice even. And notice this is all I need to change. What equation do I want? And then here, because all the rest of this is then built in. And I get my Sympy values as well as the point here. And we get a nice visual of where this would be. This one, the axis looks nice. And that's where the center is. And we have the XY coordinate for it. Really good being able to get the center of mass, in 2 dimensions here and Sympy.
Let's talk about the normal curve. And what do we mean by normal? We're looking at really a frequency distribution of, the y value would be, what's the probability of a score being right around here, and the x value would be standard deviations. So little bit of statistics background. If I were to measure, anything, and I get this like range of scores, if I have enough scores, the idea is that we would find some mean score, and most other scores would be around that mean, within one standard deviation. And so, let's start with that theory, that whatever I can measure, that I have, once I find the mean, most of the scores that I measure will be around that mean. Pretty interesting thing to think about. So if I have average height of people, wherever I go, if I really measure like enough people, I'll get some range of heights, and somewhere there I can find, calculate the average height. And especially if I take it to several decimal places, maybe I don't find anybody who actually is that exact average height, right down to so many decimal places. But most people would be within a certain range, and then that would be one standard deviation above or below. Or, whatever I measure. The normal curve theory really kicks in when I have a lot of scores. I mean, millions, ideally. So, that's what we're looking at. That if I measure something that I can calculate the mean, then most of the scores are going to be within one standard deviation. And what's standard deviation? Well, once I have the mean, pick any other score, the difference between that and the mean is deviation. It's really not average deviation because the formula is a little bit different, but a large standard deviation means that there was a lot of differences, and so therefore the scores get more spread out. Very tiny standard deviation means that the scores are all really close to one another. So what this measures then is, if I talk about standard deviations, I'll just say 1, 2, and 3, because the normal curve theory that most scores are right around, 1 or, 1 standard deviation above or below, and then, I could find this range, not drawn to scale. We might see that we might look at this and see, yes, maybe that looks like a snake eating an elephant. Definitely not a hat. Some people call it the bell curve, but really it's all about that frequency distribution that, most scores, and when we say most, in terms of frequency, like it really kind of caps out here at like 0.4 as a frequency. So, I changed the scale of this a little bit because otherwise it gets like really steep. I don't know. It works out nicely just to see it a little bit more spread out. So within one standard deviation, we can say that most scores are there. And this is where the calculus comes in, because if I look at all these scores, like how many of those scores would be within that, we find that if we get the area under the curve here, then we can figure out a percentage that would be here. And actually, that's where the calculus comes in. Once I establish this normal curve, and this is the equation for it, which we'll talk about in a second, but once I establish this normal curve, the area under the curve is exactly 1. So that's what's kind of interesting. The area is exactly 1. And then when I get this area here, it's about 68%. So it'd be like 34 and 34. But then that's what we're saying. Like, given something, if I have enough data points, then I calculate the mean. I expect about 68% are going to be right around the mean. And, we can look at, what percentages are beyond this. So if I'm measuring something beyond one standard deviation, now that's news. Anything within one standard deviation, I'll say, yeah, that I'll lump that in with like that's average. It might be, maybe close, maybe a little bit above average, but I might not even call it significant. Once I get beyond one standard deviation, and in some statistical tests, maybe you talk about around 2 standard deviations, hey, now we're talking about something significant. Hey, this is news. Wow, that's noticeably different. But the calculus of this is all about looking at this, and this happens to be the equation for this. I put it here, but I often see the e exponent written as a negative exponent in the numerator or even beside it. And when we get into the code, we'll look at how if I put this in one way, how Python will then display it, in a slightly different way. And that's fine mathematically, as long as like the factoring works, that yes, this is the same equation. So, this is the equation. And if we notice, then whatever x is, this is never going to be 0. And that's what happens. We get this, it drops off beyond, it right around 2 standard deviations, it drops off kind of steeply. And then a little bit beyond 3, if you look at the graph, and we'll look at that in the code, it's very close to the x-axis. So, 4 or 5, hardly any scores would be 4 or 5 standard deviations away, but it's still not officially 0. And a lot of times, if you, set it as like, an upper range of like 10 standard deviations, the official would be it goes up to infinity. But even when you get up to like 10 standard deviations, that's enough for it to like demonstrate a lot of the theories. How many standard deviations, beyond the mean are we? So the calculus of this is calculating the area under the curve. So we're going to look at integrals, and then we're going to look at ranges here, given a certain standard deviation. Now this, the general simplest form of this would be a mean of 0 and a standard deviation of 1. So essentially we are exactly counting standard deviations. So 1 standard deviation, 2, 3. There we go. I could actually have, and we'll look at this in the code too, but you could have this shift wherever and have the mean be whatever actual number that would be, and then the standard deviation be a number of like, what would that be? Let's say I was giving a test that I gave to millions of people, and there is a definite average test score that could be my mean, and then the standard deviation, what would that be? If I gave it out to millions of people, what would the standard deviation be? Then, we could graph it that way, and then this would show up. The x-axis would be different, but it would show up. The mean would be somewhere on that x-axis, and then the bell curve would develop at that point. And we could see how spread out it was or narrow. So, these are the things that we can do. That works out really well to work this in the code, because we're doing a lot of this. We're going to focus not so much on the statistics, but on the calculus of it, calculating the area. Because maybe I want to find out how many standard deviations away till I get like the extreme scores. And a lot of times we talk about like the top 5% or the top 2% or the top 1%. So how many standard deviations away does that need to be? We can use calculus to figure that out, because I can use, negative infinity, or as I said, standard deviations. I could even do -10. That's actually extreme enough to demonstrate. From there up to some point, if I want that area, so if I want the top 5%, I would find some point so that from the lowest point all the way up to some point here, that the area would be 0.95. And then I know, given that, then the top would be, that's my cutoff. So beyond that would be the top 5%. So we'll look at the calculus of how we find these critical values. But really, it kind of all gets woven into this notion of, if I have enough scores, things will distribute to this. If I'm doing any sort of measurement, any scores, I'm not necessarily going to get a normal curve at all. Whatever I happen to be measuring, and especially not so many scores. Yeah, I get scatter, points wherever. But the idea is, if I have a lot, like millions, it will even out to this, which is kind of an interesting theory. So we use this a lot in statistics to say, all right, if I did this, if I have all these scores, then what's my cutoff score to say that something is, this is news, this is extreme enough for me to take notice and do something. So let's take a look at how this would play out in the code here.
Now we're going to see how calculus, statistics, and Python all interact. looking at the normal curve. So math-wise, this is the equation of the normal curve. And you notice there's a few ways you could write this. This is the most common way I usually see it. So I put it this way: 1 over the square root of 2 pi times e to the negative x squared over 2 exponent. And this is the simpler version because the mean is 0, standard deviation is 1, and with that, there's a bunch of other things that then cancel out. That's nice. This works, and really, this is the z graph. The z-score is really counting standard deviations. So that's why the mean is 0, and then we're really talking about how many standard deviations away from the mean we are. This will then illustrate all the theory with the normal curve and area under the curve and probabilities. That works out really well. And then we're going to look at the more complicated version so that I can have the mean be whatever and the standard deviation be whatever, and how that adjusts the curve and everything. So let's take a look at this. So we also notice that there's other ways I could write this. I could put the e in the numerator. This is a negative exponent. I could put all this in the denominator, but this is the usual way. And then here's how I would do this in Python code. I'll do that 1 over the square root of 2 pi, and then all that times, and remember sympy.exp is e to this exponent. So when I run this, and I said this is the normal way I see it, there's a couple other ways you might see it. This is a rare way because what Sympy did here is in the denominator, it factored out the 2, but then to make that work out here, you had to multiply by the square root of 2 over the square root of 2 to get that also in the denominator, in the numerator. Very weird. I felt like it was unnecessary. So I wanted to check something here because Sympy does do simplifying and such. So I took this equation and I wanted to multiply it by the square root of 2 over the square root of 2, seeing if I could cancel that out. And no, it didn't. So there we go. There's your normal curve, and we have it stored really as EQ. So when I plot it, now I really don't need to add this xlim, and I'm going to show you if I didn't have that, I could just plot it, and that's fine. That's nice, because this is a default built-in. Sympy works out nicely like that. There we go. And I have center at 0, 0, and there's my highest probability right there, 0.4, and you see right around, 2.5 standard deviations, it really drops off. The reason I had this in there is because I just like that proportion of setting out this limit. It just makes it a little bit more stretched out, and really it's so remember, this is the frequency distribution. So the line that this defines here is the probability, the frequency, the likelihood that this shows up. So, we're saying that right around the mean, we would expect about 40% of the scores of whatever I'm measuring. And then, the Y value here is that frequency. So how frequently do any of these scores, 1 standard deviation above the mean, 2 standard deviations above the mean, how often does that show up? And then we see, what's the frequency beyond 3 standard deviations? It's really, really low. So that's why, it just gets so low beyond that. I feel like it's nice to just cap off the graph here. But that's all. That's just, a preference for the way this displays. And this is the bell curve because, as you can see, it looks kind of like a bell. So there's your normal distribution. And again, the Y value is the frequency at any given point. And this is the theory if I get enough scores of something that I get normally distributed, then that's what we get. Most scores right around the mean of whatever I'm measuring, and the further away I get above or below, it really drops off in terms of like, frequency of how often that those scores show up. So now let's bring in the calculus, area under the curve, and we're going to take the integral, sympy.integrate, and I'm going to integrate that equation as x goes from negative infinity to infinity. And remember that sympy dot lowercase 00. So the area under the curve is exactly 1. And that's the beauty of this and why it relates to probability. Because that cumulative probability, what's the probability? The area under this whole curve, that's 1. That's every score should fit under this if it's normally distributed. But then if I have certain values here, what's the probability that if I go, from some low value, -4 or whatever, all the way up to something, what's the probability that I have scores that are within that area, that range? It's the integral, and then we just, identify our lower and upper values. So that's what we're doing here. I can, going back to that, I can say, all right, well, now lower is -1 and upper is 1. I'm going to take, the integral, lower to upper, and I'm going to do two things here because I want to show you. I'm going to print out sympy.n. So remember, I'm going to get that area. When I do the integral, it gets the area. That's going to be, you'll see it the way Sympy displays it, but I want it to be an actual number. So that's where I do the sympy.n to get that number, and I'll print that out. Then I also will show you what that exact area is, because then we'll display that too. So when I do the integral, now this is from -1 to 1, so within 1 standard deviation, above or below. And as we were talking about before with the theory, about 68% is within that range. Now, what's this look like? In Sympy, it's the error function. That's why they call this. It's the error function of this. Like, that's the actual, if we'll take a look at doing this. So the error function of root 2 over 2. That's the behind the scenes, the exact math answer. So, if I take the integral, now notice I'm just doing this again here, taking the integral, because this, remember, I gave it up here a definite value. Take the integral as x goes from here to here, in this case -1 to 1. So it gave me a definite value. But if I just take that, go back to that equation, and if I just take the integral, what the integral involving x, what is that formula? This is what it's going to give me. The error function of, and then this, root 2 over 2 times x, and then all that divided by 2. Now, if I just plot this, this is what the error function looks like. Shaded, I just took the integral, there's my error function. And now if I plot this, and again, I decide to cap it off at -5 to 5, because it, beyond that, it just continues like this. Now remember, that doesn't exactly flatten out. It gets so close to 0. That slope is never going to be 0 on either end. And remember, if this is the integral, the slope of this, the derivative is our normal curve. So we see this slope, it's actually officially positive, so close to 0, but officially positive. And then it gets to be a greater slope, and then still positive, but again, the slope still positive, but less and less, so it's like close to 0, but still positive. So we see, and I'm going to show one more thing. So right in here would be the number 1. So what's the slope here? If I go up 0.4 over 1, you see, so the slope right around here is exactly 0.4. So you see that slope. positive but close to 0, gets steeper up to about 0.4, and then less and less of a slope, still positive but 0. And that's exactly what we're seeing here. The y value of this is the slope of that. You see, positive but close to 0. These y values increase up to 0.4, decrease down to 0, or positive but close to 0. So we see, we see the connection here of these. And then what we do is, if I look at this, so back to that error function. Now, if I have that, remember, I take that and I'm going to substitute in for x Sympy. I cut the graph off here, but supposing I plug in negative infinity for x, what do we get? Negative 1/2. You see? So I probably don't even need to go down to negative infinity. Sometimes, like, maybe even like negative 10 or something, not even close to infinity, works, because it just continues and the values beyond that are so tiny. But notice then, remember, I plugged that in. So when I did that integral here to get the area, so when I plug in, when I take that integral and plug these in, Sympy.infinity, the value that's 1/2 minus a negative 1/2, and then that's where we get the 1. So that's it. The y value, see, it goes beyond 0.4. So we have like 1/2 as that value minus a negative 1/2. And then, so there we go. From when I plug that in, plug in negative infinity, the answer is negative 1/2. If I plugged in positive infinity, the answer is 1/2. So then that's where we take the, again, just coming at it from another angle, taking the integral. I'm going to go back to plugging in as negative infinity because I'm going to use this for something else here. So how can I find that critical value? So remember, I'm going to take that integral and then plug in, so that shaded is the integral. Remember, we take the integral, plug in the upper value, plug in the lower value, and you subtract them. So here's the integral with x still as a variable, and then the integral, taking the integral and then plugging in that lower value, in this case negative infinity. So that's how I would find that area from lower to upper. So that, and I'm going to set that equal to, if I want it to be 0.95. So that's what I'm going to set this equation to. So that's it. Just going back to those definite integrals. Integral, plug in the upper, lower. The upper value I don't have yet, so that's going to be shaded. That integral with x still as a variable, minus the integral plugging in that specific number, negative infinity. So there we go. That, when is that, what x value makes that equal to 0.95, and then solve it. And you see, we get these z-scores that this is a critical value, and plugging in 0.95, or maybe I have like 0.99. You see, what z-score do I need to get that level of certainty? And there we go. So maybe if you've looked at different charts of the z-scores, how do they get all these numbers? This is how they get the numbers. Given that area under the curve, what critical value do I need for that area to be 0.99? And so, and let me go back to 0.95, because that might just be easier to see on the graph, 1.64. So what this means is that then we have, right about here, when the z-score is 1.64, that means if all that area under the curve up to here, that's 95% of the area. And then this top part is the extra 5%. And a lot of things, social science research, top 5%, we're going to say that's extreme enough, that's news, and I can reject the null hypothesis. So there we go. How can I set this up so that I can, find my critical values, all this, and then the area and everything we're doing is like leading up to that. So this theory all carries over. This works out well, the z-scores. We can carry all this over to the more complex version. All right. And also notice it's still this first fraction here. Now, this is where, remember, that Greek letter sigma is the standard deviation. So you see now that works its way into our equation. Remember, the earlier example, the standard deviation was 1, so I didn't even need to write that there. And then I get that times e to this exponent. Now, if we take a look at this, so if the mean was 0, you see x minus 0 I don't need to write that in the simpler version. And the standard deviation being 1, I didn't need to write that. So then it goes back to that x squared over 2. Still a negative exponent here. So in this more complex version, then what it gives us is the ability to then put in whatever mean or standard deviation we want. And then we can see that. So I'm going to start. I imported these symbols, and I know I could have done this all in one line. I just kept it this way. I'm going to start by just showing the comparison, supposing the mean and standard deviation are 1, or the mean 0, standard deviation 1. But this is how, because of this more complex thing, just to make sure I get it right, I like to break a lot of these formulas down into parts. So I just made the denominator of that first one, standard deviation times the square root of 2 pi. And then that first exponent, you see, x minus the mean divided by the standard deviation, and then all that squared. And then exponent 2, I'm just doing Sympy.x, so it's e to this exponent, negative 0.5 times that other exponent. I just like to break that up. If I put this all in one line, it just becomes a mess of parentheses, and that's, you want to reduce the likelihood of error. So there we go. And then this one I'm just going to call bell for the bell curve. And for our examples here, I made it a different variable so that I could keep the other things for if I want to reuse that. So now what do I have? 1 over that denominator times that exponent. Because that's what I did. I made that whole denominator something, and then this. So 1 over that denominator times that exponent. And we get to this. So, first of all, really funny that it still does the same thing about factoring out that square root of 2 and putting this in the numerator. Weird. But also, just the way it happens to do it, it makes this 0.5 instead of x squared over 2, times 1/2. Okay, so we just notice the subtle differences, but this is where, in writing the code, knowing the math, you also want to be aware of when, hey, this is mathematically equivalent. It just happens to be how they're setting this out here. All right. So now when I plot this, there we go. Good. And then when I do the integral, now I plot this, and because I made the mean 0, standard deviation 1, that is exactly the same plot. We're going to go back in a second and adjust this with different mean and standard deviation, but I just want to show you that if you go to those values, it's the same plot. Now, when I do the error function, even though I made it that the mean was 0 and standard deviation 1, the error function, notice that looks very different than when I did the error function up here. You see? Very weird. Actually, it's this. This is the integral of the error function here. So it should be the same. And again, this is where we want to like take notice of where it's mathematically equivalent. Because if I take this error function, now this, if you do enough trig, you remember that this decimal here, 0.707, and it goes on and on, is exactly the square root of 2 over 2. But this part is actually just kind of funny because Sympy decides to put it like this. This weird decimal times the square root of 2. So I wanted to show you this. If I do square root of 2 times that decimal, and then I'm going to convert it to an actual just decimal number, it's exactly 0.5. So Sympy output this whole mess instead of outputting 0.5. Go figure. But notice then, if this is 0.5, and this in the parentheses is the square root of 2 over 2 times x, then we do see that it does match up with that. You see? Square root of 2 over 2 times x, and then all that divided by 2, or times 0.5. So these are some of the things, and a little bit later on in the course, I will go through some other examples too of a few things where Sympy outputs something, and then I'll show the factoring to see, hey, these two things are actually mathematically equivalent. Just Sympy has its quirks for how it outputs things. So that's fine because this is now stored as the error function, and we can use it. This works. This is just a check. So now when I do the area between values here, you see, I'm just going to set this up. Lower is error function. In this case, I'm going to say negative infinity. And the upper, well, I'm not going to, we could check this that it matches up with the other. Yeah, we could do that. If I say like 0.682, so we see, what am I doing? I'm saying from negative infinity up to here, I expect all these, I really just want to make them all numbers. So sympy.n, what's the lower, what's the upper, and I expect the probability to be about 0.95 if I do this. You see, from negative infinity to here, because I still have the 0.75. Oh, do you know why? Because I put 0 instead of 1. There we go. So yeah, from negative infinity up to here, yep, we expect that's about the right probability. I'm just rounding here. Still works the area between curves, but this is where this more complex version helps us. If we go back to this, and now if I change the mean and standard deviation, I can make them anything I want. So I don't have to convert everything to z-scores right away. I can just say, like let's say I talk about a test that I give, it would have to be a test to a lot, like millions of people for that distribution to normalize. But let's just say there's some test that's like the mean is 72 and the standard deviation's 8. So, there we go. So, one standard deviation above is 80, then 88, then 96. So, you see, somebody getting 100 is going to be more than 3 standard deviations away. Let's say that works. Now, first of all, let's take a look at how that affects this. And you see, it's not just x minus the mean. Remember, the mean is 72. And in here, this works. X x minus 72. So Sympy just wanted to like write it as x over 8 minus 9, but that works mathematically. That ends up being the same thing, because that standard deviation was 8. You see, so they just split it up, x over 8, and then 72 over 8 is 9. So again, the usefulness of being aware of the math, that, why did it show up like this? Oh, Sympy split it up into two fractions, x over 8 and 72 over 8, which then 72 over 8 is exactly 9. Another just weird, so square root of 2 pi, it brought that out. And remember, the formula was 8 out of here because it was the standard deviation. So when we brought out that, and it was a 2, then times 8 is 16. So we just see that, like, it looks weird. It's a little bit different than I would have factored it, but mathematically it's correct. And then we get that now this is that curve. Now, I want to show you one thing here. This is the old one. So if I plot this here, this is the interesting thing. So I plot this. Now, it gives me, because what I set here, I just wanted to give the x limit of where I graph it. So I put this with variables. That way I don't have to keep changing the numbers every time. But the mean, that lower x limit, the mean minus 4 standard deviations, the mean plus 4 standard deviations. And that's what it did. 72 right in here, and just over 100 is 4 standard deviations, around 44 standard deviations. That's great. I defined my x limit for what the graph should display, but it's not there. This is a subtle difference, and we'll also look at like even more Sympy knowledge in a little while. But if I wanted to find the x values, I have to go this way. So graph that bell, and then in parentheses x, comma, and I don't want x limit. I want it to look like this, and then make sure I close that outer parentheses. So we see this is the way I want to do it. So just to be aware, if you do it the other way, the way you would limit just what the graph displays, that still might not change the x values that it displays. And so then you get this blank graph, and you're like, what happened? It displayed what I wanted it to, but here I'm saying plot it, and I just want my x value to go from here to here, and then the graph will actually display accordingly, so it'll be fine. So you see here, also the maximum here ended up being 0.05, but that's okay. But we see it still put that vertical axis line in the middle, but right at where that mean is. There's that mean 72, and then we see the standard deviations. So this is really what I would want. I would want to see, okay, mean, standard deviation, what's that bell curve look like? Great. And then, so this is what we have. I can keep this, change the mean and standard deviation, see what that equation looks like, see what the graph looks like, and if I do the integral of that, now, definitely it's, a huge mess, and I'm not even going to try to decode all these. It may or may not help at anything. So this, we just did that check before. I don't even need to do that again. But now that I have that, now let's talk about the area between values. So now, if I have from negative infinity up to, So let's say 2 standard deviations. So from 72 to 80 is 1. From 88, let's just type in 88 here and see, what's the probability, if 88's the score, now I can plug in that exact value. And we see the probability is 0.97. All these upper and lower, they're like my in-between values as a way of checking, because this is really like the y value of that error function. And of course, the lower you see is negative 0.5. But then the probability is 97%. So this is where we can figure out, percentiles. Oh, you scored an 88 on this test. You're in the 97th percentile, or almost 98th, really. And then it should be that if you scored an 80, that should be exactly 1 standard deviation. You should be about the 84th percentile, because remember, it's 50th, and then 1 standard deviation, it's another 34%. Remember, it still goes back to that normal curve logic here of 34% between the 1 standard deviation and the mean, 34%. So yep, so then you scored an 80, you're in the 84th percentile. And then we could then say, 2, that little bit more than 2, 88, was it 2.3? 90 should be in like the 90th percentile. Now, I'm just, showing you that you can test a few different values here. Look at that 98th percentile, almost 99th. But you don't need to do this trial and error. I just want to show you that you can, plug in whatever values, and that doesn't even have to start at negative infinity. You can say, whatever values, whatever lower and upper amount, because it should be that from 72, so 1 standard deviation below, remember the standard deviation was 8, so it'd be 64 up to 80. So 64 up to 80, and we would expect that to be like 68% score within that, because then that's 1 standard deviation above and below. And again, you don't have to do the trial and error, because we're going to get to that in a second, but you can if you have a question about how many scored within this range. This is where you would plug that in. And a lot of situations come up where you want to do that. How many score exactly within this range? Now I have that. Whatever my mean and standard deviation, I can plug in whatever score ranges I want, lower and upper, and, again, just outputting these out of curiosity, but this is really the probability that we're looking for. So how do I find that critical value? So just like we were doing with that simpler version, but now I have this here, that error function, substitute the, from negative infinity. And if I want to find out where is that cutoff from 95th percentile, I'm going to do that same thing. That error function is the integral, because we already did that. That integral minus, this one is the integral plugged in that lower value. Set that equal to 0.95 and then solve it. So 85%. So, for whatever I'd want to do, if there's like a cutoff, there we go, 85%. So, we could do this, 99. There you go, 90.6%. So now I have that for whatever score, however I score this test, and it can be, scores with, it doesn't even have to be bounded by 100. It can be however I decide that I'm scoring this. Once I get the mean and the standard deviation, I can set up that and, area between two different values, your probability to fall within that range, what is the critical value given, the probability that I want. There we go. And then notice I can check this. So once I got this, I have lower, and then notice I didn't even call it negative infinity. I just called it negative 10. That's actually probably going to be close enough. And then step 2, this is the answer here, so I'll just make that the upper because that's really what we just solved for. And then if I take the integral, 70 root 2. Let's try this here. And let's print sympy.n. So we see, yeah, that's great, but and what this shows us then is I went up here and said, what's the cutoff for it to be in the in the 99th percentile? Oh, a score of 90 or 90.61 actually. So then I'm going to just take that 90.61 as my upper, and then look at that. It says that yes, if I go from there to there, that is the the area under that curve is exactly 99%. And like I said, you can still do it to the negative infinity, but it levels off so much there that even negative 10, you're beyond, significant changes there. And then there we go. So there we go. I just had it here of like area and then probability to do it again. Yep. Pretty cool. So there we go. We see how we have this formula that defines this normal curve, and we can plug in any mean, any standard deviation, define the normal curve, plot it, get the error function, which is the integral, and I can use that to figure out, probability from that any score falls within a range, or if I want to know what probability, then I can solve it. What's my cutoff score for that probability? And there we go. Calculus explaining statistics and being able to write it all with Python code. So you can set this up that if you're setting this up for yourself, you can keep this, and all you have to do is change the mean and standard deviation. And this, you don't have to change anything, so you can see the plot. And each of these, you just might run this one. You don't need to, that was just a check. And you can keep this, and then you can keep this for the critical value. You can keep this other check if you wanted to. And there we go. All these fundamental questions in statistics you can answer. You set it all up, and now you know what this means, and you can answer it, change a couple values, and decide whether to reject the null hypothesis.
We've been looking at a lot of different default Sympy plots. Nice, easy, you could just Sympy.plot the equation. And that's great in its simplicity, but what if you want to add something to the graph, change it, modify it, really focus on particular X values or Y values, or add a point to the graph, and all these other things. So we're going to look at all these things that are already just set by default that you don't have to use. But what if you do want to use them? We're going to look at all these different attributes that you can use and see, some ways you can really make use of these for certain graphs that it's going to really benefit you, that you can say, oh, I want to focus on this part of the graph, or I want to add this to it, or I want to change this. And we're going to look at how you can do that in the Sympy plot. So let's take a look at the code.
So let's look at all the other options that are available when you do sympy.plot. And we were been talking about plotting, just you can just plot the equation and call it good. But all these things, this is from the documentation, when you plot, these are all the arguments that are available. And let's go through these here. So, these global options, you can put a title. And so notice the setup of this: args, comma, title equals, x label equals. You can go through and have as many or as few of these as you would like. So the title, string, pretty straightforward. You can put a title to your graph. X label, string or symbol, because if you have X and Y as your symbols, then you can just make that the label as well. So that's why. Or string, you can put a letter or word in there for your X label and Y label. Z label, in the near future, we're looking at our two-dimensional graphs, so just to know that that's possible. The legend and Boolean, true or false, and for one line, you might not need the legend, you might not want it, but multiple lines, that might be useful, especially, different color lines, and then it really spells out which color line is which function. For the X scale, the Y scale, the default's linear. That's just my go-to. You can make it a logarithmic scale, and maybe there's some situations where that's going to help you, but just to know that you can change that scale and do anything. Axis is a Boolean. You can turn the axis off. Maybe that suits your graph a little bit better. You just want to see the shape. The axis center, and it normally would be auto, but you could make this a tuple, and you can put the center of where you want the axis or the graph to be, move it around. And again, it enables you to focus in on different parts of the graph. So it's one I don't use that often, but it's useful to focus on different parts of the graph. The X lim and Y lim, especially the X, that's a big one, and we'll demonstrate this because I might want to have a graph that, maybe a lot happens like right around X equals, plus or minus some low number, but then some part of the graph causes it to be zoomed out, and maybe I just want to limit that. So that just, limits the X, or you might want to limit the Y. Again, different reasons why you might want to focus on one part of the graph, and we'll look at how we can make that happen. Same with aspect ratio. Again, I could change this. One of the things that I like with the aspect ratio, and we'll look at this, is Python tends to elongate the graph and make it a little bit more of a rectangle and not a square. But if I want to graph something that's a circle, I might want that aspect ratio. We'll look at that. Auto scale. Now, if you change that to not auto scale it, then you also have to include another argument for what you want that scale to be. You have enough other things you can change that I like to have auto scale, just the default. Margins, again, the default's nice, but maybe you want to print this or save it, that graph as an image, in which case you might want more of a margin. The back end is going to be Matplot library, so this is next level. I don't feel like you need to tinker with this. Size of the graph also. Again, maybe the size of the graph, the margins, depending on if you want to do something else with it. Annotations. This one, I don't use very much as far as annotations for each of the points that tends to be too crowded. Markers I do use, and again, you'll see the default would be none, but this is everything except for, well, you would keep these braces, notice square brackets, curly braces within that, and then I keep that args colon, and then here's what I'd put in again, square brackets within that. Some X value, some Y value, and then in these single quotes, a color and some indicator of what the dot would be. So this is good because it's going to plot a point on that graph. Maybe I have this graph and maybe I want to highlight, here's a particular point on the graph. I'd have the XY value of that point. Now in this case, this is a red triangle. You could do the star and it'd be a red star. RGB are the go-to, red, green, blue, star, triangle. If I just put an O, lowercase o, then that would be a circle. So some good markers. We'll look at some examples of these. Rectangles, kind of an experimental feature. We're not going to worry about that. Fill. This is pretty cool, and we're going to see a good example of this. Your usual default's none, but you can fill the graph. And more than just changing this, we'll look at some other code that you'd want to include before you do this. Backend default, there we go. So let's see some examples of this. This is our normal, I'll just import all these Sympy, and then here's my equation. There you go, x squared minus 3. Okay, so one of the good things, you can just keep all the defaults and just plot that. There's my equation, plot it, boom. There we go. Nice. All right, and we see where it's centered. It looks nice, proportional. There's a lot of things. Sympy knows where the center of the graph is, and a lot of that's going to be your go-to. Let's just see what this looks like. All right, now here's what the plot would look like with all the options, but notice I kept all the defaults here. So this, what am I plotting? I'm plotting that equation. That's that first argument. We do need that. All the rest are optional, but this is just keeping all of them in there. And, there we go with all the default options. And when I run this, that's going to be exactly the same graph. So we can do this we can just simply plot EQ without all the rest of this, and it's the same. Now, let's start modifying this. Like the title, I could put the title in here, or I could make it another variable and then put it up here. A lot of times it's future convenient for separating out this variable and putting it here. So there we go. Let's say I add this title. There we go, some graph. And X labels, now, just because I want them to be X and Y, I showed you, here's another way. I can just put it right in here. X label equals X, Y equals Y, that's fine. And this works with one quote, single quotes, or double quotes. Z label, I'm not worried about it. Aspect ratio, we're keeping the same. X lim, we'll come back and change this, but I want to show you that for right now, we're going to leave that. Leave most of these. I just want to show a few at a time here. And then here's the markers. Now, you can plot any point you want, but it helps if you pick one that's on the line. So I just picked, there's markers, and then, here's the brackets and everything you need, args. So for our equation, if x is 3, y is 6, that'll be on the line, and it's going to be a red circle for the point. And all the rest of these, I kept the defaults. So let's just mark a few things. So we see the title shows up at the top. X and Y. There we go. And then here's our one point on the line. I also made the legend true instead of false. So this is the legend here. You see it shows x squared minus 3, and that's our blue line. So that's nice. And then I can go and let's change some things here. So the x lim, let's just make it, so square brackets, and I'm going to make it from like -4 to 4. Now, I don't need to change the y limb. I can, but I don't need to. Watch what happens when I do that, though. You see, it looks really stretched out because I didn't change the y limb. And since I defined this point based on coordinates, that's still on the graph, because I didn't change the y limit. So if I did, because look at this point here, it really, it's not very high up, so this is kind of wasted. So if I do then decide to change the y limb, and maybe I'll make that like -1. I want to see a little bit below the axis instead of -1, -5. Remember, this is like your like ongoing workbook here. So, you're solving some things. You want to decide how you want to graph this, how you want to display it, maybe to save it for something else. And, you say, okay, I changed this. Great. Oh, but then I changed that axis. And then now, this is all nice and zoomed in, where we see like that demonstrates this nicely enough. But now we can make some things, I want to zoom in on this part where, maybe I want to see a better look at where this crosses the x-axis here, or some other things. So, that's really where x limb and y limb help you. I could turn the axis off and just see the graph. For a lot of things that I like to do, that doesn't help as much. Annotations, the markers, good. So all these different things that we can do, I want to get into the one more thing that we can do, and this was the shading, and up here that goes into fill, which right here we have none. Where am I going to very often want to fill is if I have, you might recognize this equation, that's my normal distribution. So let's say I have this as my equation, and I just called this F because I used EQ up there, and we'll just keep that. So there's my normal curve, and you can connect all this with other code you already wrote. I just picked a value here just to put this here. But remember, you could have whatever else you did to find that critical value, whether it be the integral or other things. And this is, like I said, what other things you need to do if you're going to shade or fill under the graph. I needed to incorporate some NumPy stuff because I need this array. There we go. So I just, knowing this, I picked the lower value of -4, knowing that anything negative beyond that, you're not even going to notice it. So np.linspace, there we go. I'm going to set up this array from -4 up to that critical x value, and I want 1,000 points here. So there you go. There's this array, this x array, and then this other twist. If f is my function, my f array, I've been dealing with Sympy stuff, but now I need to lambdify this so that I can get these y values here. So Sympy.lambdify for the variable x in function f across this x array. So that's kind of the thing, here we go. We have Sympy.xArray, and then I'm going to plot that function. There we go, my normal curve. And then x, remember not x lim, I really want those x values. And actually from -4, let's do that, up to, now that's, that's nice. It actually, Sympy.py works out just as well, but let's go up to 4 here. So I'm plotting this, f function as across these x values. Now this is Sympy plotting it. But now when I do the fill equals, this is now all that I set up here. Now this is what I have, fill. For my x value, I'm going to use x array. For my y value, I'm going to use this f array. So it's filling in all those values. And then on color, I'm going to say blue just because I like blue. So all that goes in the curly braces for the fill. And then when I fill it, now we really get that there's my normal curve, here's my critical value, and I've shaded everything up to that value. Good times. So these are so many of the different modifications you can do to a Sympy graph, and as you see all the different parameters you could add to it, tinker with some things, but I wanted to highlight some of the ones that I feel like are the most useful going forward, especially relating to some of the stuff we've been doing in calculus.
Let's talk about arc length, which is the length along this curve here. So, not really the y value, not the total y value, it's the length along the curve. So, I could have an even parabola here, and if I just talk about y values, maybe I end up at the same y value. That's no good. I want the length if I were to actually draw along here, along this curve. There we go. If my curve was a full semicircle, then I could even do geometry to figure out that. But what happens if I have some curve, any curve, how do I get this length here? And let's think about this and kind of the distance formula on a really small scale. This would be magnified on a really small scale here. So in whatever these xy values are, then what's my length here? It would be dx. And then what's my length here? That would be dy. And we'll do like a squared plus b squared equals c squared. We'll call this c. Then, what do I have here? So just like I have, a squared plus b squared equals c squared, then what do I have? I have dx squared plus dy squared equals c squared. And if I take the square root, there we go. Now, that works. That's nice, especially if I have definite values here. But let's talk about the notation and link this up with calculus notation. And notice we were talking about, slope as dy over dx, derivative. We were talking about the rectangles, dy times dx for the area, integrals. And now we have dy dx, Pythagorean theorem. Are we going to use derivatives or integrals? We're going to end up using both. So let's just talk about a little bit of notation here. Then if I have, so this is my distance here. So if I take this and underneath this square root, if I multiply everything by dx squared, I'll move this over here, so multiply everything under this square root by dx squared over dx squared. There we go. So distribute this. Now, times 1, I didn't change the problem. But if I do this, so now I have, this would be, I'll leave this out here. So that's going to be dx squared times dx squared, that denominator distributed becomes 1. Dx squared over dx squared is 1. And then over here, it becomes dy dx squared. So we see the distance here. And now if I leave that out here, under the square root, that comes out. And so what I'm going to write it as is the square root of 1 plus dy dx squared, all that times dx on the outside. And remember, we're adding these up, so it becomes the integral of this from whatever points here, from A to B. So then I get this, integral and derivative. So the dy dx is exactly the derivative. So when whatever equation I get to define this line, then, I'll square it. I'll take the derivative of that and then square it. And then add 1, then square root, and I'm doing the integral. So what's interesting is, if it wasn't for this plus 1, then I would have the square root would cancel, derivative, integral would cancel, but it's not going to be that easy. It's plus 1 in here. But we're not just like putting the plus 1 to like make your life more difficult. The plus 1 comes from the fact that it is Pythagorean theorem, and then this little factoring trick here to get this, like, that's really where the plus 1 comes from here. But that's where we get, this is nice, because we bring in integrals, derivatives, Pythagorean theorem, all good. Now, the good news, since we're going to be talking about doing this in code, if you were doing this like the factoring way, it ends up being this plus 1 really throws it off, and you're like, oh, I could have factored it, it's so close, I can't. It gets frustrating sometimes. Some things work out nicely, some things don't. Writing it in the code, hey, we could set this up and it'll work out, because Sympy will do that solving for us. So that's really the nice advantage of doing everything in the code. A lot of things that would take a long time with factoring, is one line of code and it'll happen right away. So there we go. That's what we get that's how we get the integral and the derivative is that whatever that original function is, then the derivative squared plus 1, square root of that, and then the integral. And then we get the arc length, the length along that line. So let's take a look at how to do this with code.
So with arc length, as with some of the other formulas, once we know the formula, we can just put it in code and set this up for future use. So all my usual imports, and I'm going to use this range here because I'm going to use this equation, Sympy square root 9 minus x squared. And I'm using this because I'm picturing this as a part of a circle, 1/4 of a circle there in the first quadrant as x goes from 0 to 3. And that way, in the back of my mind, I can think about the geometry way to get this arc length and see if this works out, So there we go. There's my equation. So what do I want to do? Remember that arc length formula. I first of all want the derivative. And I'm not plugging anything in yet. So I'm just going to put that there. The derivative, DER. And I want the square root of the derivative squared plus 1. And I like to put this in, 2 steps here. So it just works out. So there we go. So the derivative, and remember it's the square root of the derivative squared plus 1. I'll just call that equation 2 now. Because now, for arc length, and I'll just make that my variable. It's good to have variables that, make sense. Sympy to integrate, I want to integrate equation 2 from here to here. And like a lot of things I do with Sympy, I do want to see this answer, so I'm going to have it print out arc length here. And I also have this, that I want it to be Sympy.n arc length. One of the other things that you can do is you can put this n first, and then you can just have this as the last line, arc length. Because if it's the last line, not even within a print statement or anything, it'll display nicely here. So if we run this, then there we go. And you see, just to compare the different outputs here. All right, this is nice, and that tells me what I want to know. This is the decimal answer that I wanted. And also, this is the Sympy answer that I wanted. The exact answer, 3 pi over 2. Formatted nicely. So a lot of these, remember, you're using these as your calculator to give you information that you might need for something else. So, hey, have it output all the different versions of the answer. Which one do you want to use? So there we go. So there's arc length. And then I can have the arc length, now all I want to do is, supposing I have the arc length of, any other formula, x squared. And here, maybe I'll make it, from like -3 to 3. So all along that parabola. Now here, we might not see any, very interesting how it prints out here. But this is it. So what this is this is the arc hyperbolic sine of 6. But again, you see the exact answer formatted and the decimal answer, which may often be what you want.
If I want to calculate the surface area of a shape that I'm revolving around the x-axis, so I drew this as if it were like y equals x squared. That way it has that curve to it constantly, complex enough that we can illustrate the point here. So if I'm revolving this around, and remember when we were working with volume, we imagined slicing this. So what am I doing with these here if I want surface area? Well, we have to think about the surface area of a cylinder. So supposing I had a cylinder, and all of these, I'm going to picture cylinders on the side. So if I have a cylinder, then how do I get the surface area of this? I can imagine this as like a can with a label, that if I were to unroll it, that label is a rectangle. So, yes, this is right from the horse's mouth, I'm telling you. So how do I get the area of that rectangle? All right, well, then it was going around in the circle. So then I have the circumference of that is the length of my rectangle. And then the height is still the height of my rectangle. So there we go. So if I have these rectangles here, or these, so it was rectangles when we were doing area, and then we're slicing to make discs when we're doing volume, and now with surface area, it's picturing the label of a can as I'm unrolling this here. So, all these on the side, unroll it to make a can. So what's the setup here? I'm slicing it this way, and so if I have the surface area, so it's 2 pi r, so that's my circumference, 2 pi r, and then times, now since it's on an angle here, it's kind of like if we were doing the surface area of a cone or something like that. I can't just say the height because that would be misleading. My height is going to get me dx, but I need that angle here. And in geometry, at times we call it L with a little cursive L as that slant height, because that's what we have here. Then 2 pi r is my circumference, but then I want that slant height. Well, in calculus, what's that slant height then? So if I have I have my surface area here, so it's 2 pi, and what's the radius? It's my y value at any given point. And then what's this slant height here? Arc length. So then the arc length would be, remember, the square root of 1 plus the derivative squared. So it's the integral of this dx. So that's where we get this. And it's the integral of all this. So we would put the y value here. I would put the integral symbol here. I could put it right at the beginning, but actually that works out mathematically. Any constant I can bring out to the other side of the integral. So we get to this, that's where we get our slant height, our slant length here is our arc length. So then I have 2 pi times that y value at any given point, so that becomes the radius, and then times the arc length here. And remember, it's that formula here. Remember, kind of like Pythagorean theorem. So then if I'm doing this in the code, which we're going to look at in a second, then once I define my y value, I'll set up a couple other steps. I'll take the derivative, I'll get the arc length and the arc length formula, and then I'll take it from there. But we see like the setup of this, where does this come from? It's, if I want this and I'm revolving this around the x-axis, there, 2 pi times the radius, which is my y value, and then that slant length, because if I just called it dx and eliminated this, that's going to be not the exact answer. It's too much of an approximation because it's tilted, it's not just flat. No matter how small I chop up these slices here. So I have to do arc length, so 2 pi times the y value for the radius times the arc length for this, and then when I take that integral from, my x value from where to where, then I can get the surface area. So now that we can picture this, get a handle on it, let's take a look at how to do all this in the code.
Now, looking at the code for this with surface area, remember that, now we have this set up. What do we want? We want that arc length times the circumference. So I'm going to just set this up so we can use this, my lower bound and upper bound. I just decided to pick these. And arc length times the circumference. So we need to get that equation, and I just put this here. We'll use that x squared. And remember, the y value is the radius. We're revolving this around the x-axis. So now I want that arc length equation. We'll call back to this. There we go. I'm going to take the derivative of this, and then I'll just say that as the variable der, because then I want the square root of, remember the arc length equation, the square root of the derivative squared plus 1. And I'll just call that equation 2 because we're building on this. And then, so take the derivative, use that square root of the derivative squared plus 1, and then now surface area, we're going to take the integral of that. And remember, the surface area is just like the surface area of any cylinder. And remember, we're doing all these cylinders. So 2 pi times the radius, so that's the circumference, times the arc length. And remember, because it's not like a direct dx, as if I were doing slices, it's the arc length, it's the surface around it. So 2 pi times the radius times the arc length. So we did this, and we're going to take the integral of that. So 2 pi times the radius, which is equation 1. That equation defines the radius, times the arc length, which we've built here as equation 2. So now that's our full thing, and we're going to take the integral of that as x goes from that lower bound to upper bound. And there we go. So now, once you picture it, we worked that out on the marker board. Now we know that formula. We're just going to put that in. There we go. This is what it is, and then we match up everything that we have here, revolving it around the x-axis. So I'm going to do a couple things here. This is the main answer that I want. I want that numerical answer. So we got the surface area, and then I'm just going to convert it to a numerical answer. But I'm going to put these other two things in here. This is if I just use the print statement and then just do surface area, we'll see how that how Sympy displays that. And then after all that, and this would have to be the last line of code, this is just the exact answer as Sympy interprets it. Yes. So I just wanted to show you these as comparison. This and the way this displays it, and this, which actually I guess would count as the exact answer because we're not rounding anything. We're leaving square roots and arc sine and everything. But this is going to be the most practical answer that we want. There you go. So you have this set up that anytime you use surface area, really, if you say at the lower bound and upper bound, and then what's that equation that defines that, revolved around the x-axis, y value is the radius, get that equation that defines that boundary, lower bound and upper bound, and calculate surface area.
Now we're going to look at how we match up some of the Sympy outputs to the trig integrals on the table, just in case you say, wait, they don't match up. What can I do? So let's take a look at how we can do some factoring to match these up.
So Sympy will do the integral for you and the factoring. So you're not going to have to go through and memorize these. A lot of calc textbooks will have a table of, I don't know, maybe even 100 basic integral formulas. Sympy will do that for you. And that's what's great. But some of the output from Sympy won't match up with what you expect. Now, some of these more basic integrals, yeah, it's going to give you what you expect. Power rule, your Sympy output, you're going to recognize that, no problem. du over u, so we have u could be x or it could be some other inner function. Integral is the natural log, things like that. e to the x equals e to the x, e to the u. Some of these you're going to be okay. Integral of sine and cosine, that's great. And then you get down to some of these, but some of the trig stuff, it's like a simple factoring substitution. But what I'm going to look at is a few of these where you might remember, a derivative of tangent is secant squared. So when I do the integral, it goes back. Integral of secant squared is tangent. And then we go, integral of cosecant squared is negative cotangent. Integral of secant tangent. So these few are just the direct, opposite of the derivative formulas that we remembered. But the way Sympy will do that, especially because of the inverse functions or even tangent, we'll look at how the integral is going to be, it'll say sine over cosine instead of tangent. Or cotangent will be cosine over sine. Secant will say 1 over cosine. And then we need to do those trig substitutions. So we'll look at a few of those. Some of these then, integral of tangent, integral of cotangent, it becomes something totally different. And we might need to do a couple more steps of substitution. And then that's what we'll look at. Now, the integral of tangent is what we're doing. So we didn't do a derivative formula that matches up with the integral of tangent. In this case, now log, remember, this is base e, not the common log base 10. So negative log of the cosine of x. Now our table of integrals says that the integral of tangent should be the natural log of the absolute value of the secant. So let's see how those two will match up.
So when the table says it should be the natural log of the secant, absolute value of the secant, and Sympy says negative log of the cosine, are these the same? Yes. So let's do one thing. Let's move the negative here. Remember our logarithm rules. The negative here becomes an exponent here. So what's cosine to the negative 1 exponent? So that's the reciprocal. So that becomes the log of 1 over cosine, which is secant. Remember, natural log or log, Sympy uses log meaning natural log. So that is the same. Sympy saying log is the natural log. And how do we account then for the absolute value? That's kind of a formality because it can't, if it's logarithm, it can't be negative anyway. So, writing the absolute value just kind of like highlights that. But there we go. Moving the exponent and then rewriting 1 over cosine as secant. We see how they match up.
And we get down to some of these. The integrals of these would be, arcsine, arctangent, arcsecant, integral of sine squared. We have secant squared, and the integral of that should be tangent, but its output is sine over cosine. And we're going to say, oh, sine over cosine is tangent, and we see how that matches up. And I put the negative here, so the integral of negative cosecant squared is cotangent. Again, cosine over sine, trig substitution. So we're going to say that matches up. Secant tangent, 1 over cosine. Well, that's secant. Derivative of secant is secant tangent. I also put in here that, we have, that we can take the derivative if we want. You see, I can check this. Oh, I output the integral here. What is the derivative of that? Again, the way Sympy wants to put it there, sine over cosine squared. Sine over cosine is tangent, and times 1 over cosine is secant. So that would be secant tangent. It gets back to it. So here's where we get to tangent. Sympy says the integral of cotangent should be the log of the sine of x. Sympy says the integral of the secant of x should be this mess. And the table says the integral of secant is the natural log of secant plus tangent.
So how does the table say natural log of secant plus tangent, yet Sympy outputs this? And how could we say that these are the same? Well, the only way to show it is to dive into the factoring. Let's remember our exponent rules for logarithms, that 2 and that negative there. So I'll just bring this here as negative 1/2 times the log of the sine of x minus 1. And then this one, that 2 denominator becomes 1/2 times the log of the sine of x plus 1. And then that multiplier becomes the exponent. So without rewriting all this, I'm just going to move that. That goes to the negative 1/2. And then this one goes to the 1/2. And other logarithm rules. If I'm adding, what am I doing with these logarithms? I'm multiplying them. So this becomes 1 logarithm. And since the 1/2 is the square root, and negative would put this in the denominator, so when I multiply them, it becomes the square root of this sine of x plus 1 over this, which is the sine of x minus 1. And it looks like we're not necessarily getting any closer, but we will. So can I multiply this times something to factor this square root differently? Yes, I can. So I'm just going to put a little side project up here that the sine of x minus 1 times the sine of x plus 1 equals sine squared x minus 1. And we remember that that sine squared is cosine squared. Sine squared minus 1 is cosine squared. So that could become cosine squared, which under the square root gets factored out as cosine. We'll come back to that in a second. So what about this? Let me move this up. So if I have this, let's, within the square root, multiply by that sine of x plus 1 over itself. So I didn't change any of the values. I multiplied by 1. It's just this over this, anything over itself. But then in that denominator, I have this. Sine minus 1, sine plus 1 becomes sine squared minus 1. And remember Pythagorean identity, that becomes cosine squared. Now that's underneath the square root. So then it becomes the log of, it was still in the denominator though, but that's what cosine in the denominator then becomes secant, not in the denominator. So now that I factored that out, I have this, which becomes sine of x plus 1 squared. And you see, since it's the same thing squared, square root, so then I can simplify this. And if we distribute this, secant times sine plus 1, it becomes the log of, so secant, maybe I will write this back as 1 over cosine, because that's going to, when I distribute that, becomes sine over cosine, which is tangent, and then plus 1, I think I will write that one back as secant. And remember, Sympy writes log, but they mean natural log. And then because it's log, the absolute value is implied because you couldn't get a negative number from that. So we really can factor all this and get it down to the natural log of secant plus tangent.
Sympy says the integral of the cosecant of x should be this mess. And the table says the integral of cosecant is the natural log of cosecant minus cotangent.
So after doing something like this with secant, cosecant, you've got this. So the table says that the integral should be natural log of cosecant x minus cotangent of x, yet Sympy outputs this wacky logarithm. So we're going to go through some more drill that all this over 2 is a 1/2 multiplier. So it's 1/2 times the natural times the log, which also remember, Sympy calls it log, but it's natural log. The log of cosine of x minus 1 minus, and then we'll bring that up there, 1/2 times the log of cosine x plus 1. So then I'll make this our exponent again. That 1/2 becomes 1/2 as an exponent. And then I'll leave this minus here in the formula, and then I'll just put the 1/2. So when I'm subtracting logarithms, I divide. So then it just reminds me that that goes in the denominator. So it's the log of the square root of this, cosine x minus 1, over this, cosine of x plus 1. And we remember our side project here. cosine of x plus 1. If I did this, cosine of x plus 1 times cosine of x minus 1. So if I multiplied that whole denominator by this, then that would end up being cosine squared minus 1. And then remember our Pythagorean identity, that's really sine squared. So then sine squared, but it's in the denominator, I'll bring that out. Let's move all this up. So we'll keep this step to show then that under the square root, I just multiplied by the same thing over itself. So it's like times 1. And then down here in the denominator, then that's going to cancel out the sine squared, which will factor out. And then up here, then that's the same thing squared. So then I get the log of sine squared in the denominator. So I'll write it like this, 1 over sine squared. And then this is this same thing, cosine of x minus 1 squared, because now it shows up twice, but then square root, so then that cancels out. That squared square root is cosine of x minus 1. And when I distribute this, oh, this was sine, don't mind me, because it was sine squared under the square root. So now when I distribute this, it becomes the log of cosine over sine, which is cotangent, and then minus 1 over sine, which is cosecant. And that should work, cotangent minus cosecant, because if I subtract them in the different order, I'll get the same number, but it'll be negative. But I know that only the absolute value is going to work. And that is the same. I just checked. So given the absolute value. So we see a few of these that we can factor, and there's a few that then even built into the code, Colab or Sympy, the library, will factor some of the other ones. And you can see that, yes, Sympy is not going to steer you wrong. It'll just give you a little bit different version sometimes that we can factor in and get the answer.